Welcome everyone. I'm Sergio Casas. I'm the tech lead manager of our perception and behavior reasoning team here at Waabi. So Waabi, for those of you that don't know, it's a 3-year-old company focused on self-driving trucks. And yeah, we've prepared this tutorial with a lot of effort. It's a full day tutorial. It's very comprehensive beyond autonomy as it's typically perceived by computer vision people, like kind of just from sensor to the plan, but there's a lot more to self-driving that we will be covering today. So last year, we did it in Vancouver as well. And we thought it was a huge success based on the positive feedback from people. So I'd like to do a very quick show of hands. Can you raise your hand if you were there last year and you are a repeat, basically? Okay, awesome. Almost no one then, which is great. I think this tutorial is anyway meant for kind of everyone, whether you are an expert in self-driving in some specific area and you want to learn more about other areas, or maybe just getting started and just want to know more about the field. This is great for you. Hopefully, if you are on the second bucket, this will motivate you to do like a PhD on self-driving or maybe join a company like ours. So I actually think it's a great timing to join self-driving, like the efforts towards self-driving based on where we are with AI today and the rapid progress in the last couple of years. And today, I actually have some great news to announce. I'm sure Raquel Hurtasun, our CEO, would love to announce them herself, and she loves this conference. She would really like to be here, but you can understand she's been really, really busy raising this Series B that we just announced this morning. So this is huge for us. It will enable us to do driverless trucks next year. And you have the link there if you're curious to read more. And there's also this other blog post written by Raquel herself that was also released today. You have the QR code there. I'll leave it a couple seconds in case you're interested, but it talks a bit more about the vision of the company and kind of the next steps of that company. There's a very long 15 minutes video that I won't be playing, of course, in this intro, but it's very cool. So go watch it later. I'll play now this video. This is now about a year old, but I think it still summarizes pretty well what we do at Waabi and in a short amount of time.
The future of trucking is autonomous. That means safer roads, a stronger supply chain, a new era of logistics. At Waabi, we believe that to unlock this new era, we need to build the next generation of technology. Meet the Waabi Driver. Powered by our AI-first approach, the Waabi Driver is ready for trucking now. Let's take a closer look. The Waabi Driver has two components: the Advanced Virtual Driver as software, together with sensors and compute as hardware. It includes LiDARs, cameras, and radars for increased redundancy and safety. At its core, the Waabi Driver is a full autonomy stack. From sensing the world to decision-making, the entire system as a whole automatically learns from data. Thanks to Waabi World, our groundbreaking simulator, we're able to expose the Waabi Driver to the vast diversity of experiences needed to hone its driving skills, which would be impossible otherwise. This makes it safer and smarter before the wheels even start turning. The Waabi Driver is a single AI system that is both modular and interpretable, which means we can trace every choice it makes and we can validate its decisions. The Waabi Driver has superior generalization capabilities. It can apply learned skills to new situations and geographies it has never seen before, unlocking new autonomous routes with unprecedented speed. We built the Waabi Driver with production intent from day one. It's designed to be easily integrated on the assembly line for a safe, reliable, and scalable product. And it's highly flexible, adaptable to multiple redundant truck platforms and sensor configurations. We are unveiling a new paradigm, safe, scalable, and ready for the road. The future of trucking is autonomous. The future of trucking is here.
But hopefully you could hear another room. But yeah, since then, this video was has more than 1 year now. Since then, we've actually been driving on public roads in autonomy for last year in Texas, actually. And we've also been regularly delivering loads for our customers, including some of the largest shippers in North America. So now we'll go a bit more into kind of autonomy for a bit. I'll talk a bit about Waabi's approach, and one of our latest, I'll do a quick, I guess, reveal of one of the papers we have at CVPR, and then we'll move on to the tutorial topics. And the tutorial is more an unbiased view of the field rather than our work. We just basically introducing our company in this introduction. So autonomy stack, we have sensors at the very beginning. We use basically different sensors like camera, LiDAR, radar, which is really great to have redundancy, and they have their pros and cons, as we'll see in later parts of the presentation. It's also a good thing that for tracking, the economics work a lot better, so you can put a very high quality sensors on that truck compared to, like, let's say, passenger vehicle. We also believe high definition maps still have a lot of value. And even though they cannot be trusted 100% of the time, and you need to understand when the map has changed, it's still a very strong prior for the different tasks in this stack. By the way, this overview, I want you to think more about these modules at a kind of more high-level capabilities rather than actual modules that are cascading. We'll get later more into the different paradigms for autonomy, but here I'm talking more at a high level what a basically self-driving vehicle needs to reason about. So it needs to do perception to some degree, and typically that's done with detections and tracks, meaning that we are trying to essentially see where the other agents are in the road, kind of maybe their kinematic state a bit, the history, so that then later on we can actually understand what they might do in the future. This is very important because we actually don't know for certain what other agents are going to do. So we need to be very smart about how we understand our uncertainty about the world and how we can then plan a safe maneuver around these vehicles. And finally, that maneuver or that trajectory that we plan needs to also be executable by a controller, and basically the vehicle being able to follow the actuator commands. So you might be thinking, we've been doing research as a community in self-driving for about 2 decades now, and self-driving are not still widely deployed out there. Why is that? So self-driving is actually a very hard problem because most of the time it's very easy, and that has been solved already. And many companies have products that can drive most of the time in supervised autonomy, where there's a driver kind of without that safety driver, without touching the wheel. And most of the times the system is driving autonomously. But there are certain cases that are very hard. Here you have some images. There are some animals like elephants and a bear there. The second image is actually very dear to our hearts. The very, very first time we engaged in autonomy in Texas, we saw that vehicle with the house. And of course, you can imagine, like, we were watching it, and it was a pretty tense moment the first time you put it out there. The system reacted very well around it, even though probably it hadn't seen something like this before, although it had seen many, many things in simulation. And the third picture is of a Chrome car that we saw in Toronto. And yeah, for a camera, this is kind of one motivation to have redundancy in sensors. For camera, maybe not so hard for this vehicle, but you can imagine if the trailer of a big truck was painted the same way and it reflected basically everything, doing perception can be pretty hard with camera only, which you don't get like the depth aspect, like the geometry. So that's a great motivation for LiDAR and radar. And it's not just driving that it's hard around these examples. It's also the fact that these examples exist and we need to account for them means that we need to test very, very thoroughly, especially in simulation where we can recreate these ones and create new ones too, like purely synthetic. once. So now we'll talk a bit about the modular autonomy. So this is the industry's traditional approach, but it has kind of hit a wall. So in the traditional approach, before I ask you to kind of think of these modules as capabilities and kind of general ideas of what the self-driving needs to reason about, self-driving vehicle, but here it's actually taken very literally. And in this diagram, they are meant as different modules, basically cascading modules. And what this means is that there are very narrow interfaces between these different modules. And essentially, there's a huge team typically dedicated to each of those modules, or maybe parts of the module actually. And these teams are fairly siloed. They have their own metrics typically that they are trying to drive up, but those metrics are maybe not quite what we care about. Like they don't correlate that well with driving in the real world. And so you have these massive amounts of people working on different teams, trying to optimize things that are not quite what we want. And the fact that it's modular and it has these components and these very thin interfaces also means that if there's any mistake, let's say a perception mistake, then prediction will do even worse because it has very limited information about the world compared to what perception had, which saw the sensor data. At least it knew that it didn't know about it. Now prediction is trying to make sense of some perception output that doesn't make a lot of sense. And actually, so that's one way, kind of from upstream to downstream, but it can happen the other way too. Like let's say the planning team now decides to change something on the planner. And now the prediction team also needs to adapt because the planner now assumes a certain properties of that input. So they need to go and change what they did as well. So basically a change or mistakes in any parts of the pipeline cascade both ways. And yeah, this can be really, really hard to develop, to basically have a agile development here. And of course, because it has huge number of employees, it's also very expensive. Some of the companies with this paradigm burn billions of dollars every year. So kind of the other paradigm that has emerged, which is a complete opposite, is this basically end-to-end neural network, where we have a neural network that consumes the maps and sensors and outputs directly the decision. And it's actually very difficult to make progress with this approach because of several reasons. First, let's say the system doesn't do something well. Really, the only way you can go fix it is by either designing this neural network again or adding examples to your training data. But it's all very indirect and it's very hard to get basically kind of a quick development cycle where you get a lot of feedback back from testing. The fact that it's not interpretable, it's also a problem. First, it's a problem because it's hard to understand for developers what the system's doing. But second, it's also a problem for regulators, which expect some level of reasoning in that vehicle that can explain why it did a certain action. And finally, it also requires a huge number of examples for training. Training can be very long and very costly too. So we are kind of shifting the cost from a huge number of employees in the previous paradigm to a huge amount of dollars for training this system end-to-end. And the reason is that end-to-end training can be inefficient because, or at least if it's solely end-to-end training, it's hard to learn about everything that's happening on the world just from your kind of an expert controller or let's say driving a simulation, but with only feedback from the right action. It's not from any kind of world understanding. And finally, since everything needs to be tested, or we should test everything before going to the road and be confident before actually going driverless, this can be very hard to test because it basically grows exponentially the amount of tests that you need to do with the amount of factors that could change the output of your autonomy. So in this case, since it's end-to-end, anything that changes in the input can change the output. And we cannot really test, let's say, for example, our perception doesn't do very well with a certain type of clothes and maybe when they are wearing a hat and carrying some object. We would know this, let's say in the modular approach, we would know this because we will have metrics at the perception level and we can bucketize it by different types of actors. And then we can know this well in advance. Let's say if we've only seen a person on the side of the on the sidewalk with those properties, and we didn't do very well. But in this type of system, you will only realize you don't do very well when you actually encounter that person in a situation that you should react, right? Because basically the only feedback you are getting is from the driving itself, not from your understanding of the word. So that's quite limiting. So this is the paradigm we are proposing instead. You get maps and sensors. You are able to learn both from unsupervised data through this foundation model with generative AI, and you are also able to learn with supervised fine-tuning this additional layer of reasoning that can output interpretable representations. So coming back to what I was just saying, this upper layer of reasoning can be supervised and can also be interpreted. So it can be well understood what the model is reasoning about, and this can be great for both training, which we can encode a lot more of our knowledge, as well as testing by getting to know early what the system as a whole cannot do by understanding what the system doesn't understand of the word. And this also unsupervised pre-training with supervised fine-tuning is a very powerful framework because it allows you to leverage the scale of your collected data, which is cheap on the foundation model side. And it also allows you to essentially inject your knowledge through supervised tasks that we'll talk a bit about later in the other sessions. So it's still AI first. The system is end-to-end trainable. It's interpretable, which can help with verification and safety. It's scalable because it does this complex reasoning. We can tell from similar situations whether it's going to transfer to another one or not better than in the end-to-end paradigm. And finally, it's very capital efficient. We don't need a huge team. You can think of the backbone of the reasoning happening in the foundation model, which basically has the pros of the end-to-end paradigm. And then we also don't need thousands or hundreds of thousands of essentially annotated cases with a lot of human knowledge, because we only need to fine-tune this model for the reasoning that we want. And here's a teaser, maybe a glimpse into what I mean here. This is a paper that it's here at CVPR. We call this our occupancy foundation model. Maybe contrary to other foundation models, it doesn't try to output the sensor data itself, like trying to reason about basically the future sensor data, which it can be hard to use. It's not clear how to use a word model where you're predicting images or LiDAR. Instead, what we are doing here, which is the outputs that you see on the left, we are trying to reconstruct the geometry of the word, like everything that is going on in the world around us as occupancy. So actually, that's a 4-dimensional occupancy, X, Y, Z, and time, that we can actually query in the motion planner, right, and understand which parts are occupied and which not. So it's interpretable. It can understand what that couch in the middle of the highway is, which we actually found some time ago in Texas. So this is the sort of thing I'm talking about, where we are bridging the gap between kind of some end-to-end black box and interpretable representations. Sorry. Yeah, so if you're interested, that's the project website. You can learn a bit more about it. I'll talk a bit about it in a later session that we have. And that the oral presentation is tomorrow, Thursday at 1 p.m. and the poster also Thursday at 5 p.m. Cool. Now we move a bit from autonomy to simulation. And we've really flipped this pyramid. So typically, or traditionally, there's essentially a little bit of simulation that developers do to understand the performance of the system. Then there is more closed course testing. And finally, there is a lot of testing in the real world. And this is kind of, okay, like it's been working to get it to work to that level that we were talking before, where it can do well on most of the cases. The problem is, first of all, you don't get to see a lot of interesting cases in the real world. If you're driving on the highway in Texas, most of the time, nothing really is going on until it does. And the second thing is that you get a lot of exposure basically by running all these millions of miles or even billions of miles in the real world, which can be dangerous unless you have a really, really good safety case. So instead, the approach that we've taken at Waabi is to do a lot more simulation. That's basically at the core of what we do. We actually developed the simulator before we had even collected real data, or starting developing the simulator before we even had started collecting with our trucks. Then you do closed course testing, of course, which is great to see the transfer from sim to real. And then once you are confident that your analysis and simulation basically can transfer to the real world, you go and just to verify that everything is working as expected, you do some testing in the real world, but by no means the amount that is typically done. And this is just kind of a quick overview of Wabi World, which is our simulator. Essentially, the philosophy behind it is that the world is out there. So if we can clone it, we can get the realism, but also the diversity of the world. And that's what we are trying to do here. We are trying to build this digital twin where we can simulate the different sensors. We can reconstruct objects that then we can place in the scene in very modular and controllable ways. We can generate complex scenarios for testing, but also for learning how to drive. Essentially, you can put your autonomy now and see how it would do in closed loop and learn from that feedback. Cool. So now that's it for kind of talking about Wabi as a company and kind of our vision and what we do. And this is the schedule for today's tutorial. So I'm doing the intro. Andre will be talking about hardware and sensors. I'll have another session on perception and motion forecasting. And then Kelvin will talk about motion planning and control. We'll have the lunch break. Andre will talk again on intelligent data mining, which is basically all the data that fits this system. We'll talk a short session on vehicle-to-vehicle communication, which will be very, very relevant in a few years when basically autonomous vehicles are deployed at scale. We'll talk about that simulator that I was talking about, as well as the behavior models that are inside with Siva and Kelvin. And finally, after an afternoon break, Andre will wrap it up with the mapping and localization sessions. Cool. So this is just a very, very, very high-level overview of what you'll see. On hardware and sensor session, we'll cover sensing, like the different sensors that are on the truck, what's their purpose, kind of what's the latest today, as well as the same for compute. We'll then go and talk about perception. So how can we utilize all these sources of information efficiently to perceive 3D object, but not just a few categories of interest like vehicle, pedestrians, and bicyclists, but actually in an open world where we can find couches on the highway like we saw. We'll then talk about motion forecasting, which is also called prediction in the industry. So this is, how can we anticipate how the world might unroll in all the possible ways that it might. And then the later part of the stack, how can we reason about all these interpretable representations and put them into an actual plan, a decision that we can execute. And then we'll switch more to the offline world. We'll talk about intelligent data mining. So specifically from all these kind of process from the moment you collect data to the moment you evaluate the networks, will focus on data curation and labeling. So basically how we select the best data before it's labeled and how do we label it. We'll talk about vehicle-to-vehicle communication. So how can we communicate in a smart way between different agents, autonomous agents. I talked about this digital twin of the world, and we'll get into a lot more details later in this session, and including how can we simulate our self-driving platform as well, not just the world itself, but the ego vehicle. And part of this simulation is also the behavior of the other agents around us. So we'll talk about this behavior modeling in detail. How do we represent a scenario on one hand, and also how do we design these intelligent agents that can navigate the virtual world? And in the afternoon, after the afternoon break, we'll talk about mapping. So what's the end-to-end pipeline basically to create these beautiful high-definition maps that gives us a lot of prior knowledge, as well as how can we know where the vehicle is located in the world to centimeter level accuracy. This is my last slide for the intro. I think we'll have questions basically at the end of every session, if there's time according to the schedule. And otherwise, there will be also extended QA during the breaks, as well as at the end of the day. And yeah, I mean, we are hosting, you can ask, I think, definitely in person and in Zoom as well, right? Yeah. Cool. Thanks, everyone. That's it for the intro. Started with hardware. All right. Or you can grab your phone, yeah. Okay. All right, so now that we got the overview of how this tutorial is going to be structured, let's get started. And first, we're going to start talking about the hardware and the sensors. And then we will have a look about how they're actually used in various parts of the autonomy stack. So my name is Andre, and I'm a research scientist at Waabi, and I work on a bunch of different things, and among them, some state estimation and some sensor simulation. So let's get started, okay? The overview of this talk is basically to give you a sense of the kinds of sensors you typically use in autonomous vehicles, then to give you an idea of the kind of compute you design for these kinds of tasks, and then having a look at how all of these things actually come together, basically from the mechanical engineering standpoint, to actually make a functioning, reliable autonomy system. Okay. Okay. So let's get started with the sensors that we use for autonomous driving systems. So I'll be talking a lot about various sensors that use in autonomous systems like LiDARs and cameras. But one point that I want to highlight is because, this is just an introductory tutorial. I'm not going to have the bandwidth to go into a lot of detail for these specific sensors, but I will do my best to provide detailed references whenever possible for you to learn more about how GNSS works, or details about LiDARs, wheel encoders, IMUs, whatever, so that you can learn more about them and see how they apply to your own research and your own robots. Okay. So let's first consider which aspects are desirable in one of these autonomous system platforms, right? The keyword here is robustness. This is hardware that's going to be out on the road, exposed to the dust, to potholes, to wind, to adverse weather conditions, often for more than 8 hours every day. And at the same time, it's responsible for a multi-ton vehicle, potentially at really high speeds. So here, safety is paramount. And of course, we want sensors that are individually resilient, but we want to also think about resiliency and redundancy at the platform level as well. So we want sensors that can provide rich information about the environment, as well as what the state of the vehicle is within the environment. So we want to be able to perceive the geometry of the scene, its appearance, the configuration of the road, and also potentially, our own state within this environment, like our position, velocity, and so on. So to group this session, we will begin by talking about GNSS, and then sensors that sense our own internal state, proprioceptive sensors, like, for example, wheel encoders and IMUs. And then we will talk about sensors that we use to perceive the scene around us. So let's take a closer look at some of these sensor categories. So GNSS, the Global Navigation Satellite System, of which the United States GPS is one notable example, are beacon-based localization systems which leverage time delay measurements to multiple satellites to triangulate your position. And because at the consumer level, there's essentially no cost apart from the receiver itself, this kind of consumer-grade GNSS is highly inexpensive. And because most of the time you can operate in a multi-constellation manner with connecting, to Europe's Galileo or GLONASS or whatever, you have basically very dense coverage anywhere on the surface of the Earth. But of course, GNSS is not without the limitations. So if you use GNSS systems alone, without any other fancy receivers or anything like this, you typically don't have centimeter level accuracy that you typically want in order to leverage, for example, HD maps. And while things like real-time kinematic or RTK systems can improve upon this, they come with their own additional costs, as well as complexity and so on. And furthermore, of course, the satellite readings themselves might be unreliable, for example, in urban environments due to multipath effects. And of course, if the signal itself is completely unavailable, for example, in a long tunnel, underground parking garage, a mine, indoors, and so on, then you will not be able to estimate your state without an additional system, like, for example, some sort of visual odometry or some simultaneous mapping and localization or some map-based localizer. Okay, second. Okay, the next step is to use something like an RTK or real-time kinematic system as kind of the next tier of satellite-based positioning. And
the idea behind RTKs is that while they require somewhat more sophisticated tech, as well as the availability of base stations near you for corrections, they actually do have the ability to deliver centimeter level accuracy for any sort of autonomous vehicle in a wide range of environments. So the way they work, just to summarize, is through essentially two main ways, which is on the one hand, they leverage differential GNSS that lets you get corrections from nearby base stations in order to improve your range calculations. And then they also use carrier phase measurements to further refine the satellite pseudo ranges and bring down your error rates. And of course, these are typically combined with something like an IMU to result in these smooth trajectories over time. Okay, but of course, they're not also without their own downsides. So while they are more accurate than GNSS and pretty widely available, they still require more expensive equipment. Typically, the receivers are more expensive to purchase than regular old stuff that you might have in your phone. And they often, for real-time corrections, require a subscription to some sort of correction service, which might end up having a cost that is per robot or per vehicle, which can add up pretty quickly. And of course, RTK isn't magic, right? If your receiver cannot see the GPS satellites at all, or if the measurements are just extremely noisy, then it cannot help you. Okay, so as initially introduced for perception, we basically want sensors that capture the state of the world around us. And in this case, LiDARs are one of the most common examples. Where they can perceive the 3D geometry of the scene directly using typically time of flight measurements and provide you with direct point cloud readings. Then you have radars, which have some similarity to LiDARs and how they work. And they have the ability to provide you with a complementary sensing modality. You have also, for example, ultrasonic sensors, which are yet another provider of range, which is particularly useful at very close range. And then, you naturally have cameras, which have an extremely wide variety, microphones, and a lot of other potential sensors. So let's have a look at these sensors in a bit more detail. Radars work using an antenna to emit some sort of low frequency radio waves and then pick up the reflections, to just overly summarize entire textbooks. But the idea is that you use the angle and the time delta of this return, and you can kind of figure out the 3D position. And the radars have the extra benefit here that you can observe the change in frequency between the emitted and the reflected wave, which can inform you of the radial velocity of the target according to the Doppler effect, right? You also have the ability to manipulate the emitted wave for more spread or more range, potentially even in the field, which gives us a lot of flexibility in your operating mode. You can have like more long range focus or a broader focus, wider field of view. And because you use low frequency radar, you can penetrate through things like rain, snow, and a lot of precipitation pretty well, which makes radars a really good additional sensor to improve your weather robustness. But this benefit can also be a limitation because radar often has the risk of penetrating through small obstacles if they're small enough, which again incentivizes the idea to combine them with other sensing modalities like radars or visible light cameras. If you compare them to something like a LiDAR sweep, the number of LiDAR points that are radar points that are returned by most radar firmware is also a little bit smaller. So you need to take that into consideration. And because of how waves propagate through space, you can sometimes exhibit things like ghosting artifacts or other effects like this because of multipath effects. Right, you can have like here in these examples, you can have rays that are bouncing around because of a bridge or a wall or whatever, and cause additional returns that your perception system needs to be able to deal with. LiDAR is in some ways similar to radar, but instead of radio waves, you typically use lasers. And LiDARs are popular in autonomous driving because they can provide you with a direct 3D reading of the scene that you can then directly process to perform perception in 3D. The way they work is typically by shooting some sort of laser beam, typically some infrared, and doing this at a predetermined angle, and then measuring how long it takes for that pulse to return. And because of these angular readings of the laser when it shot the beam and then the time of flight, you can infer the location of the 3D point. A LiDAR sensor can employ a wide number of individual lasers. So you can have sensors that have just one laser up to even like 64 or 128. often stacked, for example, in a column, if you're familiar with those spinning LiDAR types. And yeah, 64 and 128 are typically common configurations that you see in autonomous driving. And one of these sweeps will typically net you about 80,000 to 150, 180,000 points per sweep. Now, in terms of strengths, you, as I mentioned, get very accurate, directly actionable geometry. And another cool thing is that because they produce their own light, these sensors are not sensitive to the outdoor lighting conditions. So they work basically the same way during day and night. And because you can measure the change in strength between the emitted and the returned wave, you can actually get a measure of reflectance, which is informative of the color and the material of the object you are hitting, which can be useful, for example, for long-range perception of things like signs and lanes and stuff like this, which is of particular interest when you're driving very quickly. Now, in terms of cons, there are a bunch of well-known ones. For example, the cost is one of them. While the prices of LiDARs have been decreasing over the last few years because of new efficiencies in the technology and manufacturing processes, you can often see most units still cost in the order of thousands, if not tens of thousands of US dollars. So it's definitely not affordable. And the resolution itself, or the number of vertical pixels that you get in your readings, is still lower than cameras. So for example, if you have a 64 beam LiDAR, it basically gives you a range image that has a vertical resolution of 64, which is of course much smaller than something like an HD camera with 1080 pixels in the Y dimension. And of course, just like with radar, in LiDAR, you can also have ghosting effects that you need to account for in your perception system. For example, seeing objects underground because of highly reflective surfaces on the ground, or other effects, caused by shiny surfaces or wet roads and so on. Although in a lot of cases, many of these artifacts happen to be underground. So because you can have a prior on what your ground height is, you can actually filter these returns somewhat easily. Now, spinning LiDAR types are not the only type, right? There is a lot of other technologies that you can use to perform similar ranging. So, for example, solid-state LiDARs are also a cutting-edge design that is aiming to reduce or completely eliminate moving parts in the sensor. And forms of these sensors are actually becoming really, really popular even beyond autonomous driving. So, for example, in consumer electronics like your phones or even some games consoles. And there's still a lot of different ways to do this sort of broad solid state LiDAR. So we'll go over 3 categories in this talk, although there are many other technologies that can be employed to do this because there's a lot of startups innovating here. So one of the most common ones is gated cameras. So the idea behind a gated camera is essentially emitting an infrared wave at a specific frequency and then making a sequence of gated captures that you kind of time very precisely in hardware. And each of these gated captures basically corresponds to a fixed round trip time for this wave, which defines kind of a range slice in the image. And while they have a lot of advantages and they're lower cost, but one of the issues here is because we're doing this sort of slice-based depth, you will have discrete range bands rather than continuous values that you'll typically observe in time of flight sensors. Okay. Another format is to do MEMS LiDARs, so micro electromechanical system LiDARs. And these kinds of LiDARs, like the one depicted in this image, they essentially aim to get kind of the best of both worlds for these classic spinning types and the purely solid state LiDARs. And the way they typically work is by using this MEMS system to control a really small mirror that basically lets you steer the beam towards the angles that you desire to sense. And in a sense, this is not fully solid state. It's kind of a quasi-solid state system in the sense that there's still some mechanical actuation. But because this is at the micro scale and the lasers and the other optics remain static, it is still a little more scalable to use these kinds of sensors and to build them. And one really cool applications with this family of sensing is that these sensors enable custom scanning patterns, actually. So you can, for example, have your software actually decide to spend more cycles scanning exactly in front of you and less on the sides. For example, if you're on a highway and you're interested in longer range perception, and then change this configuration once you are, for example, trying to park and you're driving very slowly. The LiDAR designs we covered so far typically use a pulse amplitude modulated laser. So here your range is actually defined by just a time of flight for that pulse, right? You just measure how long it takes for the pulse to return. But a different approach relies on using continuous frequency modulated laser. And in this case, the range is actually calculated differently by comparing the frequency shift between two coherent waves, one from the internal sensor oscillator and the one from the actual reflected wave. And one interesting side effect of this is that because you're using frequency modulation, you can simultaneously measure both the radial distance as well as the velocity because of the Doppler effect, which is similar conceptually to how radars do it. But of course, this also comes with its own set of challenges. So because you want to estimate position and velocity accurately, but these readings are essentially entangled in the sense that they both affect frequency, you still need to come up with strategies to disentangle these effects. And second, the frequency comparison between the source and the reflected waves is also only really possible if they stay coherent. So you are limited in the range of these LiDARs as a function essentially of the coherence length of the laser wave. And because of these complexities, these FMCW LiDARs are still a little less popular and sort of less available than other modalities, but they still have a huge amount of potential, as we will see in this video, where we can see some example data from one of these sensors. I think it's from Aeva. And here you can actually see that on the top half, you can see the perceived radial velocity color-coded, which gives really nice features on the moving vehicles. It basically also almost segments their motion at the sensing level, which means that your models, now that they get this kind of input, can actually focus their capacity on more higher level reasoning, motion forecasting, interaction reasoning, contextual stuff. So in a sense, this carries the philosophy of the LiDAR just offsetting computation away from your model one step further in terms of the motion. Of course, no talk about hardware for any sort of a modern autonomous robot would be complete without mentioning cameras. They're probably the sensor we're most familiar with here. We all have them in our phones. We can all see. I don't think most of us can perceive radio waves that easily. So we have this connection where essentially we can more intuitively figure out what's going on with the camera. So just again, to summarize things quite a lot, the way they work is essentially by having some sort of array of photosensitive cells. And each of these cells typically has some sort of filter for a color band. It's typically red, green, and blue, with more green cells to red and blue ones, although nowadays a lot of sensors use much more esoteric patterns for these things. And essentially, once you have this reading, you can then convert these kinds of cell patterns to an RGB color that is familiar to humans using a process called debayering, and you essentially interpolate some sort of RGB color from these raw readings. Now, the benefits of the cameras are that, by directly perceiving colors, you can quickly infer the texture and the materials of the scene. Cameras are also generally pretty cheap. So they give you pretty high resolution data, and they're vastly available, meaning that they can also, when you're developing a system, there's a huge body of many decades of literature that you can use to figure out how to effectively use their data. They also provide pretty high frame rates, anywhere from 30 to 120 FPS, even more, which is much faster than typical LiDAR sweep frequencies, which are about 10 Hertz. You can also use, of course, lenses to mix and match and kind of focus on what you want, and configure cameras to be, very wide angle, or use telephoto lenses for very long range. Now, on the cons side, any image that you get is essentially just a 2D plane. So there's no explicit depth information, right? And while with a well-calibrated system, you can infer the angles of these rays, you would still need some sort of stereo setup or something like that in order to directly figure out the 3D geometry of the scene. And at the same time, because cameras are essentially ambient light sensors, they are sensitive to the lighting conditions in the environment and essentially rely then on external illumination conditions. So are a bit less effective in the dark. And then, if you have things like quick changes in lighting as you're entering and exiting a tunnel, for instance, you need to pay special attention to how your exposure automatically adjusts to accommodate this. And of course, there's also potential artifacts that happen with lenses, like lens flares, chromatic aberration, lens distortion, that you need to make sure you calibrate for and account for. Okay, last but definitely not least, event cameras. are a cutting edge vision sensor that kind of departs from this traditional frame by frame paradigm that we've seen so far by instead operating on a principle of asynchronous event-based sensing. And the idea here is that instead of integrating data on a frame by frame basis, like you would in a normal camera, abstracting away effects like rolling shutter and whatever, you have the event camera actually just asynchronously fire off events on intensity changes in real time with extremely low latency, something on the order of microseconds. Now, in terms of strengths, these sensors have really high dynamic range also, which allows them to very easily deal with changes in lighting conditions, such as entering and exiting a tunnel, for instance. They also have really high temporal resolution, often as high as a microsecond, which is orders of magnitude better than many other kinds of sensors. And this allows them to excel in scenarios with really high speed motion. And they also consume little power, which makes them really helpful on resource constrained systems like drones. Now, in terms of cons, much like classic cameras, they don't perceive 3D information directly. So you would still need some sort of stereo setup or whatever to get that kind of info. And they're also somewhat low in the spatial resolution comparing to traditional cameras, though because of innovation in the field, this is slowly improving. And of course, they're also a little less standardized and less studied than other sensors, which means that you might require a little bit more engineering and research in order to integrate this into your robotic system. Although once again, as you'll probably see even at this conference here, there's constant research ongoing to improve these kinds of, to improve models' performance on these kinds of sensors. So let's have a look at a quick demo. So we can see a comparison here between an RGB camera on top and an event camera during the night. So you can see here that the pedestrians in front of the car that are very, very difficult to see on top, they become very obvious in event space, even though, if you're just doing perception in RGB, it might be hard for them to be seen. So this makes it very helpful to get really quick reaction times, even when, for example, the lighting conditions are poor. Okay, so let's now turn our attention a little bit to the kinds of computers that we want to run our autonomy systems and our models on in order to make sense of the sensor data. So we've picked our sensors and maybe even decided on some sort of GPU setup to run our models on. But how do these elements, actually come together? Well, let's look at this diagram from the left to the right. So on the left, we begin with the sensors that we already talked about, like LiDARs and cameras. And you typically also have some sort of cellular connection, which is necessary for things like maybe GNSS corrections, if you're getting them over the internet, dispatch of routing commands and stuff like this, remote assistance, over-the-air updates, as well as potentially map updates. Then you have most sensors communicate with the central computer, which we denote by CPU here via some sort of Ethernet connection and a series of switches. You might want to upgrade this kind of connectivity if you have really high bandwidth sensors. I don't know, like a cluster of 8K cameras and stuff, but Ethernet is still very reliable otherwise. Then you have GNSS and other localization specific systems that are typically hooked up to talk to something like a positioning engine. This could be either a standalone computer or just your localization system that is encoded, that is just a part of your central computer. So a physically separate positioning engine is common if you use a drop-in solution, like I don't know, like an OxTS solution or something that might come with its own unit that you then need to wire up to your main computer. And then, of course, you have the autonomy system that runs on the main computer, will produce some sort of commands that you will validate with some sort of high-integrity compute system that will, if all things look good, interface with the drive-by-wire system to actually actuate the vehicle. Okay. All right. So now that we have these sensors, we have the central computer, but how do we actually build the whole thing, and how do we integrate it with an existing vehicle, whether it's a small delivery drone or a truck that weighs 10 tons? The initial process kind of looks something like this, where you want to produce a detailed system block diagram as your output. And this kind of diagram will be much more detailed than the high-level compute plan that we start with. And the process typically begins by reasoning about specific sensor field of view and the placement of every single sensor. You can do this heuristically, or you can actually use simulation to figure out an optimal placement in terms of some metric that you're interested in. You then have the engineers build this system build a system block diagram based on this specification. And the system block diagram will basically tell you exactly what sensors and modules you'll have where and how they are wired together and how they communicate. And then you gather further requirements for the overall system, which range for things like the compute specifications that we mentioned earlier, like how many ops do we need, how much hardware sensor processing capabilities do we need, stuff like this. And then combine these with other requirements, like, for example, the physical things, the physical constraints, like the size of the sensing array, the heat and vibration resistance, that sort of stuff. The design process then is what takes us from this initial block diagram to the final product. And here, one of the important lessons is to not reinvent the wheel. So if an off-the-shelf component exists for a specific task, it's important to use it and not start building stuff that's not necessary from scratch. And then in terms of the key design process elements that we need to think of, we need to think of things in terms of modules. So here, modules being building blocks that come together to form the physical system. You have things like component schematics, printed circuit board assemblies, connectors, housing, stuff like that. Then you need to think about the harness, which essentially tells you how all of these blocks are actually physically going to communicate with each other. And not all of these sensors are together. And this is particularly challenging for larger robots like a self-driving vehicle, a self-driving car, or even a self-driving truck. You might have a wheel speed sensor and a GPS antenna and a camera on the front grille, and you need to make sure you can actually reliably wire all of these things together and then do so reproducibly for multiple vehicles. Now, in terms of mechanicals, you want to use something like computer-aided engineering to ensure that your design that you put together, after you figure out things like where everything goes and what kind of housing and brackets you use for all the sensors, now you need to make sure that this design can actually satisfy the requirements of the real world. So you basically have to use CAE software to figure out wind resistance, temperature change resilience, velocity changes, stuff like this, to make sure that all the sensors that you mount stay where they are and are resilient, to all sorts of windy conditions, braking, weather, stuff like this. Okay. Okay, so to wrap things up, we hope that basically a key takeaway of this talk is that there's no one-size-fits-all solution for autonomy driving sensors, because each of them basically has its own set of pros and cons. Now, the key for safe and scalable autonomous robotics basically is to be cognizant of all of the trade-offs that can be done, and essentially designing hardware and software solutions basically together in a way that leverages the strengths of each sensors while also mitigating their shortcomings. So you need to have sensors that can kind of provide orthogonal ways of orthogonal kinds of information about the environment. And it's important to have redundancy in your system as well in order to make sure that you're resilient to partial failures. Okay, so yeah, thank you for your interest in this hardware session, and also special thanks to the hardware experts at Waabi that helped contribute to these slides. So now I'll hand it over to Sergio, who will be talking about perception. Oh, there's also some references. I'll leave this slide up for like a few seconds while we switch speakers. If you want to learn more about various kinds of sensors, there's a bunch of textbooks that can give good introductions and then references to more advanced, super specific things. Okay.
Time for any question? I think you want to.
I think we have time for a few questions if you're interested. Oh, yes, please.
Have you ever made a special sensor that you cannot actually find in the market?
Sorry, could you repeat that?
Have you ever need a special sensor that you have to actually order specially and that is not available in the market?
So the question is if there were any sensors that we were interested in that were not available in the market. I can't give super specific details about the sensors that we use, but I'm not that familiar with the purchasing process and all that stuff. But generally speaking, I think, yeah, I don't know. I don't like, for example, I guess it depends on the kind of sensor. Like if you're, for example, if you're working with a supplier and you want like straightforward automotive grade cameras and spinning lidars, you should be able to find them. If you want, for example, a very specific lens setup or a very specific model of event camera, that might be a bit more difficult. More questions? Yes.
So, I'm gonna read because I typed it out.
Yeah, no problem.
So, could you please talk about, how most of these sensors that you mentioned are integrated and are calibrated together to extract meaningful insights? Because, for example, how are the cameras and lidars calibrated or combined to get 2D and 3D information from a scene? Because this kind of information is hard to find online.
Yeah, sure. That's an excellent question. So the question was essentially how you calibrate the sensors and how you combine the information. For actually combining the information, assuming calibration is done, I think Sergio will give a lot of details on multi-sensor perception, motion forecasting, and so on. And in terms of calibration, yeah, I agree. I think one of the challenges we faced is that often in the literature, the calibration approaches that are described are for specific, each paper almost has a very specific sensor setup. So a lot of the approaches are difficult to generalize. Like if you have, instead of just one stereo pair and a LiDAR, you have a bunch of LiDARs and a bunch of wide angle cameras and whatever, it's kind of a little difficult. So I think even now we're still constantly improving the process, but a lot of the stuff we kind of had to develop in-house for the calibration. Basic things like figuring out the camera intrinsics is kind of solved, but then jointly calibrating all the sensors is kind of an open problem. And we basically came up with like proprietary software to do that because there was nothing academic that we could reference or any off-the-shelf solution.
Okay, yeah, because like single camera, single LiDAR is kind of easy, but when you have multiple cameras, multiple LiDARs, and then LiDAR to IMU, LiDAR to GPU, GPS, all that is, okay, I thought there was like some relevant information that's online or something like that, but if you guys are having a hard time, then it might just, I mean, a hard time, if you guys are developing your own tools,
Yeah,
then it might be, hard.
Yeah, we have some research coming up that tackles part of this, but not all of it. Like our full pipeline had to have a lot of kind of custom components. Also, there's a couple of questions on Zoom as well. I'm gonna take a couple of those as well. One of those is about event camera usage, specifically at Wabi. I can't give like specific details about our sensor setup, unfortunately. And there's another question about sound sensor applications. I don't know, do you have any sound-based perception insights?
Is a question about the applications? Yeah, so definitely, for example, one is to be able to hear like a siren from an ambulance, right? Sometimes you can hear the siren before you can actually see the object, or you can see the object maybe far away, but you can still not tell that it's an ambulance and it's active. But if you have microphones, you can tell that.
Okay, let me just check this. I think we should get started with the next session, but we will be around here for more questions during the break. And there's going to be an extended block of time dedicated for any questions you can write down right at the end. Okay, so then.
Can I ask a question?
We're moving to the next session, but we can have more questions during the break. But please type them up in Zoom otherwise. Thanks.
The break is after this upcoming session.
Okay, and then 3D perception. Okay, go for it. Thanks, Andre.
Just make this bigger 1 second.
Yeah, take your time.
All right. Yeah, welcome everyone to this session on 3D perception. Oh. Yeah, so I mean, I covered this before, but for those of you that joined just now, basically the session will be about how can we utilize these multiple sources of sensor inputs in a way that is efficient to be able to perceive basically the objects in the scene, but not just the kind of well-known categories like vehicles, pedestrians, and cyclists that maybe some closed word autonomy systems typically do, but more in especially towards the end of the talk, we'll talk more about this open world perception. to be able to basically perceive anything like from animals to like anything we can find on the road. So the session is structured with these sections. We'll talk a bit about tasks within 3D perception very briefly, then spend quite some time on the input representation and the scene encoding, as well as on the other side, basically, how do we represent the outputs from the perception system and what are like maybe good decoders. We won't get into a lot of detail about any specific model. It would be more like going through the different like input representation, the model and the output representation, but without covering, let's say, one paper in extreme detail, more like trying to understand the different contributions from different papers over time. Then we'll talk about memory. So there's actually not that much work in this area, but I think it's very exciting. Like basically, how do we integrate our knowledge that we build over time in the scene, not just what we are currently perceiving. And finally, yeah, what I was talking about before, more like the open set unknown objects topic. So yeah, let's talk about the task. I guess what everyone is familiar with is 3D object detection. So basically trying to place 3D bounding boxes around the objects of interest in the scene. There's also 3D panoptic segmentation, which is a very interesting task where for every LiDAR point, essentially, we need to be able to tell what's its semantic class as well as the instance it belongs to. So basically, those are two very different types of reasoning. One is more about, is it a car or a pedestrian or what is it? And the other one is a kind of clustering of points for each instance. And finally, something I'm very fond of, we'll talk about 3D occupancy. I think in some datasets, like semantically, this is also known as scene completion, but basically trying to get a complete view of the scene, kind of in a more non-parametric way than object detection. Cool. So let's jump right into input representation and scene encoding. As Andre mentioned, basically, we have different sensors. I mean, I'm missing a lot of them. I'll focus today on LiDAR and camera. Radar is also super important. We talked about microphones too, event cameras, but yeah, we'll keep the presentation to keep it within the time, mostly on LiDAR and camera. And then we'll also discuss the role of high definition maps for perception. So let's start with LiDAR. Yeah, LiDAR is typically the primary sensor in most L4 companies. The reason is that it gives, it's buffering a bit, but it gives basically a really, really good understanding of the scene. You can see there from a bird's eye view, essentially what we are plotting here is all the returns from the LiDAR rays where they stop, and they are aggregated over the Z dimension in ego frame, meaning that basically we are showing here a pixel is occupied if any of the voxels in that pillar essentially is occupied. And you can see, you can get a very dense sort of understanding of the 3D geometry, especially around the vehicle. Farther away, it gets sparser and sparser, of course. So there are multiple representations to represent these point clouds that have all their pros and cons that we'll cover just now. So 3D voxels is what I was talking about. Basically, you create a regular grid and around the scene, and you reason through here. Bird's eye view is what we were showing. So it's essentially 3D voxels, but squashed on the Z dimension. Then we have range view, which is kind of close to how the actual sensor generates or shoots the rays, essentially. So you can think of this as the rays shot from the sensor are plotted in terms of like their depth, for example, in that image. We'll get into more details. And finally, you can also think of it as a point set. Basically, you have this point cloud. Each point is essentially a continuous XYZ, and actually time too, because the rays are casted at different times, like in a spinning LiDAR, for example. So let's talk about voxel grids. So we divide the space into this 3D grid, and then inside each grid cell, we can either reason about occupancy. So basically, is there any point within that voxel? We can also maybe something intermediate would be like some statistics about the points inside the voxel, like the types of the density, maybe the variance within the voxel. And then you can also learn these point features, point set features instead. Like you can basically, for example, run a point net if you're familiar with it in each of the grid cells potentially. And one of the main advantages is that this preserves the 3D metric space. Like this voxelization process actually still reflects the true geometry, I guess, of the scene in 3D without any distortion. And 3D convolutions are really, really good at extracting features for this. I guess more recently, we can use vision transformers as well. Of course, on the downside, the computation and memory grow cubically with this essentially cube-like region of interest that we have. And it doesn't really exploit the sparsity of the sensor. So when I showed the video earlier, you could see it was pretty dense near the vehicle, but very sparse outside. This essentially, yeah, will grow cubically. And when we extend to those sparse regions, we are essentially wasting a lot of compute because we are running these 3D convolutions on areas that there's nothing, or at least the sensor couldn't perceive anything. So one kind of optimization is to go from 3D voxel to bird's eye view, is squashing essentially the features on the Z dimension in the ego frame. So basically X moving forward, Y to the side, and then Z upwards from the ego vehicle. We can basically do this top-down projection and consolidate the height features. And one way to do this is point pillar proposed, which is here at the bottom. Essentially, you take all the points within a pillar and you run some form of point extraction, like a point net here, and then that gives you features for that pixel in bird's eye view. And then here we can run some 2D convolutions, which are a lot more efficient. I mean, quadratic instead of cubic. But this still doesn't quite exploit the sparsity of the sensor returns. While there's a lot less sparsity in bird's eye view than in 3D, there's still a lot, as you can see in the top right image there. So yeah, LiDAR is very sparse indeed, especially at range. So how can we make this faster? So one way is these submanifold sparse convolution networks. So a regular 3x3 convolution will diffuse the features over convolutional layers like you see on that left image. So essentially, at the input level, it will be very sparse, which is what we'll show now. And then over convolutional layers, it will get denser and denser because the features basically diffuse according to the receptive field of the CNN. So if we do that, then it's hard to exploit sparsity, right? Because even if you had something that could reason this is occupied or not, it will actually be occupied in the later layer. So at the end, towards the end of the network, everything will be dense. So instead, these submanifold convolutions were sparse convolutions were proposed, where they work as you can see on the right. Essentially, you only apply the 3x3 or whatever is your kernel size filter on areas that are on pixels that are the center of the kernel basically is occupied. So it doesn't diffuse over layers, the features. It just, the features diffuse over, I guess, the adjacent occupied pixels, but they don't diffuse into the unoccupied pixels. So that way the sparsity is preserved throughout the network. One downside with that, though, is that for LiDAR, for example, most of the returns are from the boundaries of the objects, right? Because that's what I guess your ray stops at. But detectors typically like to detect from the center of the object. So one thing we could do, or this paper proposed, it's actually a CVPR 24 paper, is to do this adaptive feature diffusion where you allow for the submanifold convolution to diffuse the features essentially around those areas that you are interested in, like potentially like high confidence that there is an object there. That way you can still leverage like most of the scene is sparse, but you get way more dense features around the objects, which are helpful. One of the weaknesses of these methods in general is that the speed up is input dependent, which you typically don't want in a self-driving system. You want to have your computation kind of as well known and controlled as possible. But it's still very good if you can bound basically the density of your inputs. And yeah, I mean, it's kind of the strength and the weakness, but it has a more limited receptive field, because if you have kind of an occupied area here and then unoccupied and occupied like some pixels, then the information doesn't quite propagate from one to the other. It stays very local. Then we have range view. I feel like this is the most, as I was saying earlier, like the most natural way to think about how a LiDAR actually sees the scene. Basically, we have the sensor right there, right? And then you have all the beams scanning the scene. Each beam has its own elevation angle. And then it's like for time of flight spinning LiDARs, these beams are essentially, or the rays are spinning by a polygon. But essentially, this is scanning the scene in these two kind of degrees of freedom, azimuth and inclination. And then you can plot those returns by different features onto an image. Like, for example, you can plot the height of the return in EagoFrame. You can plot the intensity of the return there in the second image, which you can see like tells a lot about the texture, or you can also plot the range, like the depth, how far these things are. So the good part of this is it's probably the fastest, because you can then run 2D convolutions on this very dense and very small compared to bird's eye view image. But this doesn't preserve the 3D metric space. Like the distance over 2 consecutive pixels in 3D might be very different. Like for example, at a boundary of an object, you have a very sudden change of depth, which can be hard to reason about. Especially, of course, if you want to just do 2D detection, this is fine. But if you want to do 3D detection, which is what we are thinking here, like 3D perception, this is actually harder to reason about. And finally, point sets. So these are unordered sets of 3D points. The features, for example, can be the 3D coordinates themselves, or maybe the 3D coordinates with respect to some neighbors. So the good part of this is the localization accuracy typically of detectors that, for example, use this can be very high, because they have access to kind of the most raw information without like quantization issues, like for example, in voxelization. But first of all, it's quite expensive typically because it has a very irregular memory access. And you also, something that is typically done in perception is that you run these at different resolutions. Running different resolutions and multi-scale features is useful because basically objects are different sizes, they are farther or closer. So having multiple scales in your reasoning can be helpful to be able to perceive all these different objects. But that is hard to do at the point level. Typically, that's done with this key point subsampling. Like basically, you decide which key points you keep when you do multiple feature scales. But it's actually hard to decide which key points are the best ones. And finally, all these LiDAR representations can be combined. In this work, for example, they fused everything through the point representation. So basically, they have a voxel representation at the top, point representation in the middle, and a range image at the bottom. And you can actually get the best of these different representations by exchanging information between them. So every point basically can be projected to its voxel as well as to the range image. And that way you can interact between the different representations and their features. And let's say finally you wanted to do LiDAR segmentation, which is what this paper is doing. And then you would output, basically make sense to output the kind of final classification from the point features, because it's already at the point level, which is the task that you care about. But you are still able to benefit from the reasoning of the other two representations. So yeah, you get basically the best of both worlds as the strength, but of course this is additional computation. So it's more like if you can afford it based on your hardware and your system, you would do it. Otherwise, you would basically compromise and pick some of the some subset of the representations. Cool. So now we'll move on to camera. Essentially, camera gives you these two-dimensional images, right? With color, as Andre was explaining. But we are interested in 3D perception because, I mean, the world is in 3D and we need to navigate it, and we need to know if our track is like the distance to things, and to be able to, plan a safe maneuver. So at some point, essentially from the 2D image to the 3D output that we want, we'll need to lift, basically lift from 2D to 3D. So we can lift at the input level. Like for example, trying to convert the image into a point cloud, we'll talk about how, and then we can just do the reasoning in 3D. We can essentially do some reasoning in 2D and try to lift at the feature level. And we can also do all the reasoning in 2D and just output basically our final output in 3D. So we'll start with the 3D lifting at the output level. So what this means is we are running some form of network, like convolutional network potentially, or a VIT on the image. And then we are trying to predict a 3D bounding box from the image. And this is typically actually hard to do. So for example, what this paper was doing, this is many years ago, it was trying to essentially predict key points in 2D. These key points are easier to predict because they are kind of a property of the 2D image. And then based on the key points, basically certain distinctive features of cars in this case, you can try to match it to some template that you have built offline from your data set. And then this template can be mapped directly to 3D. So essentially, you are kind of separating the problem, but instead of doing full regression to 3D, you are regressing these key points in 2D, then doing matching to avoid basically doing the 3D shooting, which is typically the hard part. So this is a simple design. And the good part is we can take a really good off-the-shelf 2D detector, right? And repurpose it by adding this additional kind of head. But typically, this doesn't yield the best performance of the different methods. So like kind of the opposite side of the spectrum is to lift the 3D, lift to 3D at the input level. So we have the image at the top, and then we can predict a depth map for the from the monocular image, which you can see in the second image there. And finally, you can essentially shoot the image into 3D with this depth map, right? Like basically for each pixel, you know the depth, so you can put it in 3D. And this creates this pseudo LiDAR input basically. And so the good part is now you have a pseudo LiDAR, so meaning you have a point cloud, so you can take advantage of the quality of 3D detectors. But this is actually quite a bit of overhead in terms of computation, because first you need a depth prediction network, which is, it already does some reasoning, right, to be able to predict depth properly. And then you kind of throw that reasoning apart because you've transformed this into a point cloud, and now you're applying another 3D model. So you need to basically reason from scratch again about everything to try to detect in 3D. So kind of the best middle ground typically is to do this lifting at the feature map level. So let's say you have run some layers of a convolution or VIT model on an image, and you have some basically image features. What you can do is you can predict the depth distribution for every pixel in the image, and you can essentially shoot to 3D the features themselves, not the input, weighted by basically this depth distribution. So you'll shoot many features at different points along the ray, and this will land right in different points in 3D space. So you essentially end up with kind of this frustum, right, from your image of dense features in 3D, or more like a point cloud in 3D, which then you can voxelize and apply, like, do more downstream reasoning. But the good part of this is that you don't need to start that downstream reasoning from scratch. These image features are already very powerful, right? You've already run some processing basically on them, and what you are raycasting is the features themselves, not the geometry. You can do something similar if you have a stereo pair and you have basically left features from the left image and the right image. You can do something similar where you actually first start with your voxel grid, and then for each voxel center, you project it back into the two images, and you grab the features of the like the image features of both and concatenate them. And essentially, that kind of on an intuition level, if the features inside each of the grid cells are similar, that means you are probably at the right depth in that 3D volume, right? Because the two cameras are seeing the same. Finally, we can also use this form of attention basically to, from a bird's eye view, in this case, BBFormer, what they propose is from a bird's eye view feature map, which is like just seen from the top, right? We can lift the features to 3D by simply copying the features at multiple heights. That's what those red dots do. And then from each of the those 3D points, we can attend back to the image features on the images that hit basically that 3D point. Like not all the images will actually see that spot. So the inference in 3D space typically can understand better 3D geometry. So these methods typically work better. It doesn't need a depth estimation, so it's still more efficient than like lifting at the input level, but it can be more computational than lifting at the output level. Cool. So now that we've seen LiDAR and camera separately, we can go into fusion of these two sensors. So the first approach is to do this sort of cascading fusion, which means that we break down the problem into two. We detect the objectness in 2D. So basically in the image, we say there's a vehicle here, and we do 2D detection essentially. And then we can compute the 3D frustum if we know the extrinsics and intrinsics of our camera, right? And then given the points from LiDAR in that 3D frustum, we can localize the object and predict a 3D box. So this takes advantage of mature 2D detectors, meaning that basically your proposals will be very good if the 2D detector, image detector is very good. But at the same time, that's a downside because any object that is missed by the image detector will not be recovered by LiDAR, right? Here we are just using LiDAR to localize, not to detect if there is something. Completely different is output level fusion. So here we essentially are running two systems in parallel. We have a camera detector that goes to 3D like we saw before, and a LiDAR detector that also outputs boxes in 3D. And then we try to do some fusion at the output level. This typically basically requires many heuristics to where the engineer essentially decides which box to trust more in case they are close by, or if there's no agreement, do we still preserve it or do we not preserve it? And typically, this is just a very hard system to tune. In theory, you could get kind of redundancy from two independent systems, but I think just the tuning and kind of all those heuristics make this hard to work with in practice. And another approach is to do the fusion, but more at the input level between the two sensors. So we can, for example, get semantics out of the image in this case, and then project those semantics into the LiDAR, because we know essentially if the LiDAR and camera are calibrated, right? We can tell essentially which parts of the image corresponds to which point in 3D, and essentially we can color the point cloud to put it visually here. And then we would run our 3D detector on top of that. So the kind of having all the fusion in one place at the input level allows for a lot of processing, like on the joint information, which is typically a good thing because you do basically all this learned fusion, right? And you don't need to hard code anything in terms of having two proposals from two different systems and which ones do we trust more and whatnot. But yeah, again, here we are trusting our calibration blindly, right? We are assigning a label to each point based on like which parts of the image correspond to the point cloud. And we also are doing very limited exploitation of the camera data. Like we are running some camera processing, then assigning either features or some class, and then we are giving that to the 3D point cloud, but we don't do any more reasoning in 2D. So maybe somewhere also like a more of a sweet spot is this feature level fusion of camera and LiDAR, like proposed by here BV Fusion. Oh, I just noticed like a lot of the citations, I guess, are getting broken down here at the bottom, but
I think it's sort of the projector, but they will.
yeah, only the projector, yeah.
They will look good in the recording.
Yeah, they do in the recording, yeah. So sorry about that, but if you need some of the reference, you will be able to refer it back once it's online. But yeah, here we're showing the diagram of BV Fusion. Basically, there's a LiDAR point cloud, which we run a LiDAR encoder, basically a point cloud encoder. And we can get these 3D voxel features, right? Then we can flatten them in bird's eye view. And we can do something similar as we saw earlier with the image. We can use the frustum of the image and a predicted depth distribution to shoot the camera features into 3D. Then once we have the camera features in 3D, we can also flatten it into bird's eye view. And at that point, we have the LiDAR bird's eye view features and the camera features in the same space. In bird's eye view, we can simply concatenate them along the channel dimension and run basically this bird's eye view encoder to do any bird's eye view task that can essentially use the two modalities. And it doesn't, if you think about the calibration requirements here, they are a bit lower. You still need to know, like you still need to have a decent calibration. So like when you shoot to 3D, the image features, they are kind of at the right spot, but we are still gonna run a lot more processing on that 3D volume after fusion, which means that if they are slightly off, let's say a couple of pixels off, or yeah, like something reasonable, that fusion network can still essentially fix those calibration issues and understand what are corresponding features between LiDAR and camera. But of course, this needs more computational memory footprint than or memory than some of the other approaches I just talked about. Cool. We'll get now into the final part of this kind of input representations and fusion and see how we can leverage high definition maps. So one of the interesting things that high definition map provides is this ground height. So essentially it tells you, it's a layer that you can think of it as in bird's eye view, where you can essentially query what's the height of the ground at any point in 3D. And this ground height can be either built offline or online. For example, if we want a plane to simplify things, depends on the application here, the OD, like the operational domain of every robot. But if you want a plane, you can apply RANSAC maybe to the point cloud. Otherwise, we can just have some non-parametric shape, like just a raster, where we encode the height of every of the ground. And then we can essentially, if we're doing this online, you can think of, for example, your 3D point cloud in bird's eye view, and you have some fully convolutional network predicting like the height, right? And finally, maybe this is the most interesting one. Once you have the height, let's say we have this like sloped road with a change in elevation. In the point cloud, if you didn't do anything with the map, that would look like basically a variant. It will have a high variance in Z, right? The point distribution. But now you can use the ground and actually essentially subtract the ground height from the point cloud, and it will look like the ground is flat now, right? You've basically, now your Z dimension now is the height above the ground of the points. That's what we are doing in that image. And then when you voxelize, first of all, you need a much smaller voxel size, because you don't need to cover as much range in 3D if what we care is things that are on the ground, on the road. But it's not just the computation, it's also like, it's much easier to learn on this space, because this basically the distribution over Z is much more, I guess, has a lot less variance over training examples, or over examples in general. Yeah, so this will help detection. Of course, the downside is that we cannot always use this. Like sometimes the map changes, or and then we need to basically update. Typically, the map doesn't change too much in terms of its geometry, like the ground height, unless they are doing some major remodelation. But yeah, it's something to still look out for. Another important piece of information that the map provides is these kind of more semantic rasters that you can build. So these maps typically contain semantic information, geometric information about the lanes. You can see them, those in colors there, like for example, color representing the direction of traffic of that lane. So that's a huge prior for perception, right? Like you can know if you expect to see a vehicle in that direction, in that area. That doesn't mean that there cannot be a vehicle like in the completely opposite direction, right? But this can help the system kind of with some priors. And the fusion can be really simple with these rasters. You can basically raster in bird's eye view, run a CNN, and you get bird's eye view features. We've already seen how to fuse, like for example, concatenating those two modalities. So it's very easy to implement. The fusion is very simple, but still pretty effective. Of course, this has lossy rendering. Like you need to basically build this raster, and if you're using convolutional neural networks, it will have basically a limited receptive field, which for perception, I think is fine. In the next session, when we talk about forecasting, we'll see that we want a pretty large receptive field to reason about like long horizons temporally. And probably the most used today is these lane graphs. So we can represent each of the lanes as a sequence of vectors, and we can do the same, for example, for tracks of the objects. And then they all live in this vector space, which is sparse, which is great for computation. And we can apply graph neural networks with transformers on it, which are perfect, essentially sequence-to-sequence models. And yeah, here is very easy to achieve a large receptive field. You just need to, for example, have skip connections, right? That connect, like it's all about the adjacency matrix, basically, that you are using in that, the connectivity in that graph that you are building. These have been shown to be very parameter efficient. And it's a very natural fusion at the object level. It's not so natural with the sensor level, which we'll see some work later. And typically, yeah, there's a lot of kind of handcrafted features in terms of what do we connect to what, like is this lane connected to its neighbor, if there's a solid line or a double line, like that type of feature engineering to basically bake in priors. Cool. So now we'll switch to the second part of the presentation. I think I need to accelerate a little. Basically, so we were talking before, this is a very well-known representation, right? We want to output these 3D bounding boxes around objects. It's very interpretable, but it's also a very coarse shape, like it's just a bounding box compared to the actual shape of the object. It doesn't typically propagate uncertainty very well, right? You output this box, and typically you output a confidence about how confident you are on that estimation. But if it's not that box, you are also not saying what else could it be. So it's not a great form of uncertainty for downstream. And typically there's a lot of post-processing that goes into these detectors to make them work really, really well, like non-maximum suppression, for example. So there's kind of two frameworks at a high level. I'll just keep it very high level here. Essentially, one stage just means that from the features that we've been talking about, that we've extracted from the scene, you just have one shot, basically, detection based on, let's say, dense convolutions that output this layer that has all the classification, like the scores as well as the regressions. So basically, you can build the bounding box from it. And two-stage is similar in, like, it first does this. This gives you object proposals, but then these object proposals can go through some more reasoning, like, for example, a transformer decoder, where you are looking at the interaction between the different boxes, and you can attend from these boxes to the sensor data again and try to do a bit more reasoning to basically refine these detections. I'm going to skip these ones because they just talk about kind of that, but in slightly more detail. But and then we get into how to train it. So we have a system that outputs these bounding boxes, right? We can there are kind of two paradigms. There's this more heat map based loss, which means that you are assigning essentially the ground truth to the inputs. So let's say there's that object, and then we are telling these are the pixels responsible for detecting that object. Let's say the center pixels, right? That's the heat map that you see there around the vehicle. And then during training, because we have this pre-assigned pixel that needs to detect this object, we can just train that part of the image, like the output, to output the corresponding detection to that. And we can train all the rest of the pixels to be essentially saying that it's negative, like there's nothing here. And the other way is this matching base loss, which was made popular by Dieter paper a few years ago. And essentially what it means is that you don't do any assignment from labels to inputs. You instead have your detector, you output the different bounding boxes, and then you have a set of bounding boxes that you detected and a set of bounding boxes that basically have labels. And then you have this cost function between the two, basically a pair of a detection and a ground truth that defines how good a match it is between the two. And then you can run some greedy matching or Hungarian if you want to try to get the optima to get the assignment, and that based on that assignment, you train your detector. An alternative to detection is this occupancy. And here we are talking about the explicit case. Explicit meaning that we are actually defining a grid over which we are defining whether or trying to predict whether each pixel is occupied or not. So the good part of here is that you don't really need to do any post-processing. This output is already very friendly for motion planning. So you can basically tell, it can propagate a lot better sort of the uncertainty, right? Like if you're uncertain if some pixel is occupied, that can just be a scalar between 0 to 1. And that gives a perfect picture essentially of the beliefs of the model for downstream use. And simple training is usually super simple here. It's just a cross entropy loss, for example, focal loss, your favorite classification loss essentially for every pixel. And it can capture any shape, right? Like for example, here we've put that large object and it could be even articulated, and you'll just see like different pixels being occupied. There's no constraint basically about being a bounding box. Of course, there's quantization errors. We are defining that grid, which you don't have in detection because you are just outputting this continuous 3D box. And it can be computationally expensive because of this trade-off, right? Like basically the more you quantize or the coarser your resolution, then the outputs are worse for downstream. So you want a pretty high resolution, but when you do that, it's a lot more compute. So let's see how we can improve that. We had this paper actually last year at CVPR. Instead of representing the occupancy as an explicit grid, we can represent it as an implicit function. And essentially what you are doing here is you are querying a continuous X, Y, and time location. I'll get at the time in a second why. And then the implicit model is essentially spitting out whether you think like the probability that that point is occupied. And now what you can do is you don't need to query this model on a grid. You can query this model on, for example, the trajectories that you are considering for planning. Or you could even have multiple stages, like you query first on certain points, and then based on that, you can query that farther, maybe at a finer resolution in areas that you are more interested in. And the time is important here because, as I was talking before, the sensor is actually a continuous stream. Like all the LiDAR points that we are showing that image did not come at the same time. And typically, for example, if you are training this in a supervised manner with bounding boxes, those bounding boxes that you annotated are also not representative of the world at the same time. They are each of them representative of the time that the sensor hit that object, right? With the rays. So essentially, there's a small time. This is especially important for highway where there are high speeds and things are moving very fast. You want to consider that time in your model. And essentially, if you're thinking about how to actually use this, you could query at a constant time to get a basically constant representation of the world. But when you are training this model, you can query it at different times, basically according to the different times of the objects in the scene. So yeah, this has the same strength as this explicit occupancy that we saw, but it can also represent the scene at an arbitrary resolution. It's continuous, basically. I guess it's bounded by your input resolution. And finally, it only predicts values where they are required. So this can be more or less efficient depending on your, I guess, planner and how you use this model. But yeah, it's not basically a fixed computation that you're gonna have to go through no matter what. This actually these are the perceptions over time, basically. And you can see there in the middle, for example, this like large articulated object and how the shape is actually not just a big box. And you can also see like occlusion, like when there's occlusion, we can see a lot more uncertainty, like in that top right part of the image. So it's also a better indicator of how confident are we, should we be cautious around here or not. Cool. What do we have about, is it 7 more minutes or so?
Just keep going.
Okay. Okay. Yeah, let's talk a bit about memory. So essentially everything I've talked so far is kind of aggregating sensor data, either the last frame only or a very short, basically sequence of data. Like for example, you can aggregate LiDAR for the last second or so, or half a second, but you can really not do that much longer, just because it will take a lot of processing to do that every time. So the long-term memory basically allows you to accumulate sensor evidence. Like here we are on the left, you can see how a vehicle looks in a single frame versus how it looks if you aggregate the 146 frames, basically over a log, let's say a 15-second log at 10 Hertz. You can see a much better picture of that vehicle by aggregating that information. And you can, of course, also be able to reason through occlusion if you have memory, which you cannot if you don't. Like, for example, in that case, at some point, the pedestrian is occluded behind the pickup truck. The typical way this is done in kind of traditional autonomy is just through tracking. So you essentially have some hard association with some state estimation. So you had some trucks up to now of your belief of the object trajectories, and then you can try to extrapolate basically based on their motion. And if that extrapolation agrees with your detection, then you are more confident that that object is actually there. And also the other way around, like if you detected something that is not in the memory, you will maybe downweight it a little bit. And if you have something in the detector that is not in the memory, you can basically birth a new track. I think sorry, I just repeated the same, but basically the tracks can die as well. Like if we have something in the truck that is not anymore in the detection, then we will downweight it, and over time it might die. Like it just will go to basically very low confidence. Yeah, this gives something like this where you can basically track instances over time. But although it's very interpretable, which is the good part, it's very handcrafted. It takes a lot of tuning typically, and it's restricted to object level information. You cannot really kind of reason about the whole scene, including the background over time. This is similar, but maybe a little bit more learned, is this object level feature memory that has been, there are a few more works recently. essentially you, instead of trying to track and associate the instances one-to-one from frame to frame, you just kind of bring the previous outputs to the input of the next cycle of autonomy. So essentially you provide the new perception model, like the current perception inference with the outputs from the past, even if they don't need to be associated in any way. So this is a lot more flexible than tracking, but it's also more compute, I guess, depending on how you are dealing with your previous inputs, how long you're accumulating, those could get big. Still restricted to object level information. So let's see what can be better than that. So we can also have a scene level feature memory. The idea here is that from your previous perception, you can use the dense feature maps, let's say at some point within the network. Here, we are going from the input, then backbone, and basically at that level, we call the memory. So that's what we call our memory, which is basically just one of the feature maps in our network. Then that feature map can be passed into this fusion layer at the next time step. So essentially we are the advantage of doing this late to early fusion is that you use more processing from your previous frame and you feed it very early on your next frame, which means that you can still use all the processing of your current inference to process these inputs. This is what you kind of get when you aggregate over time. This is principal component analysis over the features of the memory. And you can see how they get very dense and very, very semantic. You can see the trees in red. These are not labels. These are just PCA over the features. So this is what the model is learning. And I don't know if it will play, but yeah. So typically, basically, this is how a LiDAR actually works and how it's seeing the scene. And you can, by having this memory, you can actually do this packet level reasoning instead of reasoning at a chunk, kind of a full scan. And the reason is that now we can leverage all this compute that we've already done with this memory that we have, and then we can just reason about this kind of new update, right? New sector of information that we had, and we can update the memory with that. And from there, output detection is kind of at the scene level. This can basically help with latency. Yeah, by detecting a lot faster. Awesome. And yeah, now we got to the last part of the presentation for this section. We'll talk about unknowns. So I showed this video in the introduction, but maybe for those that joined after, essentially we were driving in Texas with our trucks and we found, we found some couch in the middle of the road, just sitting there. So this is the type of thing that we are going to cover now. How can we perceive this kind of more out of distribution, and maybe these examples don't fit as well like the traditional classes. So one approach is to try to do this open set instance segmentation by clustering, essentially. And what we are doing here is we are projecting the LiDAR points into some category agnostic embedding space, and then you can think of just basically clustering on this embedding space at inference time to put things together that belong to the same instance, and that we don't really know what they are, but we know they are something that essentially moves together or belongs together. We can also try to do unsupervised object detection. And one approach that we proposed last year was basically to first do point clustering, and then also use ground priors to kind of understand what is a likely object, like a likely cluster. Then we can train an object detector with these pseudo labels. And if it's a convolutional neural network, we can actually then run it on a this clustering typically is only good when you have very dense points, which is only near range. But you can still extrapolate to basically long range by using the equivariance of CNNs. So now you run your convolutional network that you've trained on short range, on long range, you get pseudo labels for long range now. And now we can track over time. I apply one of those trackers that I talked about to basically remove things that flicker. And we can refine these trajectories, kind of maybe smooth them out and whatnot. That gives ground truth or pseudo ground truth for now training the detector again with this new data. And you can basically do this iteratively for several iterations. And the model converges to something like on the right, where we are able to track pretty well without ever seeing any label for those objects. A similar idea can be extended and used along with a language model for open vocabulary detection. So how this works is that first you build this unsupervised multimodal auto labeling at the bottom. And this works very similar to the approach that I just talked about, where you essentially leverage clustering and tracking and some other, basically to build this offline model that can give you pseudo labels of where things are in the world. And now we are pairing that with a VLM, vision language model, that already has aligned embeddings between camera, images, and text. So what that means is that if we say, let's say, red car on the text, that will look similar to the features that you see on the image on the red car, the pixel of the red car. And this VLM can be frozen, as indicated by those snow symbols there. And then what we can do is we can now push during training the features of the point cloud that belong to those objects close to the embedding of that meaning in language and in image. And we can also train this 3D detector at the top, which is the part that will keep our inference, to have those embeddings from LiDAR only, as well as basically predict the bounding boxes. And then at inference, the whole VLM kind of goes away. We just keep the text encoder, and then we can query for any category that we care, that any word that we care. And by checking the alignment, let's say like cosine similarity, by checking the alignment between the text embeddings and the pointwise features, now we can tell which points belong to which category. And this can give you something like what you see on the right. When you query for a bulldozer, like the points in red are the ones that are firing by having a similar embedding. And then you are also getting this bounding box. So by basically, you can look at how many points are inside the bounding box that belong to this thing that you query, like a bulldozer or stop sign. And then you can reason about what that instance is. And here we didn't use any labels really, aside from, I guess, everything that was used to pre-train this vision language model that we used to train. Cool. And the very last thing I want to cover is this self-supervised occupancy. So this is the video, the same work that I showed at the very beginning in the intro. So here we are reasoning about what parts of the scene are occupied. And we show that we basically can do this from LiDAR points alone without any labels. So I'll skip this one and just get directly to the core idea. Essentially, when you get a LiDAR array, what you can essentially is a sparse proxy for what's occupied and what's unoccupied in the scene. The green part of the array here, we can consider it unoccupied. Otherwise, the array would have stopped earlier. And the red part we can consider occupied. So what we can do now is take the implicit model I talked about earlier. I won't have time to go into the details about the architecture, but essentially the important part is that your inputs are the LiDAR, and you get some high-level feature map, and then you are querying these continuous points X, Y, Z at time. And for every continuous point, the output will be essentially the probability of occupancy. And because the arrays are continuous, like I was talking earlier, and we can use this as a proxy for occupied and unoccupied, we can train essentially on these labels by querying of different occupancies along the array and balancing our positive and negative queries during training. And by doing that without any labels, we are actually able to essentially perceive the couch that I showed earlier pretty far away. So here you can see essentially on the left, hopefully, it's maybe I can try to stop it. But basically, we get occupancy here for the couch, just like we do for everything else, the guardrail, the trees, and the car. So this system that I just described can be essentially trained with no labels and perceive any object out there. Cool. Since we are a bit late, I think we can wrap up. Basically, we saw all these concepts, how to incorporate like different sensors, how to fuse them, occupancy as a emerging representation, memory for being able to reason over time, and then this how different approaches to handle unknown objects without having to basically label everything in the word. Thank you so much.
You okay with doing like 2 or 3 questions and then quickly and then just going to prediction?
Okay.
Okay.
Question?
So,
Go for it.
challenges like when you combine multiple cameras, like multiple views, like your glossiness, I think in the format, they do some analysis of that and they're able to get robustness. So can you make comments on robustness with like light perturbations and extreme calibration? And then one more thing, how to apply strong augmentations, right? In this kind of setup.
Yep.
Multi-view.
Yeah, so I mean, I actually not familiar. I mean, I'm familiar with the ViewFormer work, but I don't remember the exact results from that study. But I'll take a look again. But I would expect that basically it depends on your decoder, right? So after you've done this fusion where you are attending to the different cameras and putting the features back into the 3D voxel grid, it depends on how much processing you can afford and how much, let's say, how big of a receptive field you can afford on the decoder that goes on top of that feature map. I think you will be able to be more robust or less robust to calibration errors, right? Like the more processing you put on top, and the more, I guess, the better, the more data you have, the more robust you can be, because it can essentially, find where how it was miscalibrated by basically looking at the whole scene.
Not just errors, but also perturbation. Like let's say I just move my cameras around a little bit.
Yeah, or even vibrations, like on the truck, like the sensor can vibrate a lot. Yeah, so that calibration error cannot be just like a constant, right? It can be changing over time. Yeah, and yeah, then coming back to the augmentations, I think that's the good part, right? During training, we can play with it and know kind of what will be our deployment noise in terms of like those perturbations, and we can add that as noise, like for example, like some Gaussian noise, or I don't know what would be the best type of noise. Random crops.
That's important.
Yeah, like you also want to be robust to like even camera dropped, and yeah, great question.
So you started with LiDAR, let's say you can use some sparse models for LiDAR. However, like at the end, when you say you want to fuse camera data with LiDAR data, you come to an easy feature, which is kind of dense. I'm wondering, have you thought about, is there any way you do sensor fusion while still keep this sparse?
Yeah, that's a great question. I actually was thinking about it yesterday too when I was making the slides or finishing the slides. I think there's little work on that. It's a very promising avenue for sure. I guess there's nothing preventing you from shooting sparse features instead of dense features from camera. I don't want to give away maybe some ideas either, but basically, yeah, you can try to reason about which parts of the scene will be relevant, right? And only shoot features there, for example. So, but yeah, I think it's a super interesting area of work. And I think these sparse detectors on LiDAR right now are making great strides in terms of leaderboards and whatnot. So I won't be surprised if, yeah, we have a lot of more fusion. And maybe there is some work out there that I don't know that does this sparse fusion. Yeah.
Again, great presentation. My first question is, okay, for instance, instead of the couch, let's say you have like a piece of maybe like a plant, right? So the truck will easily run over it. Does your setup have the ability to decide, okay, this is a light object that can run over it, or instead you have to get out of the way?
Yeah, so that system that I showed there does not have that ability, because it will just reason about what's occupied and what's not occupied, not about what you can go over or not. So I think there are many ways, kind of in an unsupervised way. It would be interesting to try to model the physical properties, right, of like density, like you were talking, like weight, by how they move. But I think those are all unexplored areas. Very interesting though. And then of course, coming back to the intro, I talked about this kind of more foundation model, which this could be like a model of that sort, and then something more like a supervised fine tuning, right? So you could also move to that supervised fine tuning, that task of deciding whether this is something you want to potentially run over, or is something that you should basically keep away from, like a plant versus a couch, right? So in that case, one way would be to label certain instances, right? Examples that you want from both categories, and then only fine tune this model, the unsupervised model, to be able to basically add this reasoning in terms of semantics.
Sorry, are these slides available?
Not yet, but at some point it will be released.
The recordings for sure will be available.
Oh yeah, recording, yeah. What do we do?
One more and then we
One
can
more?
get going.
Yeah, I think you were before.
So if you
in industry, I would imagine that during your development, like for example, you will upgrade your box. For example, you would like to add or remove some sensors. So basically, for example, the positions of sensors or type of sensors, angle of sensors will fluctuate during your development. So when you like train your model using your previous sensor settings, do you observe some kind of domain adaptation issues? And if so, how do you set that up?
Yeah, that's a great question. Let's see. Many parts to the answer. For kind of the placement, that's totally right. And I think for that's why it's especially important to basically be able to track your calibration, because what that means is, let's say you change the camera from another position, right? And you are doing the shooting to 3D of the features or whatever. As long as your calibration, the new calibration is now correct or close to the true one, then I think the model will generalize a lot better than a model that, for example, assumed no calibration and no knowledge about the input placement, right? And had to figure out what's going on between these different two images. So I think that's one way to deal with it is, yeah, just use your extrinsics and intrinsics properly in the model. Now, you still might change the actual sensor, right? And that is a bigger domain gap, I guess. For that one, we can leverage, so we rely a lot on our simulator too. So we simulate all these sensor data, and we can generate data that we can use for training. And that's one way we use a lot to basically bypass this domain gap when we change and we are still acquiring data. I think it's very important also to keep using your previous data from previous sensor rigs, unless it's like totally different, because it's hard to build these data sets over time of interesting events, right? So you definitely want to leverage them. So keeping the training flexible to essentially be able to train with different sensor rigs, it's important. Yeah. Thank you.
Okay. Yeah, I think we should move on to the next session.
I can close this. Some forecasting. I think there's a video that will not work.
Oh, there's a video. I don't know. It's okay.
Okay.
All right. Yeah, thanks for staying here throughout. Yeah, I kind of ate, I think, the time for the break. But yeah, we now have this session, my last session, I guess, on motion forecasting.
Actually, give me 1 second.
Oh.
I have to do something here logistically. No Kelvin right there. Never mind. Go for it.
So let's dive right in. Yeah, as we saw before, basically motion forecasting or prediction is this reasoning kind of in the middle of the stack, if you will, where we, given kind of our perception of the world, we try to estimate what's going to happen in the future. Now, I guess contrary to perception, this is not a thing you can try to get perfect at, because there is a lot of latent variables that you don't observe about what's going to happen in the future. So it's more about how you model the uncertainty, in my opinion, rather than, or maybe both, how accurate you can be and how well you can model the uncertainty. There are things like this is probably illegal U-turn done by this vehicle here, or you can see the interactions down the road there, kind of going over a vehicle that's waiting for a left turn. So it's a very complex interaction graph. The agenda for this session is to talk a bit about the task itself. Then how do we, similar to the perception, like kind of how do we encode the scene to do reasoning? And then how do we actually model the future in terms of different paradigms or task formulations as well as representations? Cool. So yeah, about the task, I guess really quickly, some of the main challenges. We don't really get to see everything to start with, right? Like perception won't be perfect, essentially. We'll talk a bit about joint perception and prediction models here, which I think is a better fit than just propagating, basically separating outputs from perception into prediction. But anyway, basically, you don't get to observe everything perfectly. Like, for example, for that vehicle behind, we only see a bit of it. We also don't know what they want to do. Like other vehicles might want to left turn or go straight here, depending on the route, which we don't have any knowledge about. And finally, let's say on an intersection like this, there's some negotiation there going on about who's gonna go first and who's gonna go after. So the classical approach to this problem is to essentially use a tracker, like I talked earlier in the previous session, and unroll the tracker state. So with some kinematic model, right? We can assume either they are keeping constant velocity or a constant turn rate and acceleration model, or if the high definition map is available, they will follow the center lines, for example. That's something it's typically done in these more traditional stacks. So that's great because it allows us to incorporate our prior knowledge and doesn't need a lot of data. It's fast, but it cannot really capture the diversity of the real world. Like you can see there, those are the predictions versus the ground truth for different pedestrians. And for the ones that are going straight, works great. But for the ones that are doing something slightly different, then it does not. Cool. So basically, the field moved from that to doing ML-based, machine learning-based prediction, but within the same kind of framework. So we have these tracks as input, basically the past states of the objects that our tracker has been able to track, as well as the high definition map. Then we put a neural network and we output future predictions. However, here, if there's some noise in the input, detections and tracks, then it will propagate to prediction, right? It will be really hard to predict a good trajectory for something that we haven't even tracked well. There's also some redundant computation, like we've extracted features to understand these vehicles and how they are moving, and probably we need similar features to do prediction, but now we are separating that into two separate models, which is just redundant computation. And overall, it's a complicated system, hard to train, many dependencies. If the detection team changes something, then the prediction team will have to adjust. And so it's a lot of overhead. Very hard to get right. So instead, what we can do is this more joint perception and prediction. And essentially we get, instead of getting the tracks as input, we now get temporal sensor data as input. So you can get multi-sweep LiDAR, for example, there. You could also use memory like we saw in the previous presentation. And the idea is that this will output both the current state of the world as well as the future state of the world. And we'll see later in the presentation, in this section, some approaches that really unify these two. And it doesn't need to be necessarily bounding boxes and trajectories. Here we see basically, this is the same model I was showing earlier, but earlier I was showing the perceptions only. And here we can also basically forecast. What you are seeing here is the model forecasting into the future. I'll cover in more detail as well later. So yeah, now let's get into how we can actually understand the scene. So as I was talking about before, the first methods basically take these tracks, right, of the actors, these trajectories. Then we can encode these past trajectories, which is what we are gonna see how to do now, and then have some decoder which we'll cover later. And these trajectory encoders can be like, it's basically what we get as input is a sequence of waypoints, right? Perhaps with some uncertainty, different features that the tracker might give us, but essentially it's like a sequence of waypoints or states over time. And this can be, basically we can use convolutional neural networks, recurrent neural networks, or transformer, any sequence model basically to extract features from it. This is typically super fast on the prediction side because the trajectories are low dimensional, but it has very limited expressivity, right? Like everything, all the information that has already been lost by this point is huge. So an alternative, as I was saying earlier, is this multi-sweep LiDAR. And what we are doing here is we are taking multiple LiDARs over time, I think the last 5, and coloring them with the basically time those LiDAR points were captured. And you can see, for example, for this object, right, you can very clearly see actually like its movement. And not only that, this input has already kind of attached to it, if you will, like kind of how uncertain we are or how certain we can be based on the observations that we are getting, right? We are not just getting that we thought this object did this trajectory. We are actually getting the points so we can reason about oh, we didn't have many observations, so I'm gonna be more uncertain in my predictions, or I had a lot of observations and it's super clear what's gonna do. So how can we, well, the way we can put this together is essentially, like we saw earlier, we can, for example, voxize it in bird's eye view. It could be sparse, it could be dense. We get this feature map. And then from the feature map, we can do object detection, for example. And around the object locations, we can extract certain features and pull them. And from here, we essentially can get an agent feature vector that is kind of the embedding for each agent. From this, the simplest form of prediction, I guess, is taking these agent feature embeddings, passing them through an MLP, and that will give you a future trajectory, right? And the future trajectory here can be as simple of predicting a 2 times t vector, which is like the 2 coordinates x and y in bird's eye view, times t time steps, which is like the amount of time that you want to predict into the future. And this is like CVPR 2018 was the first paper that did something like this. And these are very short range predictions, and it's not great, but the field has advanced a lot since then. And the same ideas with new architectures and the new loss functions can work very well today. Cool. So I won't talk too much about the high definition map. We already covered it in perception. So this is just a quick recap for those that joined now, but basically the map can be represented in a sparse way through this set of vectors, basically. And we can encode it with any sequence-to-sequence model like graph neural network or transformer, and learn rich node features, basically. And then we will be able to use these learned features downstream for prediction, like we'll see in a bit. And finally, there's these actor-to-actor interactions that are everywhere in the scene. So in this 4-way stop intersection, for example, based on the past, we cannot really tell what's going to happen. Here, it's more about knowing the rules, like maybe they will yield to the right vehicle, depending, I guess, where. And also just sort of doing relational reasoning to try to understand, maybe if this object is moving a little bit, that means it's going to go and the other one's going to yield. But anyway, it's going to be a very uncertain prediction. And so, yeah, we are talking basically about this point, like we've already extracted agent features, and now we are trying to do some interaction reasoning between the different agents that we've perceived in the scene. So how can we do that reasoning? One way is with graph neural networks. Let's say if every agent is a node in this graph, and then we can assume a fully connected adjacency matrix to basically reason about all the connections between them. Basically, we can extract features like those agent features will become node features in this graph, right? And then we can exchange messages between them, for example, with an MLP. Then all the messages incoming to a node can be pulled with a permutation invariant pooling, like max pooling or average pooling, any pooling mechanism. And finally, we can update the node state of every node. This is just showing one for sort of visually explaining it, but this happens in parallel for all nodes. They can all be updated with a residual connection or with a gated recurrent unit, for example. And the same can be done, of course, with transformers. Transformers are kind of a special case of graph neural networks in which the message and aggregation are fused into this dot product attention. So basically, dot product attention is taking care of which messages, basically weighting the messages from incoming connections. Cool. So now let's see one example of how to put this together. This is a paper that we released on arXiv a week ago, I think. But basically, on the left, you can see we have these object queries and poses volume. So it's going to be a bit abstract, but basically it has 3 dimensions. There's an object dimension, basically number of agents, maximum number of agents. Let's say that your model is modeling, let's say 400 or whatever it is. You have a time axis, which is like the future time that you want to predict. And then we have this mode axis, which is just to be able to predict different modes of the future distribution. So the way you can think about this cube is that essentially we are modeling the different hypotheses that we have for every object in the scene over time. And so each grid cell means our beliefs about the position at that time of that object for that particular future. And now we are trying to refine this in a refinement transformer end-to-end to basically get the detections as well as the predictions. So detections here are just the special case basically t equals 0, right? If you think about the trajectory of the object over time. And this refinement transformer is consuming LiDAR from an encoder, LiDAR features from an LiDAR encoder and map features from a map encoder. And then we can run this refinement transformer iteratively for B blocks, and that can give us our refined detections and trajectory predictions. So let's see in a bit more detail how this works. So we extract LiDAR features like we saw in the previous session. That can give us, for example, multi-resolution tokens. So it's just multi-resolution features basically of the LiDAR in bird's eye view in this case. From that, we can initialize the poses, this volume that I was talking about, to maybe be, let's say, stationary object, like an object detector can give you an initial pose that can be the same pose over time for all objects. This is just a really bad estimate, but it's a starting point for the model to then refine it, as we'll see later. Then we have our high definition map. We run it through some lane graph encoder map, and then we get these sparse tokens, right, of the map. And finally, we can initialize also features on this volume to just describe essentially anything relevant to the motion of the object at that time. These are initially randomly initialized at the beginning of training, and they are just parameters basically of the network, these initial queries. And from here, we can go into this refinement transformer, which essentially is doing all sorts of attention that we'll talk a bit more detail in a second. And it's attending, I guess, both to the inputs, like the LiDAR and map tokens, as well as doing self-attention. And then we can literally just update the initial poses volume, right, and the queries. And at the very end, the poses volume will be our detections and predictions. Essentially, we designed an input that we are going to be refining, right? And at the end of this process, those are our actual predictions. So these are how kind of the attention works and the inductive biases that we bake in. For the position of the object at that time, or the position that we believe the object is, we can essentially do deformable LiDAR attention, which is an efficient attention mechanism that won't cross-attend to every token, but instead just cross-attend locally with some learned offsets. And we can do something similar with the map too, where we can just do, for example, K nearest neighbor map attention. That way we keep it efficient, and this kind of local reasoning allows us to refine the position of the object. And finally, we also can do self-attention. We factorize it because otherwise self-attention in this cube will be very expensive. So we do self-attention on each of the 3 axes of the cube. We reason about object interactions, about the different modes that we are predicting, as well as about time throughout the trajectory. And these are sort of what the model does. So initially, as I mentioned, we initialize it to be all stationary objects. And then after one refinement, it's already pretty decent at speed estimation, but you can see it has some map following problems here. And after another refinement, iteration equal 2, we still have some issues. But in the third one, the predictions get pretty good by basically just attending to the local neighborhood of features. And this is basically at every iteration, we are refining. This is just over time. At every iteration, we are refining basically both the detection as well as the predictions. They are just because we are just refining this post volume that basically captures both. Oh, and most of the time for this section is for this last part here, which is about what are different, like actually prediction is kind of a very overloaded term. And there are many different tasks that one can formulate that kind of tackle similar problems, but not exactly the same one. And then there's also the representation aspect. Like, do we want to predict future trajectories? Do we want to predict the future sensor data? Or do we want to predict, for example, occupancy? So we'll cover all those. Maybe to start with something visual. So here what we are doing is we are predicting what that car might do. And we are saying, it could be in these 2 places at some point in time, let's say 5 seconds into the future. And now, if we try to answer like what the self-driving vehicle can do, really the only option is to kind of brake and go after the vehicle, right? And that's a pretty hard brake. But as we'll see now, like this is not how the model, how the world actually works. How the world works is that these are joint rollouts, and the vehicle might yield to us, right? And we might go first, or the vehicle might accelerate and we need to go after. And you can see the futures for the two vehicles align with the futures for the two vehicles there, but the futures for the ego vehicle, like the self-driving vehicle, actually none of the two cases we had to hard brake as hard as we had to hard brake in this marginal prediction setting, which is basically telling us that that's not a great problem formulation, even though that's what most of the prediction models do today. So we can define multiple prediction tasks. This is the marginal prediction is what we had on the left, meaning that we are modeling each agents independently and trying to predict the distribution of each of them separately. Basically, you can see the color in yellow for one of them and in blue for the other one. We can instead model the joint distribution over different agents. So here you can see that there are joint samples, right? Like we have the pink future and the purple future. And these are joint futures across all the scenes. Basically, these are telling us the future might roll out in this way at a scene level or in this other way. And finally, we have conditional prediction as well, which we won't talk too much about, but it's also very interesting. Essentially, we have some power about what the future positions of the self-driving vehicle, right? We are controlling it. So we can try to condition the model on different future actions from the ego vehicle. Of course, you cannot be certain 100% of where your ego vehicle will do because you might change your plan in the future. So it is a very hard problem, but very interesting. Cool. So how can we represent basically these futures? It can be as trajectories. We can try to predict the future sensor data as well. We've seen many world models recently that do this. And we can also try to predict the future occupancy. So let's start first with trajectories. Kind of the simplest form of trajectory prediction is this mixture of Gaussian trajectories. It's a very simple parametric representation. We are essentially saying there are these k futures that are possible, and each of them is a sequence of bivariate, for example, Gaussians or Laplacians. And actually, if you take the negative log likelihood of this distribution and you try to train with it, it will actually not work very well. It results in mode collapse and instabilities. And what people have proposed are kind of mitigations around it by using this winner takes all loss, which essentially the idea is that because you only get to observe one of the possible futures, you only want to train from your predictions the closest one to it. So you are basically being optimistic and saying, if one of my futures is kind of close to the ground truth, I'm going to reward it. I'm going to train that mode. But the problem is that the rest of the modes are left untrained. So yeah, some of the modes at the end of training can be sometimes, if not very carefully trained, not good. Another option is to go with trajectory sets. So basically, we turn the problem from regression of trajectories and kind of the parameters of those distributions I was talking just now to a classification problem over a predefined set of trajectories. So here we can have, basically, we can try to get coverage from our sample set, which we maybe can get through clustering of our data set or just some parametric sampler that we can get. Essentially, we are classifying over a fixed set of potential trajectories. One method that was very popular and worked very well and got a lot of state-of-the-art in past years was this goal-based prediction. Essentially, you break down the problem into predicting first the hardest part, which is like, where's the vehicle going to be at the end of the trajectory forecast? Like that's what's called the goal typically. And then once you have these goals, you can predict how like the trajectory will complete from the current position to the goal and what's the score of that trajectory. So it's kind of unintuitive that you need to predict the goal first and to then predict how to get there. But if you think about it, because it's the hardest part, you can put more computation allocated to that, and then less computation allocated to predicting like the easier part. So I think that's kind of one intuition of why this works well in practice. But one drawback with this is typically goals are generated, let's say, from map nodes. So if you are trying to predict also non-compliant behaviors, maybe objects coming from unmapped areas, this can be a challenge for these methods. Another approach, which is similar to what I covered earlier with our work DETRA, is this refinement based. So you predict some initial trajectories. They might not be very good, but they allow you to focus the computation around local areas and then refine these trajectories over multiple iterations. Cool. So these are sort of representations, generic representations that one can use for marginal prediction, for example. And the way marginal prediction is evaluated, let's say we are predicting these three modes, predicted scene 1, 2, and 3 here. And then this winner takes all loss that I was talking about earlier will basically take the closest mode to one of the futures, let's say the orange one for the top vehicle, and also the closest mode, the closest prediction to the ground truth future in black for the other vehicle, in this case, the purple one. So we are kind of mixing modes, different modes from different vehicles to get the lowest error. That gives you a proxy for after training for the marginal distribution. But as we saw, that's not great. So we can instead do this winner takes all loss, but at the scene level. So instead of considering the best mode for each object, you consider the mode that gives the scene level mode that gives the best average error across objects. In this case, is actually the green one, which is neither like of the two that we got in the mean FDE case. And by doing this, basically we can extend kind of trivially or pretty easily any marginal model into a conditional model. Like for example, for this model on the right, it literally takes the marginal predictions as input, like the different modes, and just predicts how to recombine them. Like basically it weights them different modes in a way that you can get new modes from a linear combination of the previous ones. And you train the first system, the trajectories on the left with the winner takes all at the agent level, and basically the ones on the right with the winner takes all at the scene level. Cool. But instead of just doing this winner takes all, which is a bit kind of empirical, like it's not really the true likelihood of the distribution, we can try to do something better. From the agent features, essentially, we can try to predict a latent representation of the scene, which basically this latent, you can think of trying to capture everything that is not in the sensor data. So for example, you can think of this latent as capturing the intentions of the vehicles or the future traffic light states, which is something that we don't know about the scene. And then we can sample from this latent distribution. And given the sample of the latent and the input, we can run it through our decoder and predict one possible future. And we can do that many times and predict basically multiple different futures. And this can all be trained as a conditional VAE. And what this allows is to sample actually realistic futures at a scene level. So here what you can see is two samples from the model where essentially the model got at understanding that at an intersection, the traffic lights are controlling the scene. Even though it doesn't know what's going to happen in the future, it knows that the traffic light might stay green for the vehicles going north, or it might change the state and it might allow the horizontal traffic to flow. And this is very cool to see because the model wasn't trained with traffic light data at all. It just understood that at intersections, sometimes traffic light state can change, and then the whole scene changes. And because you have this continuous latent variable, you can also interpolate through it. So if you take basically two samples, which are the extremes of these GIFs, and you interpolate through them, you can essentially get this, basically latent interpolation, which is pretty cool to see that it can capture things like interactions at the bottom left, where you can see like basically if the lead object goes faster, the rear object goes faster too, or map understanding in the bottom right, where basically we can understand that it might left turn or do a U-turn. And here is kind of squashing everything together. So we are sampling 50 times for that joint distribution and then overlaying them with transparency based on just the frequency of that position and kind of displaying it as occupancy. And you can see that the model actually, for the time this was, which is 3 years ago now or 4, I believe, it was a very good understanding of what might happen in the future. Cool. And more recently, autoregressive models have kind of made a comeback, I guess, after all the success of next token prediction with language. And there have been a couple of very interesting works in this in the last year or so. What these models do is that they basically predict future trajectories by decomposing the problem about sequentially predicting the future. So basically, I'm at time equals 0, I'm trying to predict the distribution over things that may happen at t = 1. And then at t = 1, given a position, a sample from basically the previous distribution I was talking about, you will basically predict a new distribution for t = 2 and sample again. So this autoregressive sampling is very well depicted in this figure. Basically, we can tokenize the possible futures. That's what you see with the different objects those are basically tokens that the network can predict. So essentially, we are doing classification at every step, and we are trying to predict which of these different modes per time step could be the true one. And the good part of this is it breaks down the problem a lot. So you don't need I guess, as opposed to the trajectory sets I was talking earlier, where you might need thousands of trajectories to define or describe what might happen in the future. Here, you just need a lot less per time step, because essentially by having this very simple distribution chained over time, you can have very complex trajectories from a very simple conditional distribution. So this is very akin, to next token prediction in language. One of the drawbacks, of course, or the main drawback is that sequential sampling can be slow. Like at every point in time here that you're predicting into the future, you are trying to run, you're basically running some model. I guess it's all about how small can you make that model, but whether it can run real time or not, I think is yet to be seen if this can be great for motion forecasting, but they are definitely very good for behavior modeling in simulation. Cool. So we've talked a lot about these trajectory prediction, but more recently there have been a lot of effort into world models that essentially predict the future sensor data. So let's look at it. This is a video from Gaia-1, which is a model from Wave, which had very impressive forecasting abilities. This is the model actually predicting the future for a pretty long horizon in a pretty realistic way. Of course, there are artifacts, small details, but it's very impressive, the performance of this model. Let's see a bit how that's done. So basically, video data is widely available. That's one of the main benefits of this type of representation that forecasts sensor data. So we can train, it's very super cheap to collect. You just put your vehicle out there and collect data, and you can just train from those future sensor data, right? And basically, it leverages advances in LLMs to tokenize the input modalities. Then all these inputs are fed into this world model, which is essentially a big transformer. And it's trying to predict tokens that essentially represent the future. These tokens that we predict in the future will be decoded by a video decoder in this case. But here, this is actually something that is great for let's say an offline model maybe, and definitely for a demo, but it's actually this could not be done online in a vehicle. Like that model I showed had about more than 500 tokens for every time step that you are trying to predict in the future. And it's basically auto-regressively predicting every single token. So for just predicting the next frame, it has to do 500 and something iterations of predicting the next token, right? And then that gives you the next frame, and you keep doing that. So it's very slow. It's not yet ready for onboard autonomy. And it's not clear how really to use it for autonomy, like maybe distillation, but that's something to be explored. We also had a similar work, but on LiDAR. Last year was presented at iClear, and basically here you can see the predictions for the actual actions that the vehicle did in the log versus like some counterfactual actions, right? Because these world models can be queried with alternative futures. Essentially, if the ego does this, what's going to happen? If the ego does this other thing, what's going to happen instead? And here you can see it in bird's eye view, where on the left, this ego vehicle is going with like a cruising speed. On the right, we are hard braking. And we can see that the vehicle, it's hard to see, but there are some points over there, basically behind the ego vehicle, that represent another vehicle. And you can see that how it reacts differently. On the right, it's basically following the ego fast, and on the left, and on the right, it's actually trying to basically brake behind the ego vehicle, right? Which is probably what would happen if somebody tried to follow. Sorry, it's a bit hard to see, but yeah, this is the points of the object. You can see it traveling over time, this cluster of points, and here. Cool. So this works actually in a similar way, but by doing some smart, I guess, design in terms of inductive biases, we are able to bring down the number of parameters very heavily. So the previous model I showed was a 6 billion plus parameter, and this model I was showing is under 100 million parameters, which is a very, very substantial decrease. And of course, this can make the model faster. We also, I don't have time to get into details, but we also use this discrete diffusion, which parallel decoding, which speeds up a lot. Instead of predicting these 500 tokens one at a time, like I was talking about, you can predict, let's say, 100 on every step, and do that for 5 steps only instead of 500. So it's still, this is kind of a step in the right direction. It's also reasoning in 3D, which is closer to what autonomy needs to do, but it's still not fully clear, like how to distill this to the actual onboard system. In general, my takeaway from this future sensor data is that there's a very open question about how to actually use them downstream. So let's now see the last output representation that we might consider, which is occupancy. I think actually this is a very good middle ground between trajectories and sensor data. So it's interpretable like trajectories, like we know what being occupied means and not occupied, whereas the color of a pixel or a point in the point cloud, it's a lot harder to interpret. But we can capture arbitrary shapes just like sensor can, as opposed to the trajectories, which assume this like rigid body, right? So let's say, yeah, and it's very easy to use in downstream planning because the downstream planner essentially wants to avoid any occupancy, right? Just to illustrate here, what we mean by this occupancy flow is on the top, you can see like a grid and what's occupied. And basically on the bottom, we can predict the motion also in a non-parametric way. This is not for every agent. This is just at the scene level. What's the motion? And then by basically, we can warp the occupancy with the motion to predict the future. And this have been applied even in this is a end-to-end driving model we had years ago. And it can do pretty cool reasoning. Like you can understand that this vehicle might go straight or turn left or turn right. Like you can see in that occupancy distribution, this pedestrian might cross the crosswalk or continue in the sidewalk. And it also can reason about our uncertainty on the perception side, which is like on that area, we don't really see, right? Like it's occluded by other vehicles. So it can predict the occupancy over there too. I forgot to mention, but the boxes here are just the ground truth. The outputs of the model are the occupancy. So these still have several challenges, which are, first, they are pretty memory hungry. We talked a bit earlier about implicit architectures, but we'll review them again in this section. And then it's also label hungry. Like this is still trained with actual like labels for every object in the scene. And we'll see how we can train it out just from pure LiDAR in the future. So yeah, this essentially implicit occupancy fields that we saw earlier, right? Like we try to predict the future by basically getting a continuous query point XYT and the model outputting that occupancy and flow at those locations, like as seen on the right. So instead of predicting them on a grid, I mean, we can still predict them on a grid. We can just query XY for every XY point on the grid, but we don't have to if the planner doesn't need that. So intuitively, let's see how this works. So we have the scene, we have extracted our features, like let's say for LiDAR, and we are getting this query point at the bottom of the screen. So really, and let's say this is into the future, right? Like let's say we are getting, what's gonna be the occupancy there in 3 seconds? It's actually like the evidence for what might be there, it's not there in the feature map, right? It's wherever it was at t equals 0, not where what we are interested at t equals 3 seconds. So what we do is that we predict an offset to basically we ask the model where to attend on the features to basically answer the question of whether this will be occupied at 3 seconds or not. And here in this case, it would try to attend to basically this object that is on the same lane, for example. So we took this intuition and we put it into a model. So we take LiDAR and map, we get some bird's eye view feature map. Then from that bird's eye view feature map, we basically get a query point over here. We can interpolate the feature map at the query point location. So let's say that point 3 seconds into the future, right? We just interpolate at the XYT location. And then we predict these offsets that I was talking about where else to attend in the scene. Basically, where's the relevant information to answer this query? And then we can cross-attend to that. And as well as have this residual connection, which also brings the time, position, and encoding that we are requesting into this final MLP. The MLP predicts the occupancy and the flow for this query point. And we can do this for a batch of query points in parallel. Yeah, so these are the outputs. I showed something earlier similar in the previous presentation. That was just the unroll of the perception outputs over time. This is actually showing what we are predicting. Like basically we are querying the model on a grid for the multiple different time steps into the future. So this model really unifies perception and prediction 100%, right? Basically, we have some features of the scene, and then we just have this time query that controls which time the occupancy we are getting is at. Cool. And yeah, the last part, we'll talk about this unsupervised occupancy. Last year at CVPR, we saw a very inspiring paper, which is this 4D occupancy paper, which what they do is from historical LiDAR sweeps, they try to predict this future 4D occupancy, basically meaning 3D occupancy over time. Let's say you can imagine multiple voxel grids. And actually, we can differentiably render this into a point cloud, right? If you have the occupancy probabilistically, you can shoot rays and basically render where the ray would end according to the occupancy, basically depth rendering. And that, once we have that point cloud, that future point cloud can be supervised with just the ground truth future point clouds from the future. So this doesn't require any labels. Now, the specific architecture and loss function needed some work, and these works did not capture very well, for example, dynamic agents. Like it didn't predict very well the motion, even if it captured the occupancy pretty well. So we have this model that I just talked earlier, but basically we extended it to not just be able to perceive in the current frame, but being able to forecast in the future the unsupervised occupancy. So we can still use the same unsupervised task objective. Like for every ray, we can define an unoccupied and occupied area. And these rays that do not need to be current rays. They can be future LiDAR rays that we observe from the log, right, during training. And by training with this sparse occupancy supervision that we get for free on future LiDAR point clouds, we are actually able to improve the results of this type of framework a lot. So on the left, you can see the initial baselines that kind of propose this framework, which are good at modeling the occupancy, but have a hard time modeling modeling the dynamic objects. And in the middle, we have this model that I was just talking about that we proposed where, we basically the occupancy we are predicting over time is actually over the future. And this is not a generative model. That's why you see like this spread of occupancy. We are actually predicting like what's all the potential occupied, right? Like at a probabilistic way, basically, instead of trying to sample one possible future at a time. Yeah, and then we can take this model that has been trained in a totally unsupervised way, and we can supervise it with ground truth labels. Let's say for something that we care about, like vehicle category or pedestrian category or anything. And what we see is that we can actually, this is on the x-axis you have in logarithmic space, the number of examples that are used for training. And we can see that a low number of examples, let's say under 100, especially, or even under 1,000, this type of basically unsupervised pre-training first with then supervised fine-tuning only on a few labels can give very, very, very substantial improvements, like 20 points MAP at 1,000 frames. Of course, this gap closes the more annotated data you have, but that's also very expensive to annotate that much data. I think these experiments are on Argoverse, if I remember correctly, and that 100,000 is basically the full data set. So we can see that even with the full data set of annotated vehicles, the unsupervised pre-training plus fine-tuning is still better. And yeah, this is just, oh, great, okay. I can play the video, but basically the middle, on the left is just the future LiDAR reference. On the middle is the 4D occupancy that the model predicts in an unsupervised way. And on the right is this bird's eye view occupancy that we were able to fine tune with labels. And so the model can do these different tasks. We also show in the paper that it can do point cloud forecasting by fine tuning as well, not just 4D occupancy forecasting. Cool. And yeah, to wrap up, basically, we talked about how to learn a rich representation of the scene from many different inputs like trajectories, sensor data directly or high definition maps. We've talked a lot about how to model this uncertainty with different output parameterizations. And this is really key for basically safety and allowing the planner to understand the risk of different maneuvers. And we've seen that these joint predictions, inconsistent predictions at the scene level, can lead to more proactive planning by basically better showing the planner like what are the different potential rollouts of the work. And yeah, finally, we've seen that occupancy, I think it's a great alternative representation. It can capture any shape and uncertainty like we can with sensor-based world models. And it can also be effectively pre-trained in a supervised manner and then fine-tuned for any task that we may care about. Yes, so that's the end of the presentation for the motion forecasting section. Thank you. Do you want to do any question? Yeah, if there's any question, we can take a couple.
If not, there's probably a bunch of.
Explain how we use transformer and other type of model to predict motion and something.
Wait.
Rain dots on that.
Hard rule on what, sorry?
Rain dots.
Oh,
I would expect that sometimes this model will.
Yeah. Yeah, so the question is whether, for, let's say for a learn-based system like Transformer, whether we have some guardrails to basically make sure that the predictions are realistic, right? Yeah, so I think guardrails can be good and bad. If you have a very bad model that tends to hallucinate, I guess, bad predictions a lot, then you might need guardrails, but at that point, it's also a question whether that model is worth much. And in the contrary, if the model is really good, I think guardrails can be detrimental because you might actually be predicting that, let's say, something illegal is about to happen. But then with your guardrails, you might remove that, right? So I think, yeah, in general, the best or the way I like to develop or I think about it is I think we should have as little guardrails as possible. I think we should have them at the system level, at the very final output of autonomy. But I wouldn't want to have these guardrails at, let's say, motion forecasting level where we are trying to predict the future in the best way possible. It would just, I think, limit a lot what the models can do. So it's more about, I think, having the right metrics and being very conscious of what's the level of, let's say, hallucination of this model, should we deploy this or not, and rather than try to kind of fix it with some heuristics. Yeah.
No, that makes total sense. But for the full system level, we do have more radars.
Yeah, if you're asking about Wabi, I guess I cannot disclose exactly what we do, but I do think it definitely makes sense to have guardrails at a system level. Yeah, we'll have a session on motion planning, so we can talk more about how those are designed. Yeah.
I think we can go to motion planning, and then right before the lunch break, we'll stick around for
Any more questions people have? Okay, let's do recording.
Yeah, I was able to catch up a bit on time. Like the perception one was longer.
Oh, yeah.
Yeah, I have a question about the hardware area. So,
Yeah, we'll do it like right after this talk. So we're doing motion planning now.
oh,
We're doing motion planning now, and then we will have the lunch break. So we'll answer more questions then. Yeah, you're welcome.
Something like a velocity. And then trying to also classify. I'm not sure it's so. We're trying to identify. So.
Yeah, you can like make the text bigger. Yeah. Cool. Let's get started. Hey everyone, my name is Kelvin. And in this session, I'm going to talk about motion planning and controls. Okay. Can you guys hear me? Cool. Yeah, so my name is Kelvin. I'm a researcher at Wabi, and in this session, I'm going to talk about motion planning and controls. And before we dive into the details of motion planning and controls, let's revisit how they fit into the broader autonomy stack.
So if we were to take a look at a traditional autonomy stack, you'll see something like a cascade of different modules from perception, prediction to planning to controls. And this has the advantage that the stack is very interpretable and there's a very clear separation of responsibilities in between each of the modules in the stack. However, these systems typically have very narrow interfaces in between each of the modules. So you have really little information propagation in between them. And each of these modules are also typically optimized independently. And so each improvement to each submodule does not always translate to improvements in sort of like the broader system. So what we really want to be able to do is to train this entire system with the end task in mind, right? So as Sergio probably mentioned earlier today, on the other side of the spectrum towards this goal, we have these black box end-to-end approaches where we can replace all the modules of a traditional stack with a single black box neural network. Now, this approach solves a lot of the problems that we just saw with the previous one. It eliminates sort of the narrow interfaces in between independent modules, and it allows us to train neural networks that end-to-end optimize for the end task, right? However, with this black box approach, we lose interpretability. And this makes it really difficult for both developers to like understand, debug, and improve the system, as well as it makes it really difficult for systems engineers to validate and verify the safety of this like tremendously complex system, right? So the natural question to ask then is, can we get the best of both worlds? And as you can probably guess, we think the answer is yes, by building these interpretable end-to-end autonomy stacks. And as before, the overall system is still modular and interpretable. So you still have perception and prediction, predicting these intermediate representations of how the world looks like and how it would evolve over time. But now you have these, but now the interfaces in between each of these modules are made significantly more broad, thus allowing information and uncertainty to propagate throughout the entire system. And moreover, the full system is now end-to-end trainable through motion planning and controls to optimize for the end task, right? So in this session, we're going to cover some topics and recent research on how we can learn these interpretable end-to-end systems from the perspective of motion planning and controls. So in the next like 30-40 minutes, we're going to cover the different inputs and outputs to such a system, how we can train these systems, right? How we can design an interpretable end-to-end autonomy stack. And we'll also touch a little bit on how to design the system so that it can react and interact with other traffic participants more naturally. And then finally, we'll go over some of the main ways we can then convert the system's motion plan into actual control commands that we can then send to the vehicle to make it move. Yeah, so let's get started with inputs. So one of the most natural inputs to an end-to-end motion planner is raw sensor data. We've already covered sort of the various sensors on a self-driving vehicle in detail in the previous session. So here I'll just do a quick rundown of some of the more common sensor modalities being used. So first one being camera. It's among one of the most popular input modalities because they're cheap, can capture high resolution images of the world with rich textures and fine details, but they lack depth information, so we can't get 3D geometry right off the bat. LiDAR point clouds are another popular modality. So compared to camera, they give us really accurate 3D geometry. And what that allows us to do is build these, is to use this information to directly identify where's the free space in the world, where are the occlusion regions in the world around the self-driving vehicle. And as you can imagine, this can be really useful for planning a safe maneuver. Moreover, LiDAR is also more robust to lighting conditions than camera, and but they lack sort of the texture and the fine details captured by camera images. And then finally, another popular sensor is radar, which can give us radial distance and velocity measurements. Compared to LiDAR, radar can help us capture much longer range information, but they're generally more lower resolution than LiDAR and suffer from various different kinds of artifacts. So now it should be clear from this discussion that these different sensor modalities are not mutually exclusive, but in fact complementary to each other, since they capture different kinds of information and have different kinds of performance characteristics, right? So this is raw sensor data. Another source of inputs are the intermediate representations coming from upstream modules like perception and prediction. So this can be in the form of like course bounding boxes, right? Or occupancies, which tell you like which parts of the world are free space versus occupied, as we learned in the previous session. And then, or it can just be like a set of affordances or costs. Like, for example, what is the distance of the self-driving vehicle to its nearest actors, right? So these intermediate representations are more lightweight than raw sensor data. So this allows us to design more efficient methods or models to process these inputs. However, you would lose some of the details present in raw sensor data, and there are still other artifacts that you would need to handle. For example, like what happens if detections flicker a little bit over time, right? Cool. Yeah, next is HD maps. This is another super useful input modality to end-to-end motion planning because it gives us a really good prior on where the SDV can drive, right? How it can reach its destination, or the kinds of traffic rules around the SDV, etc. And this can be represented in various ways. For example, we can have rasterized images. We can represent it as lane graphs, or again, as a set of affordances. For example, like the distance to the center line of the self-driving vehicle, or how far it is to the upcoming stop sign, right? So each of these representations have their own pros and cons. For example, rasterization is super simple and can be easily processed by CNNs. But the features extracted generally have limited reception fields, and it's really difficult to encode priors into your motion planner, like saying, I want you to drive along the center line using rasterized maps. And you'll just need to sort of hope that your model has learned to do this, right? On the flip side, affordances make it much easier to encode these priors, but then it requires manual feature engineering to determine sort of like which affordances you would actually want to give to the model and how you could actually compute them. Right. And then finally, another super important input to motion planning is the intention of the self-driving vehicle, because ideally we'd like our self-driving vehicle to actually drive to some destination rather than just like go around and randomly, right? So these are usually, this intention is typically represented as routes, which can be a sequence of lanes, or maybe we can just extract a sequence of commands from the routes. So for example, we can say like in the upcoming intersection, you want to make a right turn. Cool. So that covers inputs. Next, we'll take a look at several different output representations for an end-to-end motion planner. So one of the most straightforward ways is to have the motion planner directly predict steering and acceleration. Another approach is we might have the model predict a trajectory of waypoints representing sort of where we expect the ego vehicle to be in the future, right, over time. And then we can use a very simple controller like a PID controller to then generate a sequence of steering and acceleration commands to track that trajectory. Now, both of these representations are super simple, and they're pretty well studied in the literature. However, it's really difficult for us to encode prior knowledge into the model with these output representations. And it's also very difficult for us to interpret why the model would choose to output a particular acceleration or steering value versus some other ones, right? So an alternative representation that is more interpretable is to predict the cost of a trajectory. So this follows sort of the idea from traditional planning approaches, where you have some objective function that measures the goodness of a trajectory, and then you want to find a trajectory that then minimizes that objective function. So here, instead of writing that objective function manually, you would learn to predict that objective function instead, right? Then once you have this cost function, we can then sample a bunch of trajectories, compute the cost of each of those trajectories, and then we can pick the one with the minimum cost to use as our motion plan to execute. So for example, here in this figure, we're depicting a spatial temporal cost volume that's predicted by the NeuroMotion planner, and each voxel in this volume basically represents the cost of the SDV being in that particular location at that particular time, right? So you can use this cost volume to then cost a bunch of trajectories and determine the best trajectory to execute. Now, the strength of this approach is that once you have this, it's very easy for you to encode prior knowledge into the system. So for example, if you have constraints about avoiding collision, for example, right? We can just add those as additional costs on top of the learned costs that we have in order to encourage avoiding collision. However, usually we don't have ground truth costs that we can use to directly supervise a model to predict them. So then we'll need to come up with different learning objectives, and this usually makes training a little bit more challenging than usual, right? Yeah, and besides these two main representations, there are also a couple other possibilities as well. So for example, we can predict a set of affordances, like the SDV's distance to its nearest center line or distance to its nearest actors. And then these affordances could directly be used by a controller to determine actuation commands. Or we can also train the end-to-end motion planner to perform auxiliary tasks like object detection, segmentation, depth completion, or optical flow. And these auxiliary tasks not only improve interpretability, because now we can see like sort of what the model is observing, but it also helps the model learn better feature representations that would ultimately result in better planning. Cool. So we've covered inputs and outputs. Next, let's talk a little bit about how we can actually learn these kinds of models. So one of the most straightforward ways to do this is via open loop learning. So in open loop learning, the policy's actions are never actually executed during training. So it never has a chance to observe the consequences of its actions during training. And one of the most common ways to do open loop learning is behavior cloning. So here the model observes expert states, and it simply tries to imitate the expert's actions. So the loss function for supervising such a model is can be as simple as a L2 loss between the predicted and ground truth controls. Or if you're using something like a cost-based planner, we can use like a max margin objective that encourages the model to cost non-expert trajectories, like trajectories that it rolled out itself, to be higher than the expert trajectories. For example, any trajectories that you collected from a human expert driver, right? Now, the strength of this approach is it's very simple, right? And it's very easy, and it typically has pretty high sample efficiency. However, because the model's actions are never actually executed during training, it will only ever observe expert states during training, not the states that it would see had it actually followed its own actions, right? And what this means is that this leads to a distribution shift between training and inference. So when you're actually deploying the model during inference time, the model will actually plan out actions and it would execute its actions either in the real world or in simulation, right? And it would potentially make mistakes and encounter states that it would have never seen before during training. And these mistakes can compound over time, leading to sort of catastrophic errors. So this creates a distribution shift between training and inference, and it's typically why open loop learning suffers from problems when you sort of try to deploy it to a closed loop setting. Now, typically there's ways to alleviate this issue using data augmentation, right? But the fundamental problem of distribution shift still occurs if you're using open loop learning. Yeah, so on the other hand, to address this issue, you can use closed loop learning. And in closed loop learning, the policy now actually gets to execute its actions during training, and it will actually see sort of the states induced by following its own actions during training as well. So compared to open loop learning, there's now no distribution shift between training and inference anymore, because in closed loop learning, you're actually executing your actions, right? However, to actually do closed loop learning, we'll need some way for the model to actually execute its actions. And we will either have to do this in the real world or using a really realistic simulator. And once this prerequisite is satisfied, then the question is, how do you supervise a model in these now unseen, new unseen states that we might not have potentially collected data for, right? So the first approach we'll discuss, it makes use of an interactive expert for that purpose. So for example, in dataset aggregation or Dagger, during each iteration of training, we'll unroll the learner policy in the environment many times. And then we'll query an interactive expert to help us label the state's visit by the learner policy with optimal actions. And then finally, we're going to retrain the learner policy on these new state expert action pairs and repeat this process many times until convergence. This allows us to supervise the policy with expert actions, even in out of distribution states. However, interactive experts are often unavailable, right? Or they can be prohibitively expensive to include inside the training loop. So what can we do if we don't have an expert? Another approach is maybe we can design and train a privilege policy and then distill this privilege policy into the learner policy. So for example, we might train a privilege policy that has access to ground truth simulation state information, right? And then use this policy to supervise a learner policy that only has access to raw sensor data. Now, the reason why this might work is that the privileged policy then can act as sort of an expert to supervise the learner in the same way like we use an interactive expert in Dagger. However, in this approach, the learner policy is now upper bounded by the performance of a potentially suboptimal expert, right? So designing a good privilege policy here is really important. Now, if we don't have access to an interactive expert, we can also use reinforcement learning to train the learner policy with explicit reward functions and closed loop. So again, this can be done in the real world, which eliminates the possibility of a sim to real domain gap, but it's difficult to scale this safely. Or we can also do this in simulation instead. In this case, having really realistic simulations is really important to minimize the sim to real domain gap, right? And we'll see in later sessions how we can actually do this. And even then, the sample efficiency of these approaches can be prohibitively low, right? So one way to improve sample efficiency then is to use approximate, so how can we actually improve sample efficiency then? One possibility is we can use approximate world models instead to make simulation more efficient. So for example, rather than simulating all the behaviors of all the agents around you and how they would react to your actions, maybe we'll just put the world on rails and make the simulation non-reactive to what we do, right? Another approach is we can actually improve sample efficiency by changing the model's action space instead. So while in typical RL models, you would output sort of control commands directly, this approach actually makes learning long horizon or long-term reasoning a little bit more difficult. So instead, we can learn models that reason and plan in, say, trajectory space instead, and this makes it easier to learn about long-term reasoning. The composition of scenarios that we train on is also extremely important for sample efficiency. So for example, by incorporating long target safety critical scenarios into training and scaling up the diversity of the behaviors that we observe in our scenarios during training, we can actually train motion planners that way more efficiently and to better performance than training on sort of nominal scenarios collected from the real world alone, right? And then finally, incorporating real data and combining imitation learning to RL is another promising way to address some of the shortcomings of reinforcement learning. So for example, we can directly use imitation learning pre-trained policy to initialize the RL agent. And this would hopefully make the initial exploration by the RL agent more efficient. Alternatively, we can also just use a sparse reward function in the RL part and combine that with a very, very dense imitation learning loss so that we can learn more realistic driving policies without the need to manually tune reward functions and manually shape them. Okay, and then finally, we've sort of seen how the composition of data plays a big role in learning these end-to-end motion planners. So another question to ask then is how can we sort of leverage internet scale data and foundation models for self-driving as well? And this has been the topic of several recent papers. For example, in Driver Agent on the left, on your left, Driver Agent combines LLMs with chain of thought prompting and tool use in order to predict a motion plan for the self-driving vehicle. So the LLM is instructed to sort of act as the brain for the self-driving vehicle. And then it's asked to use tools like perception or prediction in order to help it reason about the scene, and then ultimately generate a trajectory for the self-driving vehicle. Now, the LLM here doesn't actually have access to the raw sensor data. Instead, it relies on sort of textual descriptions of critical objects around the self-driving vehicle that it got by invoking these perception or prediction tools, right? So to address sort of the potential loss of information in this approach, we can also learn adapters that project visual tokens directly into the LLM's embedding space, enabling the LLM to sort of see the raw sensor data directly. And if we take this one step further, actually, we can just directly use a pre-trained VLM, right, to reason about or to see the raw sensor data directly, bypassing the need to learn such adapters, right? Now, obviously, we're still sort of in the early days for how to use these foundation models for motion planning, but this is definitely a very exciting line of research that could open up many possibilities for building more capable end-to-end self-driving systems, right? Okay, so that wraps up learning. And next, we'll talk a little bit about how we can design interpretability into an end-to-end motion planner. So in this section, we're going to go over a couple of papers in a little bit more details just to illustrate the different themes for incorporating interpretability into end-to-end motion planning. And we'll start with the neural motion planner. So the high-level idea behind the neural motion planner is we're going to predict this planning cost volume directly from raw sensor data. And then using this cost volume, we can then sample a bunch of trajectories, cost them, and use a minimum cost trajectory to execute, right? So here's how the model kind of looks like. We'll start with first taking raw LiDAR and HD maps in and extracting some features. Then using these features, we're going to predict three things. We're going to predict detections, predictions for how the agent, how each actor would move over time, and then also a planning cost volume. So as I mentioned earlier, each voxel in this cost volume represents the cost of the self-driving vehicle being in a particular location at a particular time, right? So given this cost volume, we can then sample a set of diverse, physically feasible trajectories from the current SDV's pose, right? Then we can cost each of these trajectories by indexing into the cost volume at each waypoint along the trajectory. And then finally, we just select the minimum cost trajectory to execute. So note that all of this can be done in parallel. So planning should only take a few milliseconds to complete, right? So here's a short video illustrating how NMP works. So we have LiDAR, HD maps, the model does perception and prediction, and then now we're visualizing the low-cost regions with different colors representing different time steps. And the planned trajectory here is shown in red. So from some of these qualitative examples, you can see the model has sort of captured following or lane following pretty well. In some cases, you will actually see the cost volume capturing multimodality as well. So for example, here we have intersection, and you can see that the cost volume assigns low-cost regions to both turning right and going straight, right? And we can also handle blockages with this approach. So the cost volume would sort of show a preference to lane change or to nudge around heavy traffic in order to avoid collision while still making progress. Cool. So there are still some shortcomings with this approach. First of all, planning is not explicitly conditioned on prediction, which might result in inconsistent and dangerous driving. And second of all, the model only predicts a single mode future, right? But the future we learned from the previous session is actually quite uncertain and quite multimodal. So in this follow-up work called DSDNet, we address this issue using a deep structured self-driving network that jointly reasons about perception, prediction, and planning. And now with this network, computation is then shared across modules. We explicitly model socially consistent multimodal futures into the uncertainties into the future. And then the planner can then leverage these predictions as well as any prior knowledge to plan a trajectory to avoid collision and drive safely, right? So here's how it works. As with NMP, DSDNet first extracts some features from LiDAR and HD maps and then produces these bounding box detections. Then in order to predict socially consistent multimodal trajectories for the other actors in the scene, we'll first sample a set of diverse physically feasible trajectories for each of the actors in the scene. Then we'll perform some message passing in between each of these actors in order to obtain socially consistent multimodal predictions. And then finally, to plan the SDV's trajectory, we do sort of the same procedure as in NMP. We sample a set of trajectories, cost them, and pick the minimum cost trajectory, right? Now, let's take a look at some qualitative results. So here we're visualizing the uncertainty of the actors' predictions over time, and different colors show different times. So here's 1 second, 2 seconds, and then at 3 seconds, you can see sort of like the multimodality of some of these predictions, right? Now, if we take a look at this demo, you'll see, again, the predictions of the model capturing multimodality very well, right? And in red here, we have the self-driving vehicle, and it's planning to avoid these, or planning to avoid collisions based on the predictions of these actors. Cool. Okay, so up to this point, the end-to-end motion planners that we've discussed first detect objects in the scenes, then predict their future trajectories, and then plans a safe trajectory to avoid collisions with them, right? Now, this pipeline works great, so as long as your detection module is working as expected, right? But what happens if, for example, the detection score flickers a little bit, and all of a sudden you don't see this like oncoming actor anymore, right? So in some cases, this could be catastrophic, right? You might just run into this actor because you don't see him anymore. So in this next work, P3, they propose an approach to address this issue. So rather than performing object detection and then predicting trajectories for each of these objects, this model instead directly generates semantic future occupancies, right? These occupancy forecasts are scene-based and instance-free, so we don't need to rely on things like thresholding a detection score to get rid of false positive detections or performing NMS post-processing in order to sort of reduce redundancies in the detections, right? So now, as a result, even if your detections, even if your model is a little bit uncertain about the detection, right? You don't run into the risk of misdetecting an object, but instead that uncertainty is directly baked into the occupancies themselves, right? Then the planner can then use these spatial temporal occupancy maps as well as other interpretable costs in order to plan a safe trajectory, to execute. And because the entire model is differentiable, you can actually train the model end to end. Cool. So let's take a deeper look into the semantic occupancy representation. So the model considers vehicles, pedestrians, and bikes as different classes. And within each of these classes, we actually further subdivide them semantically, right? So for example, for any pixel of interest, the model would predict how likely it is to be occupied by, say, a vehicle on a conflicting lane or a parked vehicle or maybe even a pedestrian, right? And this sort of like hierarchy allows the motion planner to then behave or learn to behave differently around different kinds of road users. For example, for VRUs or vulnerable road users like pedestrians and bicyclists, you would want to behave a little bit more cautiously around them, right? And then to predict these occupancies, the model first extracts some features from LiDAR and HD map input. Then it uses a recurrent occupancy update network to predict these occupancies into the future. Then given these predicted occupancies, the planner will then again sample a bunch of trajectories, cost each trajectory according to a set of interpretable cost functions, and then pick the minimum cost trajectory. So the cost functions that we can use here include cost functions for safety. So for example, to encourage the SDV to avoid the occupied regions that were predicted, cost functions to encourage comfort and following traffic rules, and cost functions to encourage route following, right? And importantly, the relative importance of all of these cost functions or subcosts can actually be jointly learned with the rest of the system. And then here is just some qualitative results seeing P3 in action. So the solid black box is the planned trajectory that of the SDV going into the future, right? And the different semantic layers are predicted by the model that are predicted by the model are shown in different colors here. Yeah. Cool. Moving on. So one of the disadvantages of P3 is that it predicts these explicit discrete occupancy grids, right? So this could incur discretization error, and it's also computationally expensive since we will need to predict large grids of occupancies over time at a sufficient enough resolution that you can actually see and avoid small objects. So however, at the same time, planning only really cares about occupancies around where the SDV might actually reach. So we don't really need much of the occupancy grids that we've predicted, right? Therefore, instead of predicting an occupancy grid, can we instead only predict occupancy at continuous space-time locations for the trajectories that we actually need to cost, right? Sergio talked a little bit about how we can actually do this in the previous session. So in this session, I just want to quickly cover a work that extends P3 by replacing the explicit occupancy grids with an implicit occupancy function instead, right? And now with this approach, you reduce the amount of redundant computation you need to do, and it makes the overall system much more efficient and practical to run. And then finally, we've seen a couple ways in which end-to-end motion planners can take advantage of sort of structured and interpretable costs for planning. And this allows us to encode prior knowledge about what constitutes good driving much more easily. And it also has really, really well-defined intermediate supervision, right? Making it easier to train. We've also talked a little bit about how we can use unstructured costs to capture implicitly many other aspects of driving that we might not have encoded through explicit structured costs, right? So the question is, can we combine these two different ways of costing? So we can then have structured costs in order to encode our prior knowledge, right? And unstructured costs to capture everything else that is either too difficult to express in the unstructured costs or that is left out, right? So there's been a couple of recent papers that do exactly this. For example, STP3 on the right there. And basically, it just learns to combine these learned costs with rules-based costs in order to learn more capable planners. Okay, now switching gears a little bit. Up to now, we've seen a couple methods, or all of the methods we've seen require HD maps as input. And as I've mentioned earlier, HD maps are actually a really, really great prior for planning. However, in order to use this map, we actually need to accurately localize the SDV onto the map. But what if localization fails? Or what if it makes like a small mistake, right? Or there's noise in it? Then in this case, you might actually run into some catastrophic consequences. For example, as illustrated here, the SDV might actually end up taking the wrong path and driving into opposing traffic instead, right? Besides this, HD maps are just more expensive to annotate and hard to scale, right? So on the other hand, if we were able to do mapless driving instead, then we impose much fewer requirements, right? And this approach is much more scalable because now we don't need to map everywhere we need to drive. So this next work, MB3, proposes a way in order to do mapless driving. So as MP3 receives LiDAR data as input and predicts occupancies over time. However, now MP3 doesn't have access to the HD map, so it will instead predict an online map to be used for planning. Then, given these intermediate representations, the planner will then predict a route given a high-level goal like turn right or lane follow. Then it will sample a bunch of trajectories, cost them using interpretable cost functions, and and then pick the minimum cost trajectory to execute. If we take a closer look at MP3's intermediate representations, you'll see that as a part of its online map, MP3 would predict the drivable region, intersections, and also the lanes that the SDV can legally reach. MP3 will also predict occupancies over time as well as their corresponding motion fields, right? And then given the predicted online map and a high-level command coming from sort of like any off-the-shelf navigation system, right? We can then predict the desired route as a dense spatial map using the sort of like switch of CNNs here. So for example, when the command is turn right in 50 meters, right? The output would be this green route shown in the image here. Right. Another challenge we have is how to actually generate trajectories for the SDV. So in traditional planners where you have access to the HD map, we can, for example, use lane relative samplers in order to generate trajectories that lane follow or lane change, right, with some variations. But in this mapless setting, all we're given is the current state of the SDV, and we don't know where we are in the map. So how can we actually generate these trajectories? So to work around this issue, MP3 will instead retrieve trajectories from a data set of expert trajectories and then use those as candidates instead, right? Now, of course, these trajectories need to be conditioned on the SDV's current state. So MP3 will sort of retrieve different sets of trajectories based on the SDV's initial state as shown here. Finally, as MP3 will cost each trajectory and pick the minimum cost trajectory for execution. And in MP3, the cost is composed of a set of interpretable subcosts, including subcosts to encourage safety with respect to the predicted occupancy, another subcost to predict safety with or having a safe headway with respect to your lead actor, right? And then some subcosts to just encourage that you stay within the drivable region on the reachable lanes and that you're staying on route. And yeah. And then again, as MP3, the relative importance of these subcosts can then be learned end-to-end with the overall system. So here is a visualization of MP3 in action. So these are actually closed loop simulations. So you can see like what the planner actually executing what it plans to do, right? So in blue, what we have here is like the actual plan of the SDV and what it's doing. And in black, we have the expert human driver from the log. Yeah, so as you can see, like if the command is turn left, you can see this really interpretable like green route, which basically encourages the SDV to take a left turn instead. And then in this particular example, I think we'll see like a pedestrian that's heavily occluded, but MP3 will still predict occupancies for that trajectory or for that pedestrian. And the SDV will then plan a maneuver to act a little bit more cautiously around them. Cool. All right. Finally, let's cover a little bit about reactivity. So since the SDV is a participant in traffic, its actions sort of affect how other actors behave in the future, right? And in turn, how other actors behave in the future will then affect how the SDV will want to plan its decisions or plan its maneuvers, right? So this creates a really, really complicated reasoning chain. And to see why it's really complicated to handle, right? Let's take a look at this T intersection here as an example. So if we were to just consider the marginal distribution over futures for the two actors in the scene, right? That it's really hard to predict or plan a good trajectory because this will basically mix over the possible different futures. Now, on one end of the spectrum, right, if you were to decompose this, you can see, for example, maybe in this first future, the right vehicle or rightmost vehicle will yield to the SDV and then make its left turn after the SDV passes, right? So in this case, the vehicle reacted to the SDV's intended plan, and thus the SDV was able to pass the intersection without hesitation. But so this brings us to the first challenge, right? actors' behaviors can actually vary a lot based on what the SDB plans to do, right? And then on the other end of the spectrum, there could be some cases where the rightmost car actually ignores the SDB and just proceeds with a left turn irrespective of what the SDB does, right? These situations are less likely to occur, but they're not impossible. And so we want to be able to ensure that we can plan safely in these low probability events as well. So let's take a look at different ways to address each of these challenges one by one. First of all, to consider the reactiveness of each actor, a naive solution is to just sample a bunch of SDB trajectories and then conditionally predict what other actors would do based on each of these trajectories. This is a really straightforward solution, but it's really computationally expensive, right? So how can we make this more efficient? One approach is to implicitly model the interaction between the SDB and other actors using tensor fusion. Or we can actually use more explicit approaches. For example, on the right, using a deep structured model where the pairwise interactions between the actors and the SDB can be modeled with pairwise energies. Yeah. Okay, moving on to the next challenge. The other challenge is how to deal with very unlikely events, right? So previous planners have tried to find a single trajectory that performs well across all possible futures. But since the future is dominated by very high probability events, the planner might be encouraged, for example, to just plan a trajectory that continues straight through the T intersection here. However, this could be unsafe if unlikely events happen, like what we talked about on the right-hand side here, right? On the other hand, if the planner can also be very conservative, so it can take a braking maneuver instead. And while this could be very, very safe with respect to both futures, it's actually overly conservative and might actually result in some uncomfortable or socially confusing driving for other actors in the scene. Yeah, so one paper called Lookout proposes the following approach to solve this issue. So it leverages the idea that we can replan every time we see that there is new information available, right? So instead of committing to a single trajectory now, we'll first choose a single immediate action that we want to execute right now. And then we'll postpone committing to a single long-term action to the future later. So instead, we'll consider a set of long-term actions to react to all possible futures instead. So to achieve this, we'll first sample a bunch of short-term trajectories or short-term actions. And then for each of these actions, we can then sample possible long-term future trajectories that correspond to various behaviors. Yeah. And then to select the best trajectory, we will then cost the sample trajectories based on the following intuition. The immediate action that we want to take should be safe with respect to the worst case prediction, right? And then the long-term action that we take, the cost to go, should not be overly conservative. So as long as we can safely react to every possible future out there. So to illustrate how this looks like, let's see an example. So here we can see an example where it's the same T intersection. And if the SDB continues with its current speed, right, we can successfully pass this intersection in the future. However, now if we consider the other future in red, we'll actually need to perform a hard brake to avoid this low probability event should it happen. So overall, this approach to planning is very unsafe, right? So this short-term action is not what we want. Now, instead, if we slow down a little bit as our short-term immediate action, we can still cross the intersection safely and comfortably in the first future. But at the same time, should the second unlikely future occur, we can still comfortably brake in order to avoid collision as well. So then using the intuition for costing that we discussed earlier, this second action would be the preferred action that we take, right? So here is just, here is just a quick video showing how this sort of lookout planner works in closed loop simulation. And in green, you have the SDB, right? And other vehicles are in blue, pedestrians are in pink. Yeah, so that wraps up the motion planning section. And then finally, we're just going to really quickly discuss some of the main approaches to controls. So what is controls? The job of the control module is to track the motion planner's trajectory by issuing commands to steering, throttle, and braking, or to those actuators. One way to do this is using optimal control. So for example, in model predictive control, we're going to try to find a sequence of actuation commands that optimizes a cost function based on things like tracking error and ride comfort, right? And we also need to add constraints to this optimization problem in order to account for actuator or system limits. Now, the strength of this approach is that the commands that we issue account for actuator and system limits, thus ensuring that we can track the trajectory well. And we can also ensure ride smoothness and comfort by adding constraints on jerk and steering rates here. The downside of this approach is that it's often slower than other methods, right? It can be hard to tune the objective function that we optimize. And it can be hard to debug at times as well because we're leveraging a black box optimizer here. And then finally, of course, we need to have a very good vehicle model in order to get good results from this approach. So another option is feed forward, feedback control. So here the feed forward section part sort of generates a sequence of controls that tracks the reference trajectory, assuming our vehicle dynamics model is perfect, right? And then the feedback part then uses observed tracking errors that are caused by any potential discrepancies between our model and the real system, and uses that to adjust the controls so that we're tracking the trajectory better, right? Now, strength of this approach is it's simple to create, debug, and maintain. All right, it's fast to run and has deterministic computation speed because we no longer need this optimization in the loop. Tuning is also really intuitive if we make use of something like a PID controller, for example, in the feedback part, right? And then finally, this method has been proven to work across like many practical applications already, right? Some downsides of this approach is that feedback only works well in linear regions. It doesn't account for system or actuator limits, and there's no look ahead when we're planning the controls. Cool. And then finally, last topic I want to touch on is actuators. So the controller so far would only output steering and acceleration commands, but we still need a way to translate these into actuator commands. For example, like how much pressure you want to exert on the brake, right? And these actuators need to be characterized in order to have more accurate tracking and in order to understand what is actually achievable by the controller. And some of those important limits that we need to characterize is, for example, for each speed of the SDV, what's the maximum acceleration it can actually do, right? What's the maximum deceleration of the self-driving vehicle, or what's its maximum steering rate, etc. Yeah, so I think that's it for this session of motion planning and controls. We've covered a lot of ground on how to actually learn an interpretable end-to-end trainable motion planner, and we've covered some of the basics of controls as well. Yeah, that's it.
We have time now for a few questions. We will come back at 1:20. So we'll have a little bit of an extra 10 minutes compared to what was in the original schedule, just to make sure people have enough time to grab lunch and everything. So we'll continue back at 1:20 to look at intelligent data mining, data engine, stuff like this. And then we'll talk about vehicle-to-vehicle communication and then all the simulation stuff. Yeah, so there was a question?
So in your matrix thing, right, you have a goal. So you said go left to right, you take to accordingly. But what happens if the intersection is complicated. There are multiple levels, multiple layers.
Hmm.
How does it decipher where to go?
Yeah, I think that would require like extending the model. Right now, the routing module only considers like some 3 commands, right? Go left, go straight, turn right. I think you can definitely extend the routing module to something a little bit more complicated in order to handle that kind of topology. But that's just not something considered in that paper at the moment. Yeah. Oh, sorry.
So, it's regarding the safety. Now, when we for the architecture itself, understanding the planner itself, it's depending on the previous the prediction and the feedback, the output from it. So, what happens if they have a problem?
Yeah, no, I think that's a really great point, right? Like if in those modular systems, if perception fails or prediction fails, right, the errors can sort of cascade down the pipeline and compound over time, and it could have very catastrophic failures, right? I think in some of the more recent works I presented here, for the idea is that we can still sort of maintain this sort of modular system, but now we can significantly broaden the interfaces between the systems so that the uncertainty of those systems can be propagated through the system down into like motion planning or controls, for example, right? So for example, if you were uncertain about like some actor because it was occluded, so your detection scores are really low there. In a previous pipeline, you might actually just drop those detections and consider them as false positive detections, which could be very unsafe, right? Now, if you were to instead use something like an occupancy-based representation, right, you can then, instead of saying there's no prediction there, you can express things like, I believe there's a 3% chance or a 30% chance that there is an actor there, and there's some probability that it's going to cut into our driving path in the future, right? And by having this sort of like uncertainty propagate down into motion planning can then safely plan to handle that situation. Does that answer your question? Kind of.
Because my point is that someone.
So I think now that like you said, there's not a clear-cut boundary between like perception, prediction and planning, right?
Mhm.
It's they're all neural nets, but at the end of the day, neural nets connected with neural nets, right? I mean, how do you really go about training the weights? Because earlier you had like one goal, right? For perception, you had like one loss function you were trying to tune for that loss function, right? For prediction, we're trying to tune for that loss function. But now the real loss is on the planning side, basically, right? How do you like train all these units that are like intertwined and connected with each other based on that very loss at the very end, basically?
Yeah, I think in some of the approaches I presented today, what they found was that you actually can't just train only on the end task if you want these interpretable representations, right? It's actually really helpful and really important to also supervise the intermediate tasks as well. So in a lot of these papers that I presented, they would either sort of add these auxiliary tasks or add intermediate supervision in addition to the end task supervision as well. And then for actually propagating the planning loss down through the rest of the modules, right? But because the entire system is differentiable, you can actually just compute gradients of that loss with respect to the entire system and optimize it in that way. Yeah.
Just a quick question. So in a lot of the neural motion planners, the prediction is quite good in at least the simulation. Is there a specific model that you chose to use or the prediction of other objects?
Oh, in the neural motion planner?
Yeah, sure.
Yeah. So I want to clarify that it's not my work. This is work I'm presenting, but yeah, I believe they use a sort of just a custom CNN based architecture with like I believe it's like a almost single shot detection kind of a training objective at the very end in order to train the detections. Yeah.
So back to the architectural decision. I remember your slide at the very first beginning. There is one, basically, we have multiple stage, the multiple components in the object design. And about the beginning of slide, you have say end-to-end, which one component, end-to-end. So I'm thinking just could be a research, just saying, let's train at end-to-end. Because we have only one loss function could be, and that can handle this case itself. In the middle, we'll say these two like a simple model. And with this one to end-to-end training, and does it consistent with multiple components?
I see.
Division. And if they are disagreed with a certain high risk, then there may be something like a problem there.
I see. Yeah, that makes a lot of sense. Yeah. And I think that's consistent with like what some of these papers have found too, right? You need that intermediate supervision, whether it's like with a direct supervision, or if I'm understanding you correctly, like trying to use like the discrepancy between how you imagine those intermediate representations to interact with the final plan, and use that as a training objective as well. Yeah.
I was thinking just architecturally, because I see the earlier, you basically very if my understanding your slide thinking is that kind of end-to-end training is very hard to integrate or to understand what is happening. But that give us, I think that benefit itself is really could be one consolidated object function to optimize.
Yeah.
And that well maybe will be solving the risk or mitigate the risk if we optimize an individual component. End of day, this optimization strategy maybe it's not run together. End of day, we could have some risk because individual components will be shared. If we have this end-to-end training as a symbol or as another way to viewing the timing, then they could be mitigating some of the risk.
Yeah, I definitely agree with you. Yeah. Yeah.
Interesting research.
Sorry. Did you have? Okay, sure. Thanks.
Were there any questions on Zoom?
I don't. Oh, I didn't see.
No, it's okay. Sounds.
All these slides will be available when
Andre?
I cannot say for sure about the slides, but the recordings so it's being the sessions are all being recorded. You will probably be able to access the recording on your my CVPR platform probably even next week already, depending on how quickly it gets processed. And then we will also upload like nicely edited per session videos to YouTube, maybe later, because at least last year there was a restriction. They didn't want people to immediately upload all of their sessions the week after CVPR, because people paid to come to CVPR, I guess. Yeah.
Oh, yeah. So my understanding, I think Sergio would be a better person to chat with later about this, but my understanding is you can actually just use any on-the-shelf like navigation system. So for example, maybe Google Maps, right? And Google Maps would in 100 meters. But you still require like map, right? But you don't need high definition map. You get really like course. Maybe you can deliver that. Yeah, you still require some basic maps so that you can actually know where you are and how you're probably also it's not the online get a knowledge of yeah, so the online mapping is necessary so that you actually know this is the drivable region around me, right? These are the lanes. Drive precisely. Yes. And then, but on top of that, you still need like maybe static definition after something that can actually route your self-driving vehicle to where you want it to go, right? Yeah, I see.
So in your opinion, using to like the plan, if we know that to do multiple planning, we need the rest of different plans, and that comes on the global level. But I'm not sure if we can do, if we can get a global round dollar map. Yeah, I think, yeah, so, yeah, so maybe we don't prefer like high definition maps, right? Those are really expensive to collect and create. But we can still rely on these like off-the-shelf navigation systems like Google Maps. And the next one is about the negotiation. We mentioned message passing. I'm just wondering, do you have like a region of interest where you identify these are the agents that need to like negotiate? Because when we have very dense traffic, do you negotiate with every agent?
Yeah, that's definitely really interesting, right? How do you sparsify that graph so that you don't need to, or your computation is more efficient, right? So I didn't actually run these experiments myself, but my understanding from the author is that actually like a lot of the pairwise interactions between a lot of actors, or the actors only really interact with a few actors around it, and like actors are very far away, don't actually influence what you're going to do, right? So in fact, like running this message passing algorithm is actually pretty fast because it doesn't take a lot of iterations. But yeah, a lot of the actors far away,
Like most of the cases, won't need.
yeah.
Okay, great. We can get started in a few moments. Those of you who are coming back, welcome back. Those who just joined us, thank you for your interest. We're going to be talking about the intelligent data mining and data engine side of things first. Then we're going to be doing vehicle-to-vehicle perception and prediction and planning for autonomy purposes afterwards. And later after that, we will have a couple of detailed sessions on simulation. So with that out of the way, my name is Andre. I've already presented hardware in the morning. To recap, I work on sensor simulation as well as some state estimation at Waabi. And in this session, we're going to be talking a bit about how we gather data, what the techniques are for curating interesting and useful data sets, and how to actually label them into useful artifacts that you can then use for supervised learning. So let's get started. So as you all probably know, datasets have, been a crucial part of the recent advances in all tasks of machine learning. And this ranges from things like low-level vision for things like stereo estimation and optical flow, all the way to more advanced tasks like object detection and motion forecasting. And it's worth pointing out that when I talk about datasets, this means both labeled as well as unlabeled datasets. And of course, since there's been growing interest in autonomous driving, so too has there been a significant increase in autonomous driving related data sets. And starting with one of the very first ones, definitely the most popular data set, Kitty, in 2012, we have seen data sets for tasks like perception, motion forecasting, actor behavior, and motion planning constantly being released ever since over the last decade, constantly improving in terms of their scale and diversity. Okay, so before we get started into how we actually curate and label data sets, it's important to kind of think about the data sets that we plan to use and the kinds of features that we would like them to have. Like, what do we actually want from a data set? There's no one-size-fits-all solution. So depending on the tasks you're trying to solve in robotics, the data set choice might be different. So there's a few properties that we can consider when looking at different data sets. So first, there's the sensors that we use to collect the data set, which can vary significantly, and they have a large impact on the kinds of models you might want to use and the difficulty of the task. So for example, in autonomous driving, there might be data sets that emphasize radar perception more. There might be data sets that focus on motion forecasting or long-range perception and so on. Second, the presence or absence of high-definition maps is another factor. Maps can potentially provide useful supervision or priors for many tasks. And some data sets contain no maps, while other data sets might contain very detailed high-definition maps with a lot of annotations for crosswalks, lanes, as well as more abstract information like, I don't know, traffic light information and construction elements and so on. And third, of course, supervised machine learning models are as good as the labels that they are fed. So the type of annotations, their quality, their quantity, their granularity is the final factor that you need to consider when deciding on what data set to explore for a specific task. And finally, as we will discuss later, dataset curation techniques can be applied to one or more datasets in order to ensure that the examples in this dataset are more interesting and more representative for your task at hand, while also covering kind of real world scenarios. And the coverage is crucial because you want your dataset to cover the distribution of real world data correctly in order to generalize to the real world. Okay. So we've already talked a little bit about sensors in the hardware section, and then later on we'll talk about more details of mapping. And for now, we will focus more on the curation and the labeling slides. Okay, so what are the actual stages that encompass this sort of a traditional dataset building process? Well, you have to begin by collecting some sort of raw data. Then you curate it in order to extract interesting parts of this dataset. And then you typically feed this data to some sort of labeling system, traditionally relying on human annotators. And then the resulting data set is finalized, and we more or less keep it fixed for a time for comparison purposes. We use it to train models, and then we use held out labeled data to evaluate. However, there are some remaining challenges with this kind of framework. Namely, even a handful of autonomous vehicles can collect thousands of hours of data over a relatively short time span. And you need to select the best data to train on and to potentially label. And this is not an easy task because it involves balancing basically many metrics. And of course, while effective, human labeling is pretty expensive, which means that it is very difficult and expensive to scale to very large data sets. So we need to come up with ways which can leverage human annotations only when truly needed. So the focus of this talk is on these two stages, namely data curation and labeling. And we will begin first with curation, namely answering the question, okay, given a huge pool of raw data, how do we actually curate an interesting, useful, and representative data set? Before diving into specific curation techniques, as before, we need to start with the desired properties that we might want to optimize as part of our curation process. First, we would like a data set to be interesting and to contain challenging scenarios that are useful for training our models. Of course, this definition of what is interesting can depend a lot on the task, and we will see some specific examples in a bit. Optimizing for coverage, on the other hand, ensures that the selected data set that we picked is representative of the real world, such that we can generalize to real world scenarios. And last but not least, given a particular model that we're interested in, we can also consider optimizing the data set itself in order to further improve this model's specific performance on the task. So let's now start first with approaches which seek to curate an interesting data set. Rules-based tagging lets programmers write custom tagging logic, which decides kind of algorithmically what is interesting. So typical inputs to this rules system can be things like perception outputs, the pose of the ego vehicle, and maybe even an HD map. Now, the perception outputs could be the ones that you already recorded while you were recording this data and your autonomy system was running, or you can compute it after the fact. It doesn't really matter. And the idea being that you have this set of data, you process it and run these kinds of custom scripts. And whenever one of these scripts finds a match, you flag this with a particular tag. And then you can query for tags when you're building the data set. And of course, there's a long list of attributes that you might want to consider when you're building these kinds of taggers, and which could be used to define the interestingness of a scene. So you can have tags that are related to a map, to the actors within the map, or to your own behavior. So things like, for example, the map complexity, specific kinds of interesting intersections. Actor complexity might be the number of actors and their overall aggregate behavior. And then ego complexity, you can look for things like harsh braking, excessive speed, or any other interesting, unusual occurrences. Now, this rules-based system can be very powerful, but it does require significant engineering to actually write this kind of tagging logic. And the tagging logic itself, at the end of the day, is kind of handcrafted. So in many cases, it could be brittle to things like noisy perception outputs or some changes in your models. So one other approach is instead to directly learn to tag by essentially training a network which, given some sort of raw data, maybe even the raw sensor data, it directly outputs tags of interest in a scene. For example, is there heavy traffic here? Has a cut-in occurred through this sequence, etc. And this approach can be more flexible and robust than the previous one. But of course, the disadvantage is that if you cast this, for example, as a supervised learning task, then you will need a training set for each of, you will need the supervision labels for any possible tag you're interested in, which is also not the most scalable thing. One other thing to highlight is that the approaches that we're talking so far kind of have been making this assumption of a fixed set of tags for any self-driving scene. Like, is there a cut-in or not? Is the vehicle braking, etc.? Is there heavy traffic? But in the real world, there's also an extremely long tail of scenarios that we might be interested in that would fail to be captured by this kind of fixed set of tags. And basically, this motivates the use of an open set tagging system. And fortunately for us, recent advances in vision language models are a very promising direction for helping us capture this long tail. The idea being that you can then learn to leverage shared embedding space for your sensor observations and some sort of text, something you can think of as a clip-like application, and then leverage this for zero-shot classification of novel occurrences. Now, later works have extended these kinds of basic ideas to more elaborate use cases. For example, doing things like open set object detection and open set segmentation. So, instead of segmenting all the cats in an image, you might have a prompt that says, I don't know, like segment only dogs that are riding a skateboard or something. And then this would try to kind of figure this out, but produce actual structured outputs. The idea behind these methods is essentially that you use some sort of pre-trained clip-like embeddings, and then you fine-tune additional heads for perception and segmentation and so on. And then you have, of course, interactive question answering, which basically takes this one step further, and it allows for more complex text prompts beyond, perception labels, and lets you do more complex reasoning. And recent works do this by, for example, leveraging recent advances in vision language models, like, for example, GPT-4, and then they potentially even collect additional data sets for fine-tuning these models for self-driving applications. And in many cases, it's been shown that these models are actually powerful enough to aid with the driving task itself, so to be used for autonomy, like natural language kind of guidance for both interpretability as well as autonomy, which highlights that these systems are powerful enough for a wide range of tasks, including things like data curation. Okay, so we've seen that the idea of optimizing for interestingness can lead to significant improvements over a bunch of different models as well as tasks. But given a particular model in which we're interested, it's now also natural to ask whether we can specifically select examples to label for this model such that we optimize the performance of this model. This can speed up training. It can also ensure that you're using your labeling budget very, very intelligently. Of course, what I just described is a well-known machine learning problem called active learning. And the idea behind active learning is that you iteratively leverage the current trade model to decide which examples to label next based on those believed basically most likely to improve the model performance. Now, directly optimizing the expected improvement of a model in the real world is, of course, a very challenging task. So in practice, this is often approximated with a related objective. Like, for example, you might select samples which have high model uncertainty, or they might induce a high information gain. You can use output entropy as well as the notion of a margin for classification in order to select what to label next. And this can basically do quite well in practice, but you're still limited by the fact that these kinds of approaches struggle when something is completely off distribution, because in general, it's challenging for a model to learn well-calibrated confidences on unlabeled examples. And within the self-driving industry, multiple companies have mentioned the use of some version of active learning as a core component of their development approach. And these approaches are basically more engineered, productionized versions of the uncertainty or entropy-based criteria that we saw previously. So one example is for Tesla's Autonomy Day, they spoke about automatic triggers, which can identify examples to be sent to labeling automatically in order to improve the system. And another example is some blog posts from Cruise that also talk about how they leverage the consistency of trajectory projections over time in order to mine for hard examples. The idea being that, if you're doing your motion forecast for some particular object at time t, you have your data already recorded, so you can look at where that object actually is in the future. And if the object ends up at a completely different location than when you predicted it, you can flag this snippet for labeling and then add it to your data set as a challenging example. Now, a lot of these systems do require a fair bit of human in the loop. And recent work has actually studied ways of bypassing this altogether. So a CVPR 2024 paper called AID actually builds on this idea, and they propose building a framework for automating this kind of data engine that you see in the industry using large language vision models. The idea being that this paper leverages an image captioning model to find issues with the detection model. And it automatically queries for additional examples of this kind of issue from a large database of raw data using another VLM. And then it uses a zero-shot detector to generate 3D labels to continually train the model. And then there's also this verification module that lets you kind of have a measure of confidence such that you don't ask for human corrections for every single correction of these, which means that you are actually maximizing the efficiency of your training and having the model kind of improve itself over time. So let's now turn to the final curation objective, which is diversity and coverage for the data. Now, selecting only interesting or uncertain examples is very good in theory, but it can also lead to a biased data set, which actually ignores common, less interesting scenarios. For example, as highlighted in this picture, you might miss the area on the bottom left completely. And for machine learning systems to generalize, it is also critical that the curated data set is representative of everything in the real world, right? Not just the challenging cases. So selecting a representative subset of the total samples, which covers the true distribution, can be formulated as a set selection problem. So you can specifically formulate this as a core set selection task. And here the goal of core set selection is essentially to find a subset of samples such that when you train a model on this subset, its performance is still very good on the remaining samples that we did not select. And in general, finding the solution to this kind of problem, the case center problem, is NP hard. But in practice, greedy algorithms have been shown to be very promising. So specifically, you can do some sort of iterative selection where at every time step, you just select a point that has the greatest distance to any of the previously selected points, or you could just pick something that has the greatest median distance to the selected points, and you do this iteratively, and you keep selecting interesting samples such that you have good coverage, but you only need to label a fraction of your raw data. Now, a question arises because we're now talking about a lot of distances and median distances and maximum distances. So the question now is, what space should we do this selection in for coverage or diversity-based sampling? One common approach in active learning is to actually use a learned space. So for example, the second last layer of some neural network you're training, or you can use a completely separate model that is pre-trained in a completely unsupervised way. And you use that as a feature learner, and then you use these learned features to embed examples into a feature space. And then in autonomous driving, what you can actually do is you can leverage a more handcrafted approach for these selection processes, where you might include attributes that you know you'd like to capture regardless of everything else, like even coverage of the geolocation or even coverage of lighting conditions or whatever, potentially in addition to whatever features another model is learning. So to summarize, we've reviewed essentially these three categories to curate self-driving datasets. And of course, there's no one-size-fits-all approach. And typically, you might want to do a combination of these approaches to ensure that the dataset covers the long tail of examples well, while also having even coverage for any potential real-world example in order to train robust machine learning models. Okay, so now that we wrapped up curation, let's look at ways for scaling up labeling. Now, the most common way to do any sort of labeling is to employ humans. And this can usually do really, really well and produce the highest quality annotations possible, but it also requires manual effort, so it's therefore pretty expensive. Now, for tasks like motion forecasting, as we hinted at in that example from Cruise, you can actually use the output of an onboard perception system itself for the annotations, because you no longer are restricted to a limited view of the time dimension, so you can compute very, very accurate trajectories offline and use these to supervise prediction. Now, these results are still kind of noisy, so while they can be useful for training motion forecasting, you cannot directly use them to improve the detector itself. So this motivates the growing interest in automatic labeling or offline labeling models, which can leverage future information as well as more computational resources in order to obtain high quality data labels, while also being able to run at really large scales on compute clusters without the need for human intervention. So here we'll provide a quick overview of the most common sort of paradigm for this kind of automatic labeling pipelines. And in this case, we will be focusing on a LiDAR-based approach, but a lot of these concepts also apply if you're only dealing with camera data, for example, or radar. And there's a lot of methods that have appeared in the last few years in this area, but a lot of them follow a similar framework, even though they differ in more subtle ways. So in the first stage, you begin by running a traditional object detector on your raw data, and that will give you some initial detections that you can then process with an offline tracker to obtain tracks over time. And then you can use this as a coarse initialization to a second stage refinement model, which is trained to refine each of these trajectories independently. And then once you have these refined trajectories, you can then leverage them as labels to train your regular old perception model. Now, one limitation of this approach is that, well, you still need human labels to supervise the automatic labeling system itself, particularly the refinement engine. And then a separate line of work seeks to bootstrap perception systems without relying on any labels at all. So these approaches often leverage the fact that self-driving vehicles might be visiting a specific area of the world multiple times, and use the fact that this will give you a sense of what parts of the environment are static versus dynamic. So what this can do is that it can help us essentially bootstrap a perception model from heuristic labels that we figure out based on this kind of differences over time. And then use those labels, those very, very coarse labels, to train a model, and then use this model to relabel our data, then prune the outputs with some sort of heuristics, and then continue this loop of self-training, which, as it turns out, doesn't plateau as early as you might think, and can actually lead to pretty decent results. Recent papers have even started using applications of RLHF, reinforcement learning from human feedback, a very powerful technique that has seen a lot of has shown a lot of benefits for training large language models, and they've been using this to improve the process for the self-training instead. But here, of course, they would be potentially replacing the human feedback with, for example, human handcrafted heuristics instead, like some sort of shape or alignment priors on the kind of labels you're expected to see. So the nice thing here is that you can kind of have a human engineer a few of these heuristics, and then they kind of get reused over and over by the model during this self-training loop. And then you end up with a pretty good detector, even though you didn't have any human labels to begin with. So to recap, in this talk, we focused on intelligent data mining for building self-driving datasets. Namely, we began by talking about data curation strategies, for example, using handcrafted rules to tag interesting parts of the data versus vision language models to do the same thing. Then we talked a little bit about how to ensure nice coverage of the data to make sure we're not too biased over safety critical scenarios and forget about the boring ones. And then finally, we talked about how to actually label the data set that we've now curated and how we can actually improve the label efficiency by using offline perception methods or even some sort of bootstrapping process that requires no human labels to begin with. So with that, we've reached the end of the intelligent data mining session. We'll have time for a couple of questions, and then Siva will talk about extending perception to multiple vehicle settings, and then we have the simulation settings, the simulation sessions. Thank you very much. Awesome. This question?
So, that, so how do you tackle the increasing amount of data throughput? So basically, if you want to scale up your systems, you probably will increase amount of flux, and through time the bit amount will also increase. So probably like it's not economic to train your model every time you collect new data, especially in the paradigm of pre-training and fine-tuning. Probably for fine-tuning, you can like train your model each time you collect new data, but for pre-training, it's extremely expensive. So how do you tackle this kind of increasing amount of data issues? Do you apply some kind of continual learning algorithms in your system?
Yeah, so the question was, given that it's not the easiest thing to keep retraining a model over and over, how do you deal in practice with the fact that you constantly have new data arriving that it is getting added to your data set? So I think, so I haven't worked directly on this kind of stuff like continual learning, but I would imagine that it is possible to keep fine-tuning a model without retraining it from scratch every time as new data arrives. I'm not saying, I don't think it makes sense to retrain it every day or anything like this, but I think it's worth experimenting to pick a good trade-off between, not having gaps that are too long between model retrains, but also not spending too much money, and then having the model kind of automatically get trained for like maybe an epoch on the latest, greatest data, while also making sure to have a very robust and well-designed validation set for all of this.
Wabi, like, are you like training your model from scratch, training your model from scratch every time you iterate, or you kind of still utilizing some previous technique?
I can't give any like super specific details about the perception setup, but in general, yeah, like I mentioned, it's not really economically feasible to retrain too often, especially if your model is very large. So that's why it's typically you have some sort of cadence that you need to decide on by experimenting in your particular use case, and then using this to decide, okay, I'm gonna do incremental retraining every, I don't know, again, these are just examples. I actually don't know. Like you can have like an incremental retraining like every week, and then I don't know, every month you do like a from scratch run or something like that. And of course, using a lot of validation data for this. Yeah. Yes, question.
For the retraining.
Mhm.
Talk about data getting the system, so how you select of the data into the labeling, but you might have to ingest everything, so thinking about data that you want.
So is the question specific to curation, or is the question specific to how do we actually go even before curation? How do we actually ingest?
You have to ingest everything, so like the label curation process and how you.
Yeah, I can answer. Yeah, so the question was, okay, how do you actually deal when you have to ingest like petabytes and petabytes of data? So yeah, I can, of course, as before, I'm gonna answer this academically. I can't give like specifics, but generally speaking, in my experience, it is important to have an efficient system for ingesting data, even if there's like a lot of data coming in. Now, about storing data long term, you can leverage some coarse tagging to, for example, decide what is definitely not interesting and what you can get rid of versus stuff that might require further inspection. And you can combine that, for example, with things like lossy compression to improve efficiency and keep your cloud costs down, even when you have a really large number of data streams coming in. Sorry, yeah, it's the one in the back, and then you, yes, and then we can move on to the next session.
How to accommodate synthetic data into real data in your pipeline? You haven't talked about synthetic data, so it's all about real data. But we know that there are conditions that we need synthetic data for performance. How you mix it with real data in your pipeline?
Yes, that's a good question. So we will see more details in the coming sessions. The session, not this one, but the one after, will talk extensively about simulation, and it will also include how to use simulated data to improve perception systems. But yeah, I agree. Generally speaking, you have similar issues with simulation when it comes to, you still have to store the simulated data and tag it and so on, but you can reuse some of the tagging ideas to find interesting things that happen in simulation when you're running simulation at scale. And then in terms of actually mixing the data when you're training a model on both simulated and real data, there's like a lot of literature on domain adaptation and multi-domain training that can be applied to make sure that the model doesn't cheat too much when it comes to mixing the two domains, and that the gains you get from adding simulated data actually materialize in real data. Okay, one more question.
I have a question regarding the data curation. If my understanding right, you mentioned the data curation is one of the way to selecting this data itself. You use the very last second layer of the model, which really is to identify the distribution of the labels. Can you add a bit more?
Yeah. So this was, for example, you can consider things like a perception model that is pre-trained, and then you might run the perception model on these data samples, and then the final activation feature map, maybe before your detection decoder or something like this. This can be turned, maybe using PCA to reduce the dimensionality, into a feature vector that you then use for various distance calculations and diversity metrics. And if you don't have this model to begin with, you can also use some sort of pre-trained self-supervised model that is trained using some sort of, I don't know, like masked autoencoder or some unsupervised learning technique like that.
Well, that selection logic itself binds to the model we choose.
Yes, so that's a good question. So that's when you go to that point, you will have some sort of bias towards the specific model or maybe even the architecture you're doing. So that's why these hybrid approaches are useful, where you're kind of using some models features in conjunction with some other rules, like for example, geographic coverage or something like that. So usually having a hybrid approach can help mitigate some of the model specific bias. Yeah, you're welcome. Should we get started with the next session? Okay. Yeah, for sure. You can do whatever you want with the present your notes.
Great.
All right. Hi, everyone. Good afternoon. Hope everyone had a good lunch session. Today I'll be talking about vehicle-to-vehicle communication and vehicle-to-X or vehicle-to-infrastructure. The topic of this tutorial is actually quite similar to the session we did last year at CVPR. The main changes for this year's tutorial is we'll have a couple new papers on ways that people in the last year have been doing like fusion of the different messages between different vehicles and infrastructure. But a lot of it is a recap from last time, but I will try to go through it. And this year is also a bit condensed, around 15 minutes. So I might go a little bit more quickly, but feel free to ask if you have any questions about it. So yeah, the title's a bit outdated because it's vehicle-to-vehicle communication, but a lot of the topics that we talk about in this session are very relevant to vehicle-to-infrastructure, which is also another very exciting area of work. And if you have like significant resources, you can have infrastructure available to also do vehicle communication. So in the previous sessions of this tutorial, we talked about all the different components to an autonomy system. And in particular, we talked about perception. So once again, we have here ego vehicle or self-driving vehicle equipped with a set of sensors. And given that sensor data, you try to detect all the agents in the scene and where they're going to go into the future. But the challenge with this type of setup, of course, this is already the main task of self-driving, is that we can actually try to be a bit safer and be more effective in our communication by actually having other self-driving vehicles in the scene. So one way you can be even more robust, see even further, is to have vehicle-to-vehicle communication or vehicle-to-infrastructure set up. So in the past, before like the big boom of vehicle-to-vehicle communication in computer vision, there was vehicle-to-vehicle communication for just routing and for also traffic flow and management. But now there's a idea of being able to communicate sensor data between the different components of the different vehicles. So for example, far away objects that we might have very few observations for, if there's another self-driving vehicle there, or there's infrastructure that has camera or LiDAR sensors in that area, you can get more observations about the scene. You can run some processing on this and then send that sensor data or autonomy outputs to the main vehicle of interest. And then the self-driving vehicle can then use that additional information to plan a bit safer or to plan a bit further ahead. So it's going to be a more comfortable drive. So there are several advantages to vehicle-to-vehicle communication and vehicle-to-infrastructure communication. So one is you can see more locations than you would otherwise. You can see through occlusions, because if you're only capturing your sensor data from a single viewpoint, you might have some visibility artifacts in terms of the LiDAR sensor, for example, or a camera when there are different objects overlapping with each other. And you can also see better because you have more dense observations about the scene. And then the one other thing to know is that if you have vehicle to infrastructure or other vehicles, they are all also having additional compute available that can process that sensor data before sending it to the main vehicle that's driving. Cool. So in this field, there are a lot of still open questions, but a lot of papers in the last couple of years have been working to address these problems. So the questions are, what information should actually be transmitted? You have an option of actually sending the sensor data itself, or maybe running autonomy on it, like perception or prediction, and then sending those outputs to the vehicles of interest. given that sensor data you receive or messages, how do you fuse those messages together in a way that you can then execute with a motion planning system? And then also the other question might be, how do you support different types of sensor data, such as images, LiDAR, radar, or if in the case where there's a lot of different self-driving vehicles out there in the world or infrastructure, they might operate with different types of perception models. How do you adapt the data you get from one type of perception model to another perception system and have like a way of combining all this information into a single useful representation for planning? The other component is that, of course, there's 5G now out there in the world, and it helps improve the bandwidth significantly, but there's still huge amounts of data in terms of point clouds and images that are very high resolution. You still need some amount of compression potentially to be able to send these messages efficiently with low latency, to be able to get the messages in time for the vehicle to respond to potentially some actor coming out of occlusion that it would have seen earlier. And then the other aspect is that just like all technology, there's vulnerabilities to potentially hacking or ways that can be causing noise or errors in the communication. And how can we best transmit these messages in a secure fashion or be robust to errors or perturbations to be able to be having robust communication for vehicle-to-vehicle communication. So we'll now answer some of these questions and go over the past works. So first, we'll talk about what information to transmit. Of course, you can transmit, first of all, the sensor data itself, images, point clouds, radars, but you also have the other option of being able to transmit the direct outputs of your autonomy system's perception and prediction stack. This can be detections, bounding boxes, trajectories, or also occupancy, if you think of like a more volumetric representation for your autonomy outputs of perception and prediction. And you might also consider transmitting other intermediate representations. So first off is the input fusion approach. And this is like a pretty straightforward method when you have LiDAR data, because you can, if you know the pose of every vehicle or all your infrastructure, you can send the point cloud data along with the pose of where the sensor data is, and then transform it all into a shared coordinate frame. And then you can aggregate that sensor data and then give it directly to your perception model. Now, this might be a bit more challenging in a image setting where you have multiple images. It's not clear than the shared coordinate system unless you have some depth values associated with the image data to be able to warp it all into the shared coordinate frame. But in the case of like point cloud data or data with an explicit 3D representation, you're able to easily transform it into the shared coordinate frame, and then you can run your standard perception models. And the benefit of this approach is that you're sending all the data that you potentially can get from any of your vehicles or infrastructure in the network. And it's also quite straightforward to combine in the case of LiDAR. But some of the disadvantages is that now you're basically putting all the sensor data into one single autonomy system and vehicle platform. It needs to do so much more additional computation to process all this additional data. And even in the case if you have, say, sparse representations, you still have to process quite a bit of data about your surrounding scene. Additionally, it's pretty expensive to transmit. Like I talked about before, self-driving vehicles are starting to have very complex multi-sensor setups, many cameras and many LiDARs. It's not feasible potentially to transmit all this data, even with very strong networks these days. And the other component is that if you just transmit the raw data, you're not able to maybe transmit information that could be done pre-processed ahead of time about how uncertain you are about certain locations of the scene. And it really depends on how much information you can send about the sensor data to the vehicle of interest to help it understand the uncertainty. For example, if I directly just send the point clouds of the self-driving vehicle from one vehicle to another, I don't actually encode my uncertainty of where that point cloud was observed if I just send it into that shared coordinate frame directly. But maybe points that are far away from the sensor are actually more uncertain than points that are close by. And the other option is output fusion. This is the fusing of bounding boxes and trajectories. This is a very compact representation, but the challenge is that now you don't propagate any of the additional context that was used in that processing by the perception model in the first place. So it's harder to propagate uncertainty, and you can also be wrong because of this thresholding effect for detection with NMS. So it's important to be able to still provide some way of providing scene context to get a more clear representation of the scene. And then there's methods that do hybrid fusion. So these approaches will try to create a combination of both sensor fusion and output fusion. Sensor fusion for regions that are far away and less uncertain or less certain, as well as output fusion for places that it's more confident in. And that's like a recent work from, I guess, a couple of years ago that does this approach. And then also there's work that tries to store uncertainty values associated with the output model. So for detection bounding boxes, for example, your perception model can output uncertainty values of how confident it is in the box. Then you can try to suppress uncertain confidences and increase the confidence of boxes that you're more confident in. And then that allows for a more solid detection for the actors that you have in the scene. That allows you to take the message that you value the most when you're in a network. All right, and then there's the work that's has had the most interest in the community because there's a lot more learning and data-driven aspects to it, which is intermediate fusion. This is where you can send intermediate outputs of your perception and prediction stack, such as BEV voxel features or point cloud features or whatnot, or even image features. You basically are able to distribute the computation across the different vehicles or infrastructure in your network, and then share more compact messages about the most important information in a kind of data-driven manner. So it's very compact and expressive. You can express the scene context and even preserve the viewpoint, and you have distributed computation. But the downside is that if each of the different nodes in your graph have different types of perception module, you need to perform some type of domain adaptation to transfer those features from one perception system or sensor modality to another sensor modality or perception system in a unified way so that you can finally do planning on the end of all the messages fused together. So now I'll go over some more details of the different types of intermediate fusion available. So there's quite a wide variety of works that try to use different types of neural networks, such as graph neural networks or vision transformers, to aggregate features from the different sensors and vehicles in the scene. I won't go into detail here, but there's a lot of variety of ways that people have tried to combine the intermediate representations for planning. And of course, there's not just how do you fuse the features together, but also now that you have multiple vehicles or infrastructure in the same scene, you might be able to leverage that additional data as a form of supervision to get better feature representation. So here's an example where there's a teacher that takes in all the high quality aggregated LiDAR data or camera data and then performs perception, but it's a bit slow. But then you can take the outputs of that model and use that as kind of supervision to your student networks that are actually running in real time on board on your perception system. So you can still do fusion, but then you can now supervise your features with the higher quality data from the kind of combined messages with your teacher network. And another approach that does this is called like BEV reconstruction. So instead of supervising on like the outputs through distillation, you actually can supervise through the reconstruction. So here this method proposes to do scene reconstruction with multiple sensor data from the different viewpoints. And then you can use that higher quality reconstruction to supervise the student network or the vehicle networks that are controlling each of the actors, like the SDVs, to do better, higher quality perception. So that's on the feature learning side. I already talked about it a bit briefly before, but there's voxel features, point features, image-based features, and BEV features. And it's kind of still like an open question of what type of features are best suited for fusion, because you have to take into account what networks are processing the data, what sensor modalities are you using, and there's like a bit of like domain adaptation work required to be able to get the features aligned all into a shared representation or domain for for evaluation. Cool. We talked about how you can merge different features together. There's also the aspect of compression I talked about before, which is how do we send these messages in as compact manner as possible? So there's different types of compression listed here. You can do like point cloud compression, image compression. Oftentimes these are compression based on only reconstruction metrics, but they don't take into account, say, compression based on the end task, which is autonomy performance. You might be able to discard a lot of data that doesn't matter to the actor of interest that you're sending the message to, that could be like removed and then have a lower message bandwidth. There's also output representation, which is already very compact. And then you have learning-based compression techniques, such as ballet compression for feature-based sending of messages. Now here are a couple of recent works that are different from the previous tutorial that have come out recently on this kind of compression for sending messages for vehicle-to-vehicle communication. So one option is, rather than having to send each message and compressing it independently, you can actually leverage the fact that you might be sending the messages at a like sequentially at a time to the vehicles in the network. So you can take the difference between, say, two consecutive point clouds, compute the flow, and then compress the flow into like a sparse representation for sending messages. So this type of sequential compression rather than single image or single point cloud compression can be more effective in the long run. And on a similar line of work, there is work that tries to have a shared codebook of features that are known across all the nodes in your network of vehicles and infrastructure. And then given this shared codebook, you can send much more compact messages about what you're seeing in the scene than you would before when you just have to do full compression of the data each time. All right, and then I talked earlier before that you have different sensor modalities, camera data and LiDAR data. You might have 2D features versus 3D features. How do you fuse them together? There are networks now that are done in recent works that try to do feature like fusion between the modalities and train the networks in such a way to think about the end perception task or prediction task and fuse in that manner. Cool. And then similarly, there's another type of like approach here that tries to adapt to different spatial resolutions. Yeah, I think I talked about this one last year too, but move on. All right, so we talked about sending messages in a compact manner and also to being able to share them in the feature space for more learnable based fusion. But of course, there can be errors and noise in your vehicle to X communication. So you need to be able to be robust to this. And standard ways of being robust to noise or adversarial attacks is to incorporate that into your training. So here we can use errors in the pose or the latency between the messages sent from one vehicle to the others and try to account for that noise to be more robust to the aggregation of those messages before you finally do the output perception and prediction. And then similarly, you can do adversarial perturbations. So this is where you optimize your noise that you apply to, say, feature maps in order to have poor perception and prediction performance. And you can again train with the augmentation strategies to try to be more robust to this. And then also you can be adversarial in your placement. So you can find which locations are challenging in a vehicle-to-vehicle setting. All right. And then the last aspect of V2V communication I'll talk about is data sets. So it's very challenging, as you can imagine, to be able to collect data sets when it's not yet the case, and it's still kind of a bit in the future where we have multiple self-driving vehicles or infrastructure available to run with. So you have to actually collect this data yourself by having self-driving vehicles with sensors equipped with it, or build infrastructure and then collect data where you have several nodes in the same region and then sending messages with each other. And then you create a data set like that. So oftentimes people resort to simulation, but there's also some recent real-world data sets that are available for vehicle-to-vehicle communication and vehicle-to-X. So yeah, highlight here two data sets that were there for realism and also like this is synthetic data sets. This one is based on real data and building digital twins. It's a couple years old, but there are some recent data sets from, say, Carla that are able to get much more controllable simulations and have reasonably dense data available for images and LiDAR from very different locations in the scene that you can use to have a pretty good development cycle with. And then now, yeah, it's cool that there's also now recent real world data sets available for vehicle-to-vehicle communication and vehicle-to-infrastructure. Recent papers have been using V2V for real as a benchmark for evaluating their models. All right. So to recap, we talked about various different types of fusion strategies and compression for vehicle-to-infrastructure perception. And similarly, we talked about the different types of data sets available in both sim and real for fusing and evaluating your models on this type of message-based communication data. And yeah, I think some of the promising directions mentioned here have sort of been tackled initially by some of the recent works, such as different types of models, autonomy-based models, or also different types of sensor modalities, and further reducing memory and time bandwidth. And it's just a matter now of trying to take these strategies and actually scale them and put them on a real-world system, because it's yet to really be demonstrated that you can get vehicle-to-vehicle communication running in the real world in a production setting. So a lot of work that's been done so far is exploratory. It's really now about, can we get V2V communication to work in practice in these settings, since we would say urban infrastructure or even on highway settings. So yeah, I think that's main discussion for this session of the tutorial. Happy to take any questions. Yes.
Given the reality of the variety of sensors, variety of modality, autonomy stacks, and so on, are you aware of any effort to standardize all the inputs, intermediate features, and outputs?
Oh, that's a great question. So the question was, are there any efforts to standardize the messages that you communicate between different autonomy models so that there's a standard format to make it easier to communicate between different representations, and then you don't need to have to worry so much about domain adaptation. To my knowledge, there might actually be a couple of recent works that try to propose this, but I'm not aware of any that's like being officially adopted by, say, self-driving companies. But maybe in the future, when there are a lot more vehicles out there, it will be more of a push to then standardize that format. Yeah, great question though. Thanks. Any others? All right, thank you.
Switch seconds. Yeah. Are we okay in time?
Yeah, we're doing great on time, checking Zoom. No questions on Zoom so far.
Simulation. Just reload for a good measure because the internet is good. Here. Others? It's the right one, right? It's not.
Yeah. Thanks. Please go ahead. All right. So now I'll be talking about simulation. So that's actually the main work that I do at Wabi, is mainly on sensor simulation. So I'll try to give an overview about the recent developments that we've had the past couple of years. There's been a lot of work recently, especially in data-driven simulation for self-driving. And so I'll give a quick overview of why we need simulation, some of the recent work, and what you would want in a closed loop sensor simulation system, and remaining open directions. Cool. So as you can see here, deploying self-driving vehicles in the real world is quite challenging, especially if you do most of your development and deployment strictly in the real world. And you can see here lots of different things that might happen. For example, elephants or a bear. And this is really the long tail that makes it difficult to get self-driving vehicles to work in a robust and scalable manner and in a safe way. And it's not really feasible for us to just take an autonomy system, put it on a self-driving vehicle, and then just drive millions and millions of miles, hoping that we'll encounter some of these situations, and only then to know that we don't perform well in those situations. So we need a better way to be able to expose the system to all these situations, provide them as learning data for these type of data-driven autonomy models, and then test and make sure that we can actually handle these situations in a robust and safe way. And so this workshop or this tutorial on simulation is going to be talking about kind of the current ways we do simulation in the industry that are like somewhat standard, and why they don't really meet the goals that we want in a closed loop simulation system for evaluating autonomy. So maybe not sure how familiar people are with these types of simulation, but I'll quickly go over them. First, there's log replay simulation. So this is where you have a self-driving vehicle, it's driving in the real world. It collects sensor data, which is LiDAR and camera, and it stores it into a log. And then you can take that data and then play it back to the autonomy system. The autonomy system can run that data and then generate outputs. So this is kind of like watching a movie. You're just absorbing the data, outputting it. But then autonomy outputs such as like motion plans can't actually be executed by the autonomy system because you already capture the data. So it's only log replay. This is called open loop evaluation. There's also a couple of papers this year at CVPR that talk about how open loop evaluation is not very sufficient for testing the full system of your autonomy system. So full performance of your autonomy system, sorry. So there's limitations with log replay. And also you still have the same problem that I talked about in the earlier slide, where you have to collect data, like millions and millions of miles, to get all these scenarios in the first place. So the other approach that is available is called motion planning simulation. This is where you can generate the agent behaviors in simulation and then send the bounding boxes and trajectories as ground truth perception and prediction outputs to a motion planning module. So this assumes that your motion planning system is, or your autonomy system is modular, that you have a standalone motion planner. And then you can send these autonomy outputs to that planner and then see what it does in closed loop, because you can then actuate on it and then put the PMP outputs that you generate into a new coordinate frame based on where the STV is. So this allows for closed loop evaluation. But the challenge here is that we are not actually running perception and prediction. There's no sensor data being simulated, so you can't actually test the full system performance. Because a lot of the challenges with autonomy is actually that the future of the real world is multimodal. There's lots of different possibilities, and you actually have to send that to the planner for it to actually like negotiate around those different futures. Then the last type of simulation that's standard in industry that is not that common, but is used in certain situations is data generation. So this is where you have a game engine like synthetic environment, potentially through procedural content generation and artist created assets. You can put these assets into a particular scene, and for like rare objects such as say fire trucks or ambulances that you don't see too often day to day, you can generate lots of synthetic data that you can then augment your perception data sets for. So you can use this in a small amount to kind of improve your perception models for certain cases, but you can't actually use it very well for full system end-to-end testing on particular scenarios. And the reason why is because there's a domain gap. You often can't get the performance of your autonomous system to be realistic in this type of virtual world compared to the real world. So those are the standard types of simulation that are used in industry, but it doesn't really tell us for a particular scenario, what is the performance of the autonomous system in simulation, and does it actually show what it would be like in the real world? So I'll now talk about like what type of attributes we might want in a self-driving simulation system. And then in the second half of this like tutorial, I'll be talking about them specifically with respect to sensor simulation, digital cloning, and asset creation. So the first type of attribute we want for a self-driving simulator is we want it to have diversity. We want to be able to capture all the different things we see that exist in the real world. A second aspect is speed. We all want to be able to run simulation on millions and millions of scenarios because there's so many things that can happen. We want controllability to be able to specify any type of scenario we want that we might encounter in the real world. And of course, realism. So this is about being able to be indicative of performance of what you might see in the real world. And immersiveness. So this is where, compared to say MP-only simulation, where you only simulate the actor trajectories, we want to simulate the sensor data as well. And then we want it to be reactive, which is the closed-loop evaluation setting. The STV should make a maneuver, the other actors should react to it and react to each other. And another important part of simulation is it should be able to provide feedback about the autonomous system's performance. This is about saying computing collision metrics or safety metrics and comfort, so that we know that the autonomous system is improving and also that we can see where it's failing. And then we want it to be scalable, which means being able to run this at not too much expense. I already talked about the other methods that are available through simulation, such as log, replay, motion planning only, and synthetic data. So log replay simulation, you primarily can only do open loop evaluation. Motion planning only mode, you can do closed loop evaluation, but you can't simulate the sensor data. And then there's synthetic data generation, which is using those procedural environments to generate sensor data, but it's not very effective for doing full system closed loop testing. All right, and then I had one other additional line here of recent works that are called like world models. They take advantage of recent techniques in generative AI, such as diffusion models and transformers, to try to learn on large corpuses of video data as well as text data, and implicitly learn the physics of the real world into these generative world models. And they also encode implicitly the appearance. They've been able to generate very realistic and diverse videos for self-driving scenes, but they still have several limitations that make them not suitable for full closed loop evaluation. So the first aspect is they're kind of still slow. For example, stable video diffusion takes a couple minutes to generate several seconds of self-driving simulation video. They're not that controllable. You can provide coarse text queries about a particular scene you might want, but you're not able to control the exact location of different actors, potentially the time to collision of those actors with the self-driving vehicle. And you may want that type of flexibility and fine-grained control to know the exact performance of your self-driving vehicle. Additionally, they're not that immersive and they have like reduced reactivity. So there's been recent work on providing like action conditioning to these world models, but it's not clear like how high fidelity this is. You can imagine, for instance, a very high dense traffic scenario. The SDV accelerates into it, and sometimes these world models will just make those actors disappear to make it more suitable to what it's seen in the data distribution. And additionally, these type of world models, because they implicitly encode the physics, it's hard to compute like exact metrics of have I collided with an object or not, or am I having a comfortable maneuver with respect to the other actors in the scene. And of course, these are somewhat expensive to train currently. So the goal that we're trying to do at Wabi is to build a simulation system that tries to achieve many of these attributes. And the way we try to do it is that we want to be able to build a simulation system that is explicitly grounded in our physics and has actual 3D representations. So you can kind of think of this as the way you play like a video game, say like Grand Theft Auto, but instead we want it to be data driven in every aspect of our simulation system, specifically for autonomy evaluation. So we can still use generative AI techniques to be able to create very highly realistic assets and content, and also behavior models. But we can also still use computer graphics to make them fast and controllable, to use machine learning to make the actors intelligent and reactive and provide learning-based feedback, and etc. And also by taking this kind of modular approach, we can achieve a bit more scale and at lower costs. So I'll quickly walk through like what a closed-loop simulation system looks like. So first, there's a simulation specification. This is where you specify all the actors in the scene, as well as the goal of the scenario that you want to achieve. And in addition, you might also specify the environment conditions of the scenario. So what the weather is looking like, the sensors that you want to simulate for your particular scenario. That goes and initializes a world state. And then from that world state, you can load in the assets that are required to represent that scene, such as the dynamic actor vehicles, the background, pedestrians, etc. And then you can simulate the sensor data according to the vehicle platform that you are interested in evaluating. Once you have the sensor data, you can feed that into your autonomy system, and it will generate outputs such as, say, steering and acceleration, for example. And then you can give those outputs then to a vehicle dynamics model, and the dynamics model then updates the state of the self-driving vehicle, its new location, velocity, acceleration, etc. And additionally, you can update the other actors in the scene based on the SDV's behavior as well as each other's behaviors. Then this all goes and updates the world state, and then this is a closed loop simulation. You can unroll the scenario out. Another aspect of simulation that's not often talked about is latency. So, for example, in a particular truck compute or vehicle compute, it takes time for the autonomy system to take the sensor data and generate actuations. And this type of delay is very key to measure and model in order to have strong bounds on the reaction performance of your self-driving vehicle. And oftentimes you're running your simulation system in a software in the loop setting. So you're running your simulation and self-driving autonomy system on cloud compute, which is not indicative of the actual hardware compute you run on your autonomy system on the actual self-driving vehicle. So you need to then model and estimate how long it takes to run different modules of your autonomy system and how long it actually takes to generate those final actuation outputs. And that's a key part of latency simulation. And then the last component is an evaluator, which says, I will take the world state at each time step and see how the autonomy system is doing, and then provide feedback to it. You can also use this evaluator to provide an assessment of how well the self-driving system is doing on a set of scenarios, and then understand which situations it's not doing well and in which ones it is. So those are all the aspects to a simulation system. And here's kind of a streamlined format of it. And this is next couple of slides are just to show that if you have the framework of a full closed loop evaluation system, you can do a lot of the simulation modes that we talked about in the previous slides. So for example, here, this is the same diagram, but now we replace the sensor simulation model and the behavior models with the original data from the log. And at each time step, you can replay the sensor data and the actor trajectories that you have from that sensors into the autonomy system and see how it performs, and then run the same evaluation system. Here's another mode that we talked about, which is motion planner closed loop simulation. So here, instead of having sensor simulation, you can replace it with a realistic perception prediction output system. So you can kind of learn, there's like a paper that we had in the past that showed that you can learn what are the types of errors that perception and prediction systems make. And based on that, train a network to generate that given a particular ground truth scene configuration. And you can give that then to the motion planner to then see how it will perform in this type of closed loop framework than just providing the ground truth actor trajectories initially. And then there's synthetic data generation as well. All right, and then the other aspect of the simulation system is that there's a variety of ways you can initialize the scene, such as log-based or heuristic initialization or procedural generation, or even specify exactly by a human. And then you also have a wide variety of ways of specifying the behavior models that are controlling all the agents in the scene. You might have a high-level orchestrator that controls all of them together. You might have heuristic actor models or even data-driven models that are trained to kind of mimic a particular behavior of a driver or agent in the scene. And given the wide variety of models you have for scene initialization and actors you can do different types of applications of testing for simulation. For example, adversarial actors, or to be able to test, say, coverage to making sure you cover all the different scenarios you might want to handle for simulation. Cool. And then rest of this tutorial, I'll probably primarily be talking about sensor simulation and asset reconstruction, as well as hardware, like the full system simulation system. And after this session of simulation, there's a talk by Kelvin. We'll go over into more detail about how you initialize the scene and how you actually model the behaviors of all the actors in the scene. So yeah, in this year for the tutorial, we split the sections up a bit differently. I'll be talking primarily about virtual world creation, so building the assets, simulating the sensor data, as well as the vehicle platform modeling. So I'll talk at a very high level about the vehicle dynamics model that takes in the actuation outputs from the SDV, as well as hardware in the loop simulation at a very high level about the latency modeling aspect of simulation. And then the second session, we'll be talking about the scenario representation, as well as agent dynamics. All right, so we'll now talk about virtual world creation. So here's a quick recap. I mean, I already talked about it earlier when we discussed all the different attributes you might want in a simulation system. It's even more so the case when you're trying to build a virtual world that you want to simulate highly realistic sensor data for. You want to have realistic assets, controllable assets, so being able to change, say, illumination conditions or the shape of your actors. You want to have a wide variety of actor shapes and classes, and you want it to be fast to render with. And yeah, in the past, a lot of ways that people have built assets are with CAD models, and this often requires manual creation by artists, and this can be quite expensive and slow. You can have very high controllability, but in order to achieve very high realism, you often need to have a lot of manual effort to do so. And so one way we can overcome this is to instead use the self-driving data that we've collected in the real world and use it to build our assets instead. So this is called like digital twin cloning or reconstruction. We can leverage a lot of the recent techniques from, say, neural rendering to reconstruct the assets from sensor data and then leverage those assets in simulation. Cool. And so we'll now talk about the different aspects of asset reconstruction or digital twin cloning in the next part of this tutorial. So there are three ways we kind of separate the asset categories in together, but there's also recent methods that kind of combine all of them all in one place. But there's background assets, which is kind of like the static scene elements you have in the scene. There are rigid actor assets, such as your standard vehicles. And also there are deformable actor assets, which are like pedestrians, in some cases like motorcycles or cyclists, that you need to model the motion and the deformation of the meshes themselves. So now we'll talk about background asset creation. There's different ways you can reconstruct the assets. A lot of the work these days is on neural rendering, but I'll quickly go over some of the classical methods that have been used in the past. So of course you can aggregate like LiDAR data or do, say, structure for motion to create an initial geometry of your scene. This is pretty simple, scalable. It's a very standard way to do it, but there can be noise when you aggregate the LiDAR together. There can be holes in your meshes, especially in like, say, structure for motion and CoMap. You're not able to get, unless you have a lot of views of the scene, a very high quality mesh. All right, and then there's these recent works that are based on like neural rendering and per scene optimization. So given a sequence of sensor data, you can reconstruct the geometry of the scene by just by remodeling the sensor arrays. So this is where actually a lot of the work that you're doing for asset reconstruction can also be reused when you're actually running sensor simulation for rendering to actually simulate the sensor data itself. Because these techniques apply the idea of, if I can recreate the sensor data, I can reconstruct the scene. So here we can see a neural rendering representation that's reconstructing the mesh for the collected sensor data. And it's pretty realistic, but the challenge is that you can only reconstruct the areas you observe, so there's no scene completion, and you're optimizing per scene. And currently, sometimes the neural rendering techniques can be quite expensive to train. But as we'll see in future slides, there's been a lot of progress in the community, such as with Gaussian splatting, that accelerates the training time it takes to build these scene representations. All right, and then there's also the idea that instead of training at each individual scene, the sensor data to reconstruct the mesh and assets, you can try to learn a generalizable model. So this trains on multiple scenes all together jointly. So for example, NKSR has learnable kernels that learn across large ground truth synthetic scenes to convert unstructured point cloud data to local meshes. And it achieves pretty high quality and is also reasonably fast to run at inference time. And there's other recent methods too that kind of like take in very sparse sensor data, such as a small collection of images, then tries to output a pretty dense reconstructed scene. But it's typically working on kind of more smaller locations rather than on large scale scenes. And yeah, there's some of the cons, not doesn't apply for all of the methods here, but some of them can be quite expensive to train because you're training on large amounts of data. This can be like on the same order of, say, diffusion models, or that train on like large amounts of image data. And the prediction results are not going to be guaranteed to be faithful to the original ground truth compared to optimization methods, which are specifically optimizing for the reconstruction loss with respect to the original sensor data. And in some methods, not NKSR, for example, but you might require accurate normal estimation to get higher quality geometry. So that's on the background asset side. I'll now talk a bit more about the rigid actor assets. A lot of the methods still apply, but a lot of methods are out there that focus on these foreground actors in particular. Again, there's the aggregation-based approach, which achieves reasonable quality, but most of these papers are now kind of older methods of reconstructing the meshes compared to the most recent techniques. And then, of course, there's explicit mesh-based inverse rendering approaches. So here you have a template mesh, and then you try to optimize that template mesh with respect to your sensor data in a differentiable rendering manner, and then predict the kind of shape. But you have priors now on basically what the final shape should look like. So then when you optimize with respect to the sensor data, you still have a pretty complete asset. This is pretty simple and scalable, but it only works if your template is a very good initialization in the first place. Otherwise, the optimization can typically fail when you're trying to reconstruct particular actors in the scene. All right, and that's on the explicit based approach, but there's also recent neural implicit approaches, such as like occupancy fields or implicit sign distance function fields that you can optimize with neural rendering techniques, similar to what we talked about for the background assets, such as like urban radiance fields. There are specific works that focus on foreground actors, such as vehicles or other rigid objects and signs and whatnot, and optimize the neural representation to reconstruct mesh. And then some of the works here focus primarily on like the geometry and the color, but there's also a very large range of works that focus on the idea of inverse rendering, which tries to decompose the asset into geometry, material, and appearance, and lighting conditions. Right, and then again, some approaches focus on like the idea of optimizing directly on your sensor data to reconstruct a particular asset. But just like in the background assets, you can train on large amounts of data and kind of learn a prior on the types of objects that you have. So here are like previous approaches that kind of train on multiple vehicles and then learn like a shape representation, and then kind of say, given a single image or a set of images, predict a pretty dense, high quality shape from it. But again, the same artifacts can appear when you have a prediction-based method compared to optimization. It may not fully match the original reconstruction you had in mind. And depending on how far away the objective is that you're trying to reconstruct, if it's out of distribution, you might fail. All right, and then yeah, there's now also quite a rich line of work on generative modeling to create these assets instead, but they're typically used more in the art field and kind of like synthetic assets that you think of when you look at some of these like visuals here. They're not fully used right now in trying to like build high quality real world assets for say self-driving simulation. But it's a very promising line of work too, where you can just provide a text query or a single image condition and generate a pretty highly complete asset. And yeah. And then the last type of foreground assets I will talk about before moving to deformable assets is adversarial actors. So there's a lot of work that says I can focus on reconstructing the real world, but I can also look into understanding from a purely simulation standpoint, what types of actors or assets cause problems to my autonomy system. And you can optimize the mesh if you have a differential rendering framework to see what type of meshes are causing the most challenge for your perception model, for instance. And there's also recent works that try to optimize NeRF-based radiance fields to see what are the most challenging scenes in terms of geometry and appearance to your perception system. All right, and then the last aspect I'll talk about is deformable actor assets. So there's a first type of way you can reconstruct pedestrians and humans in your self-driving scenes is by having mesh templates. There's a long line of work such as with Simple, and now recently some works that do it for like animals such as horses, that try to reconstruct your scene based on a single input image or sensor data, and then using a template mesh that you can deform with some learnable parameters to estimate the deformed mesh or the posed mesh that matches the original observation. So these types of approaches are like quite robust in that you can always get a highly complete human shape, but it doesn't account for clothing and it doesn't fully match the original actors in the scene. And of course, there's now recent neural rendering techniques that build these types of pedestrian assets from sensor data. There's implicit volumetric fields, and there's also recent works that use Gaussian splatting, for instance, to model the humans mesh in conjunction. So there's like one paper at CVPR this year called Goem Avatar, which is pretty cool. You build a mesh of your like pedestrian, but then you apply Gaussians on top of these meshes to then do like higher quality photorealistic rendering. So that's on the asset side. I'll now talk a little bit about the sensor simulation aspect. Again, same desiderata of realism, controllability, diversity, and speed. There's many sensors available on a self-driving vehicle, but the ones of primary interest are LiDAR simulation, radar simulation, and camera simulation. So these are all light-based sensors, but LiDAR and radar are active sensors. You send a beam of light or wavelength light into the scene, see how the wave propagates with the surfaces it interacts with, and then receive the response curves to these waves. Then camera is more passive because you have many different light sources available in the visible wavelength spectrum. You have a sensor that then receives that sensor data and provides the response curves from the light sources available. So I'll now talk a little bit in LiDAR simulation. So here's a quick video of what a LiDAR sensor looks like. So we can see we can generate pretty high quality geometry. It's somewhat sparse in certain situations, such as above or below when we don't have enough density of the beams. But overall, for close by objects, you can get very high quality geometry. And the way LiDAR works is you send a beam of light, it hits an object, you measure how long it takes to come back to the sensor. That tells you how far away the object is. You can also see that the LiDAR is colored by intensity. So this tells you how strong of a peak of a response the LiDAR beam is to the particular object it hit. And that tells you some material properties of the scene as well. Okay, so there are many different ways you can simulate LiDAR sensors, and we use the same kind of Venn diagram last year as well. We just expanded the number of papers that are available to do this type of simulation because as you can imagine, with the field growing very fast, there's a lot more papers these days that try to do sensor simulation for self-driving. And a lot of them are now recently combining the same three like fundamental aspects that you might want to build into a sensor simulation system. you have physics because there's a very exact way of how light interacts with the scene. You have data because you want to match a particular distribution of the noise that you see in the real world with your sensors. And then you have machine learning to kind of train on that data and leverage the physics to try to make a realistic sensor simulation system. Cool. So again, at a high level here, there's very different techniques available that you can use for physics, data, and machine learning. With physics, there's many different methods available in the computer graphics community for simulating light interacting with scenes, such as with ray tracing and rasterization. On the data side of things, you have a lot of data you can collect from the real world that might be useful for modeling sensor data. So for example, you can record how the LiDAR interacts with different types of materials and see at which point a particular object does not return LiDAR points from, for say, concrete versus say a highly reflective object. And then on the machine learning side, we have different types of approaches and architectures available to learn from real world data, the realistic sensor simulation. For example, there's generative models, style transfer approaches that take simulated data from a physics-based engine and converts it to more realistic real-world data. And there's also neural learning approaches that we talked about in the past for building the assets in the first place. So here, I'll quickly go over some of the past approaches that have been done to do LiDAR simulation. First is the game engine-based approach. Here, we're only using physics and we're only using artist-created assets. So there's a bit of limitation, the realism compared to the real-world data that you want to fit to. There's also more complex physics approaches. You can have very high fidelity physics models available for LiDAR sensors, but it just requires a lot more information about your scene that you could typically get from reconstruction alone. You have to have a lot of manual effort and high quality data collection to build very accurate material properties specifically for the LiDAR wavelength spectrum, and similarly for the geometry and illumination conditions in the scene. But with that, you can get pretty high quality LiDAR, but it's just a lot of effort and also not very fast at the moment. Then there's a lot of recent works on using real world data and then having a generative model predict from some type of lane code to simulate the LiDAR. So here you can see like you can use VAEs or diffusion models, and you can sometimes condition these models on particular input conditions, such as like an initial point cloud, but you don't have very strong controllability of the scene configuration. So it prevents it from being used fully in like closed loop simulation systems. And then, yeah, there's this recent work that has that most of the field is going towards, I feel, which is where you're trying to build assets of individual objects. And then you do like neural based rendering approach to kind of simulate the sensor data. So here, there's a couple of approaches that just build the meshes and do ray casting, and then apply ML at the end to add some noise to the sensor data to match the real world data. And then here, there's an example of like, again, an approach that's called like LiDAR DM that builds, that does additional aspects of the simulation system before doing sensor sim. So you can take a scene placement and then generate the meshes given the scene placement in a generative model style, but then you can then do standard traditional rendering techniques such as ray casting to generate the initial point cloud. So this is kind of a generative model combination with physics-based rendering approach plus some machine learning at the end to do the ray drop. And ray drop is where you send a beam of light of LiDAR and it will hit an object, but it may not come back to the sensor with enough signal to return as a point. And then there's a couple of works that are available for neural radiance field approaches that are specifically optimized for LiDAR sensors. So for example, there's the neural LiDAR fields NFL that specifically tries to model an active sensor and accounts for some of the effects you might see with LiDAR data, such as beam divergence, multi-echo returns, such as like dual returns. If you send a beam of light, you might get two response peaks that you want to send back as points to the sensor. This is getting very high quality scene reconstruction, but it can still be slow to render. And it still doesn't take the fact that you might need to simulate different types of sensor modalities. So I'll talk in the next couple of slides about recent works that do both camera and LiDAR simulation through neural rendering. Oh, I guess that's going to happen after I finish the camera simulation work. But I'll first talk about radar simulation. radar is probably one of the most challenging sensors to do simulation for because it's so noisy. You are sending much larger waves of light into the scene, and there's a lot more noisy propagation effects that can happen with radar sensors compared to LiDAR or camera. And then based on these waves that you send out, you can get information that's not just about the appearance or geometry, but also the Doppler information, such as velocity of how fast different objects are moving in the scene. So overall, radars are much more challenging to simulate. But again, the same core components that you use to do rendering of, say, LiDAR sensors applies to radar, physics, data, and machine learning. Some methods try to like bypass the whole like rendering approach of radar simulation and try to generate directly the detections of the radar sensor, but it's still quite challenging and it's not yet been easily generated for large scale scenes with high fidelity. And the other challenge with radar sensors is that there's often a lot of black box post-processing to kind of generate the final detections. And there's a lot of physics involved that is about how the radar waves interact with each other and what's the best like peak to signal noise ratio, for example, of these sensor data to generate the final detections that you need to potentially model in your scene. So again, lots of different techniques, but still some challenges in getting highly realistic radar simulation data. And similar to how we have neural rendering for LiDAR and camera, there are several works that try to extend it to radar. But it's promising, but they're still focusing on maybe more small scale scenes, synthetic scenes, and yet not yet there's like a really scalable radar simulation approach that works on large scale self-driving scenes that are with lots of moving actors and with kind of the standard radar you think about, which is FMCW radar, where you get also the Doppler information. But yeah, lots of different neural rendering approaches available as well. And then the last sensor simulation I'll be talking about is camera simulation. So we're all very familiar with cameras, so I won't go into much detail about how cameras work, but they're very complicated, some particular parts such as the image signal processing pipeline. And as you can see here, from compared to last year's tutorial, there are a lot more works in camera simulation than ever before. It's crazy, right? There's 40 papers here. And a lot of them are in the neural rendering and Gaussian splatting and diffusion model type work that's been happening in the recent year or so. That's leveraging a lot of data and machine learning together to kind of generate pretty high quality camera data. So again, lots of work done in the graphics industry before because of video games to simulate camera data with high quality. But oftentimes you just need a lot of manual effort to build high quality assets for camera simulation. There's also recent like previous techniques that build on like very just quick and fast view warping. So given some coarse geometry of the scene, I can warp my sensor data to new viewpoints for closed loop simulation. These work still like reasonably well and are fast. They just can't do all the different things you might want for sensor simulation, which is having fine-grained control of the actors and being able to have the SCP in a very wide variety of locations compared to the original trajectory. And then there's also the neural rendering approaches that we'll be talking about in more detail. So I'll quickly go over the previous work that's done in the past on the subtasks, but most of the work these days is focusing on full camera simulation. But in the past, there were works that tried to do certain aspects of camera sim. For example, some works focus on just the novel view synthesis aspect of simulation. So novel view synthesis is where we can take the original static scene and then render it from a new view. And then other focused on dynamic actor simulation, which is given the same scene viewpoint, moving the dynamic actors around. So this one focuses more on the static scene warping and novel view synthesis, which is called Vista. It is image warping based on some estimated depth of the image. You can warp it to new locations of the STV. And then here's some additional works that have been focusing on the novel view synthesis side. Some of them are quite like a bit old now, like BlockNerf, but there's also some recent works such as Innovis and Neuras that do pretty high quality novel view synthesis through neural rendering and scene reconstruction. But this focuses primarily on the static scene, and there's also the dynamic actors to consider. And Oh yeah, so there's one actual additional component for static scene novelty synthesis, which is also scene editing. So it's not just about reconstructing the original scene, but being able to create new environment conditions that are totally unseen for that particular scenario. So there's work such as Climate Nerf that tries to create new weather conditions such as flood or snow, which there's lots of traditional physics-based rendering approaches available. It just can be either slow or you can only model it typically for, say, the camera sensor. You need to also do an additional modeling work for, say, LiDAR or radar data. And then there's also scene relighting, where given the initial geometry mesh, you can change the illumination condition and then run that through a physics-based render, plus some machine learning to kind of generate new scene relighting. For dynamic actors, main challenge is being able to estimate the illumination conditions of your scene and then render those actors into new scene locations. So if you have good sensors such as fisheye cameras, you can capture pretty high quality environment maps for then putting into physics-based rendering engines. There's also some recent work called GeoSim, it's a couple of years ago actually, that does view warping-based methods for dynamic actor simulation. So given a dynamic actor mesh and a geometry texture that you project from a particular image, you can warp it to new locations. And now that's kind of talking about the subcomponents for camera sim. I'll now talk about the full system camera simulation approaches. So there's game engine-based approaches such as, say, Carla, or Grand Theft Auto as game engine-based approaches for camera simulation. You have full scene controllability, but the downside is the domain gap, because there's a bit of a gap between simulated sensor data and real data, especially if you're trying to run your sensor simulation fast. Then there's the purely generative model approaches. So given some type of initial conditions, such as a segmentation mask, you try to inpaint the entire scene. This has some realism artifacts. And there's also the idea of using computer graphics plus image translation techniques to leverage both physics-based rendering and machine learning to generate more realistic camera data. Cool. And then lots of different works on neural rendering approaches. So you can simulate both camera and LiDAR through these type of volumetric representations. And there's also some recent works on Gaussian splatting as well that try to represent the scene as a sparse set of points that you can then just rasterize into the camera image to generate the rendered data. So pretty realistic. And with the Gaussian splatting, there's more higher frame rate, but can still kind of be slow to train. And especially for like Gaussian splatting and other neural scene representations, you can only really simulate viewpoints that are close to the original trajectory. There's still quite a bit of challenge and extrapolation from very far away viewpoints. And yeah, here are some recent works that are on the Gaussian splatting side compared to the neural radiance field work. A lot of recent works for Gaussian splatting for self-driving scenes typically leverage LiDAR data as initialization, because typically Gaussian splatting doesn't have very high quality geometry. So if you can initialize from a geometry scaffold, you can then fit pretty well the Gaussians to the camera data that you observe. But yeah, there's a challenge with the limited viewpoints for kind of closed loop evaluation. And then there's some recent works. I think I kind of talked about this when I talked about editable neural radiance fields, but this is inverse rendering. So you can change the lighting conditions and use a combination of both physics-based rendering as well as machine learning. Yeah, and then here are recent works that do both camera and LiDAR simulation with neural rendering fields. URAD and Alignment are actually at this year's CVPR, and they kind of build off of the idea of leveraging both camera and LiDAR data to build higher quality scene representations. And by learning with both multiple sensor modalities, you can typically get better scene. And now I'll talk a bit more now into the kind of world model approach. One of the original works that tried to learn dynamics with the appearance is DriveGAN. And you can see here that you can have a lane code that updates the state of the world. And then you generate the camera data accordingly based on that scene configuration from the lane code that you have. But now there's a lot more work that's in this area where you train on large amounts of data and you encode both the dynamics as well as the appearance of your scene in these models. So of course, there's like Sora. We have some work at Wabi called Copilot 4D that generates LiDAR point clouds with pretty high quality. And the recent work, I think this month, I think called Vista, which has some pretty high quality, longer duration videos for camera simulation. And I talked a bit about this earlier in the tutorial. There's like a bit of pros and cons between sensor simulation that's kind of game engine or like assets and 3D world modeling that with explicit physics, and these world models that try to implicitly model the dynamics of the scene. You have less controllability with these type of approaches, but the world models are able to generate currently a bit better extrapolation. They have better object completion, for example, compared to the scene reconstruction approaches. But there's still a lot of challenges with using these type of world models, like I talked about before, for closed loop evaluation. And then I talked primarily about sensor simulation from the rendering standpoint, but there are a couple of cool works that happened this year that are also on doing not just the sensor simulation aspect, but also having a data-driven way of generating the scene. So there's ChatSim, which is given some text prompt. It will use like GPT to kind of ask different modules to build the scene for you. So there is a module that focuses on scene reconstruction, another module that focuses on like actor placement, and it coordinates between all of these to create a particular scenario with reasonably high quality. So this might be a good way of blending both generative models with standard like physics-based rendering with explicit representations for higher fidelity. And then there's a recent OASIM simulation framework that kind of leverages neural rendering into a game engine format for higher quality sensor simulation with scenario evaluation in the loop. And lastly, I'll just talk about how with high quality sensor simulation, you can typically do end-to-end evaluation of your autonomy system on new counterfactual scenarios. So you can see like new conditions that you may not have encountered in the past and see how it performs on them. All right, so in summary, we talked about different sensor simulation systems and how they all leverage some version of physics, data, and machine learning. And we list here like some of the pros of each of these types of approaches, as well as the disadvantages of using them. And you have to find the best trade-off when you combine them, particularly for your particular use case. Right. And then the last section of this tutorial session, I'll be talking about vehicle platform modeling. So this includes the dynamics of the self-driving vehicle, as well as hardware in the loop simulation. So now I'll talk about the SDV dynamics. So we just recall quickly that we have an autonomy system. It will output actuations given the sensor data of the scene. This includes, say, steering and acceleration. But then you need to actually have a model that says, given this and the SDV's position currently, what is the new position and state of the SDV? And oftentimes we have like a module in the autonomy system called a controller that tries to achieve a desired trajectory. But the real world is noisy and there's complicated physics involved. You may not necessarily be getting to the correct position that you want. So the vehicle model dynamics needs to model this like actuation outputs, where the state of the SDV should be afterwards. And for like say self-driving trucks, for instance, there's not just steering angle and brake, but there's also different types of braking you can do, such as engine brake versus the throttle, like pressure brakes. And these then can determine the final state of the self-driving truck. All right, so to be able to test our autonomy system end-to-end in closed loop, we need to be able to take those control actuation commands and put them into updating the state of the self-driving vehicle. And I'll briefly talk about some of the dynamics models available that are typically used to model the motion of the actor. And these are pretty simple models, but of course there are higher fidelity vehicle models available. This is just kind of to give an overview quickly of the field. So here's an example of like a kinematic bicycle model. This model assumes you basically can convert the two front wheels with a single wheel, the two back wheels with another single wheel. And then given these two wheels, you can just assume some very standard kinematic motion of how the vehicle should move given the steering and acceleration. This kind of assumes that you have like a four-wheeled vehicle, like a sedan, but there's also extensions to these type of models to tractor trailer and larger, more complicated vehicle setups. And yeah, these are very simple, easy models, and they don't fully account for all the things you might think need to be modeled for vehicle dynamics. For example, there might be tire slip. If you have environmental conditions like wet roads, there are more changes in friction that you need to account for your vehicle dynamics that don't typically get modeled in a kinematics model. So then other model that's available is a dynamic bicycle model. This takes into account these more detailed physical parameters such as mass, moment of inertia, the weight distribution you might have on your vehicle. And it can also potentially, with higher fidelity dynamics models, take into account, say, a wet road or a very windy day to account for these more challenging situations that result in more like harder to model physics that we need to be able to do so in safety critical situations. Cool. Yeah, and I talked about earlier that we can extend these type of kinematic and dynamic models to multi-body vehicles, such as a tractor trailer set up for a self-driving truck. And yeah, there's a lot of work out there that covers this in more detail, but just wanted to briefly talk about how we have vehicle dynamics that are very key to simulate, to update the state of your self-driving vehicle. And the fidelity you do it at is pretty important, especially for the self-driving vehicle. You might choose a bit higher or lower level fidelity for the other actors in your scene. All right, and then the last slide I'll talk about is hardware in the loop simulation. I talked about earlier how you have latency modeling that needs to be done if you're using software in the loop, because you need to model how long it takes for the autonomous system to run on your sensor data. But there's also ways you can build the exact hardware compute that runs on your actual self-driving vehicle as a test bench is what it's called. These test benches are very identical to the hardware that runs on the actual self-driving truck, but instead you have it now available in the cloud to run your evaluations. And these can provide you more accurate timings of how long it takes to run different modules of your autonomy system, for example. So hardware in the loop is a bit more expensive to build these test benches, but it provides you a bit more realistic indication of your full system performance. And you can actually get true real-time measurement of how your autonomy system performs compared to the simulated version with latency in the loop. The downside is that because it's with a test bench, it's expensive, and also you cannot run faster than real time because it is running as if it was actually on the truck. So if you have much more faster or scalable simulation systems, you can run them at much faster frame rates and then run much more scenarios at scale and get better signal out on an aggregate of your scenario evaluation system. Cool. I think I went a little bit quickly, but that's the main gist of like simulation system, where we talked about primarily asset creation and sensor sim, as well as vehicle dynamics and hardware in the loop and vehicle platform modeling. I think that's it. And the next session will be from Kelvin on scene content creation and modeling the actors' dynamics. And yeah, if there's any questions, I'll be happy to answer them. I went kind of quickly for this one. Thanks.
Like to feed questions.
Yeah, sure. Oh, I think there's a couple online in the chat. Neural rendering and reconstruction are often presented with minor changes to the original point of view from the captured scene. How do they perform with substantial changes? For example, the data captured during driving straight, and then the planner now makes a U-turn. This is a great point. So if you run, like, say, neural scene reconstruction on the original log, you assume in your reactive law replay setting that the STV does not deviate too far from its original trajectory. If you do have it deviate far, you have a significant drop in realism. And this is where you need to be able to do not just reconstruction, but also maybe scene completion or generalizability of being able to see parts of the scene that you maybe not have observed originally. Or you could potentially consider collecting much higher quality data by driving in a lot of different scenes and combining that data to create a more dense reconstruction for handling the extrapolation case. But in the current setting that a lot of the neural rendering approaches take, where you build your digital twin from a single log, you can have extrapolation artifacts when you deviate far from the original trajectory. So it's a good question. Thank you. That's it.
We can move to the next session then.
All right, thanks.
Yeah. Just in case.
Thank you.
Hey, I'm Kelvin. I'm a researcher at Wabi, and in the previous session on simulations, Siva walked us through sort of the various components necessary to build a high fidelity closed loop simulator for self-driving, right? So we saw how to build a digital twin of the real world, how to simulate high fidelity sensor data within that digital twin, and how to model the vehicle platform itself, right? So in this session, we're going to discuss how to generate and simulate the scenarios that populate the contents of those simulations. And before we get started, what exactly are scenarios and what kind of scenarios do we actually want for our closed loop simulator? So scenarios kind of form the content of the simulation. They specify what kind of actors are in the scene, where they are located, and how they behave over time. And they're essentially the simulation counterparts to the kind of traffic scenarios we might encounter in the real world. Only now we're going to simulate them in a high fidelity closed loop simulator instead. So if we were to allude back to sort of our old video game analogy, scenarios are almost kind of like the levels of a video game that we can use to test and train a self-driving car with. Okay, so let's go through a quick example of what a scenario would look like in a little bit more details. So to create a scenario, first, we'll need to specify the environment around the self-driving vehicle. So for example, where is the self-driving vehicle located, right? What does the road topology look like around the self-driving vehicle? What is the weather condition like, et cetera, right? Next, we'll also want to specify the initial conditions of the simulation. So here, we'll specify what actors are in the scene, right? How they look like, what are their initial dynamic states, et cetera. So for example, here we specified a scenario with roughly maybe 20 actors in the scene, some of which are cars, some of which are sort of like larger trucks or buses, right? And they're all moving, or yeah, they all have like highway speeds initialized. And then finally, we'll want to specify how these actors will behave over time and how they might react or interact with the self-driving vehicle. So for example, maybe we want to test the self-driving vehicle's reaction to cut-ins, right? So we'll want to specify that the actor to the right of the self-driving vehicle will cut in front of the SDV with a certain definition of severity or aggressiveness, right? Okay, so another basic question we should answer is, what kind of scenarios do we want for training and testing a self-driving vehicle? So the most basic kind of scenarios are nominal traffic scenarios, right? These are the kind of typical traffic scenarios you encounter when you drive in public roads on the highway or in city streets. And these nominal scenarios can be used to train and test a self-driving vehicle under conditions that we'd expect to normally encounter when we deploy to public roads. Now, as Siva mentioned in the previous session, self-driving vehicles also undergo a lot of structured testing in the real world. And this allows us to test the self-driving vehicle in sort of potentially rare situations in a very controlled and repeatable manner. So for example, as we discussed, to test the SDV on how it might respond to various cut-ins at various levels of severity. So like in the real world, we can recreate these structured test scenarios for simulation as well. But unlike in the real world, we can now run these tests much more safely, much more scalably, right, at a much larger scale, and in a much more controlled and repeatable manner to really precisely characterize the performance of a new autonomy stack before we deploy it to the real world. So here we're just showing an example of where we were able to parameterize the scenario and maybe intelligently sample different points in the parameter space of the scenario to really characterize where the self-driving vehicle performs well and performs maybe a little bit more poorly in that parameter space. And we'll go into this in a little bit more detail later as well. And then beyond structured testing, it's also really important to be able to verify how the SDV would behave in rare but safety critical scenarios. So for example, how the self-driving vehicle might behave if this actor in orange here sort of like speeds up quite a bit on like 2 lanes away and then it just aggressively cuts in front of the self-driving vehicle. So this allows us to discover potential issues with the autonomy stack early using simulation and also verify the safety of the self-driving vehicle before it ever gets deployed to the real world. And additionally, these scenarios can also be used to more effectively train the autonomy stack in simulation, as opposed to, say, using just nominal traffic scenarios that we've collected from the real world, which could be usually quite boring. And then finally, it would also be very useful if we had the ability to also take any log that we've captured from the real world and then just turn those into reactive closed loop simulations, right? And then we can resimulate those scenarios and generate tons of variations of those scenarios as well to really like test and train the self-driving vehicle with. So this will allow us to test different autonomy systems under the same conditions and answer counterfactual questions like, what would have happened if the SDV had braked earlier? Or what would have happened if an actor in front of us hard braked instead of going straight, right? Cool. Yeah, so hopefully through this discussion, I've convinced you that there's sort of a vast variety of different kinds of scenarios that we'd like to test and train a self-driving vehicle with, right? And then the ideal simulator should be able to generate and simulate all of these scenarios and many more. So this is the topic of today's session. Sort of in the first half of this talk, we'll discuss various approaches to scenario generation that have been proposed in the literature. And after that, I'll give a brief introduction into actor simulation. So how can we sort of model the behavior of other traffic participants in a scenario, and then use these models to sort of simulate the various kinds of different scenarios that we just discussed earlier. So let's get started with scenario creation. So in general, there are 4 main approaches to scenario generation: manual creation, procedural generation, extracting them from real-world logs, and generative models. Each of these approaches have their own pros and cons, which make them suitable for different applications. And as we'll see, these different approaches to scenario generation are also not mutually exclusive, but actually complement each other to support various kinds of scenarios that we want to create. So manual specification is perhaps the most straightforward approach. This approach involves having a human manually specify various aspects of the scenario, either through a domain-specific language like OpenScenario 2.0 or Scenic, or through graphical user interfaces, where maybe one can drag and drop actors onto a scene, configure their characteristics, and specify how we'd like them to behave, right? So the advantage of this approach is that it gives the human author very precise control over the entire scenario. So for example, if I wanted to brake test the self-driving vehicle, I can really precisely place an actor at various distance ahead of the self-driving vehicle, and then configure those actors to brake at various levels of severity. And this approach allows us to really precisely also recreate safety critical scenarios from public databases, for example, and then evaluate how the self-driving vehicle would behave in those scenarios. However, as you can probably tell, creating scenarios in this way, it can be quite challenging because specifying all of these scenarios in this way can be quite tedious, right? So this would really limit the scale and diversity of the scenarios we can create in this approach. So an alternative is procedural generation. So here we can compose predefined rules, heuristics, and parameters into almost kind of like recipes for how to generate scenarios at scale. And this has been shown to, or successfully applied to generating realistic scene layouts, or even realistic maps from scratch. For example, in an open source simulator called MetaDrive, they use procedural generation to sort of create really realistic maps for training and testing a self-driving vehicle in. Now, this approach allows us to generate a lot of variations at scale. But at the same time, we can also encode constraints on the kind of scenarios that we want to generate and what constitutes useful or realistic scenarios within those heuristics and parameters themselves, right? However, designing good rules and heuristics can be challenging and time-consuming, and it requires a lot of human expertise. And at the same time, the use of these rules and heuristics limit the realism and diversity of the scenarios we can generate in this way. Cool. Instead of creating scenarios from scratch, we can also extract scenarios from logs that we've captured from the real world. And this is what many popular planning simulators do today. For example, NuPlan, Nocturne, and Waymax. And in addition, we can also generate variations of those scenarios by fuzzing the parameters of the scenarios or modifying the behaviors of the actors in the scenario from the original log. The advantage of this approach is that it yields realistic scenarios by definition, and it also allows us to leverage the scale and diversity of real-world data. However, we are still limited to what we can see and observe, collect in the real world, and this can be problematic because everyday driving, especially on the highways, is usually pretty uninteresting for training and testing purposes, right? And we'll also seldom come across safety critical scenarios, but these are sort of precisely the kind of scenarios that we do want to upsample in simulation. And then recently, several papers have studied how we can actually automatically generate realistic scenarios at scale through the use of generative models. So for example, SceneGen here learns an autoregressive model that iteratively inserts actors into the scene. SimNet is another approach that learns a generative adversarial network that predicts a rasterized image of the scene. And then from this rasterized image, you can then extract like a vector-based representation of where the actors are. And then there's been two recent open source simulators called Sledge and Torch Drive End, which make use of diffusion models and normalizing flows respectively in order to generate scenarios from scratch. So the advantage of these approaches is that they're fully data-driven, right? And so the realism and diversity of these scenarios just improves with more data. And at the same time, we no longer rely on handcrafted rules or heuristics, which are not only challenging to develop, but they also limit the scale or diversity and realism of our scenarios. However, the methods presented so far generally have limited controllability, which limits its applicability in use cases where you would want a little bit more precision over the kinds of scenarios you want to generate. For example, if you wanted to generate a ton of structured testing scenarios, right? And in addition, most of the papers we've considered so far generate only the layout of the actors in the scene. But as we've seen, we'd also like to generate other aspects of the scenario, like what is the weather condition? How do we want the other actors to behave, right? What is the goal of the self-driving vehicle or the destination that it wants to reach? So to address this issue of controllability, several recent works have proposed ways to imbue these generative models with more controllability, right? So for example, this first work on the right or left for you guys is scene control, which learns a diffusion model of traffic scenes, and then it uses guidance functions to perturb the sampling process towards samples with high realism and high constraint satisfaction. This allows us to encode or use high-level constraints in order to specify things like how many actors do we want in this scenario, how dense should it be, where should the actors generally be placed, how large and fast they are, or etc. Another approach is RealGen, which first retrieves a set of template scenarios from some external database of real-world scenarios, and then generates novel scenarios that are similar to the template scenarios. More recently, some papers have also taken controllability one step further so that we can control the kinds of scenarios we want to generate through natural language directly, right? So for example, LCT-Gen uses a large language model to generate a structured description of a scenario, and then it uses a generative model that to generate the scenarios themselves, conditional on that structured description. So these are all super exciting directions to improve the controllability of generative models for scenario generation. Yeah. Cool. And now we've discussed various ways to generate scenarios, whether it's through manual specification or using generative models directly. And to ensure that we've adequately tested the self-driving vehicle, we also need to make sure that the scenarios that we generate actually cover what the self-driving vehicle might observe in the real world, right? So in other words, the real world is extremely diverse and complex, and to safely deploy the self-driving vehicle to the real world, we need to ensure that testing covers all the possible scenarios that might occur and characterize the SDV's performance across those scenarios. So therefore, we need a way to generate scenarios that will help us maximize test coverage. And this is challenging because the world is really vast, right, and very long-tailed, and it can be infeasible to test the SDV in sort of the infinite number of configurations of scenarios that can exist. So this motivates the need for a more efficient or intelligent algorithm to help us maximize coverage efficiently and characterize the performance of the SDV efficiently. So there's been a couple papers recently that come out to explore this idea of using intelligent sampling in order to generate scenarios that maximize test coverage. So for example, I'm going to cover this paper called GUARD, which proposes the following pipeline. First, we're going to test the SDV on some random initial scenario, and then we're going to update our estimate of the SDV's performance. So the scenario is shown on your right, and then our estimate of the SDV's performance is shown on your left here. Next, we're going to generate a new scenario and test the SDV on that new scenario. And importantly, the way we test or generate the scenario is we want to find a scenario that maximizes our information gain about how the SDV would perform. And then, let's see. Okay.
Reload it.
Let's reload it. Oh, how about this?
Well, that works.
Cool, that worked. Cool. And then finally, we're going to iteratively repeat this process by generating new scenarios and testing the SDV in new scenarios to both improve our estimate of its performance and to maximize coverage. So importantly, the algorithm here will prioritize scenarios where we are most uncertain about the SDV's performance. So for example, where the decision boundary lies between when the SDV will pass or when it might fail. Cool. And that's it for scenario creation. Next, I'm going to talk about how can we actually simulate the behaviors of the actors in the scenario. And before we get started, like what exactly is actor simulation? So at a high level, we're given a high definition map of the environment, and we're also given the initial states of the scenario, like what we specified earlier. And then what we want to do is simulate the behaviors of the actors in that simulation. So where they will go over time, how they will react to changes in the environment, and how their internal dynamic states might change as well. So we want to do this for every kind of traffic agent that we might see out there in the real world, right? And broadly speaking, we can categorize this into actors with rigid actors like vehicles, motorcyclists, etc., and deformable actors like pedestrians. So in today's session, we're going to primarily focus on how we can simulate the behavior of rigid actors. But note that there's also a vast literature on how we can simulate the behaviors of other actors as well, for example, pedestrians, that we will unfortunately not have time to get into. So now you might be thinking, how does actor simulation differ from other tasks in self-driving? So for example, in motion planning, we also care about learning to drive in the real world. And can we simply use SDV's motion planner to simulate actor behaviors? Well, not quite. In motion planning, our goal is to learn optimal driving behavior. That is, driving behaviors that are safe, efficient, comfortable, and follows traffic rules. And if we use an SDV's motion planner for actor simulation, we'll only train against and test against optimal drivers in simulation. But we know that human drivers in the real world are far from optimal. Human drivers can be frustratingly cautious or recklessly aggressive. And oftentimes their behaviors are irrational, right? And most notably, human drivers rarely abide by any traffic rules at all, right? So in actor simulation, we want to be able to capture the full distribution of human driving behaviors. And this will allow us to expose the self-driving vehicle to the diversity of possible scenarios it might encounter in the real world. And what about motion forecasting? Here, we're also interested in predicting the full distribution of human driving behaviors that we encounter in the real world. Well, there are three key distinctions between motion forecasting and actor simulation. First, in motion forecasting, because it runs as a part of the autonomy stack, it operates on partial and noisy observations coming from sensor data. In contrast, actor simulation, we're given perfect state information from the simulator, right? We also do not know the goals and intentions behind each traffic agent in motion forecasting, but oftentimes the goals and intentions of each actor is known to us and given to us because that's exactly what we want to control. And then perhaps most importantly, motion forecasting is an open loop task. The predictions of the motion forecasting model doesn't directly influence its future inputs. In contrast, actor simulation is a closed loop task where the predictions of the actor simulation model directly influences the future inputs it sees. So any small mispredictions by this model can then compound over time. And as we'll see, what this means is that a simple supervised learning setup is often insufficient to learn good actor simulation models. Okay, so perhaps the simplest way to get started in actor simulation is to just use rules-based behaviors, like the classic IDM model, right? So here we'll leverage classical car following models like IDM or lane change models like Mobile to simulate actor behaviors. And this is actually what's often done in a lot of popular planning simulators like Waymax or Sledge, right? This is a very conceptually simple approach that's really easy to implement. And oftentimes it can give us pretty reasonable results as well, because we can enforce constraints like actors shouldn't collide with each other or their actors shouldn't violate traffic rules, right? But this approach can only really take us so far. The problem with these rules-based approaches is that the rules we use are often far too rigid to simulate realistic human behaviors. So this might be okay if we're just trying to simulate simple lane following behaviors, but we often want to capture the long tail of actor behaviors as well, like complex non-compliant behaviors like cutting corners or illegal U-turns. We want to be able to simulate different kinds of driving styles from cautious to aggressive drivers. And we want to be able to simulate realistic interactions between human drivers, like signaling, right? And simplistic models like IDM just don't allow us to do this. So what exactly do we want from actor simulation? Well, we want our actors to be realistic so that our simulations have low domain gap to the real world. We want them to be diverse so that we can make the self-driving car experience the full diversity of real world driving. And we want them to be controllable so that we can simulate scenarios with specific semantics. And this is really important for upsampling rare long tail scenarios for training and testing the SCB. So it's unscalable for us to handcraft rules in order to simulate all of these behaviors and hit all of these requirements. And a much better solution is to try to learn to simulate these actor behaviors from data directly. So we're going to start by talking about techniques to achieve each of these requirements, starting with realism. So behavior cloning is one approach to this problem. And the high-level idea behind behavior cloning is we're going to first collect an offline data set of state action pairs from human driving demonstrations. And then we're going to use this supervised learning, or we're going to use supervised learning to train a policy that predicts an action's one-step action given its current state. Now, this approach is appealing because it uses a very simple supervised learning setup that we're all familiar with. And we can also readily collect offline data sets for this purpose, simply by just observing how humans drive in the real world, right? This makes it really easy to scale the performance of this method with more data. However, policies trained in this way are well known to suffer from covariate shift, which means that the policies are not robust to out-of-distribution states induced by its own mistakes. So when we unroll these policies in closed-loop simulation, their errors compound, leading to increasingly unrealistic behaviors. So this is a fundamental problem of behavior cloning. And next, we'll take a look at a couple techniques to address this issue. One approach is to simply regularize the policy to avoid getting into these out of distribution states altogether. So for example, we can design losses that encourage the policy to respect traffic rules and avoid out of distribution states like collisions or off-road driving. We can also regularize the policy to stay close to observation states. For example, by learning a probabilistic forward model and then penalizing the policy for taking actions that lead it to states where the forward model was uncertain. So this approach is simple and it minimally changes the behavior cloning setup. And it also allows us to incorporate common sense knowledge about human driving behaviors into the learning process. However, it can be challenging to handcraft good auxiliary losses for this approach. And doing this poorly may add bias to the learning process. For example, by penalizing long tail behaviors that you actually want to capture. And another approach is to use data augmentation to make the policy more robust to out of distribution states. So for example, a clever way is to generate synthetic scenarios by perturbing the actor's trajectory and have it learn to recover from those perturbed states. Another way is to simply perturb the input data with random translations and rotations, right? And again, this approach is simple and minimally changes the behavior cloning setup. However, as with auxiliary losses, we still need to handcraft good data augmentation strategies so that we can expose the policy to out of distribution states that we expect the policy will actually encounter in closed loop simulation. So another solution or a more natural solution to this is to directly train the policy on states it will encounter during closed loop simulation. So to do this, a couple of recent papers propose to unroll the policy through closed loop differentiable simulation, feeding into the policy the states that it predicted or its predicted actions will induce. Then we can simply apply the same behavior cloning loss to minimize the difference between the policy trajectory and the expert trajectory. And this approach directly trains the policy to recover from its own mistakes. That is the other distribution states it will encounter when it gets unrolled in simulation. However, since we don't know how humans would actually, what the humans will actually do in those out of distribution states, we train the policy to only match the original human trajectory only. And this gives us a biased training objective that might ultimately impact realism and diversity. So what if we can query a human for what to do in these out of distribution states? This is the classical approach of the Dagger algorithm, where we iterate between training a new policy on behavior cloning and collecting a new data set by enrolling the policy and querying an expert, interactive expert for action labels. So this approach allows us to supervise a policy with expert actions, even in out of distribution states. However, interactive experts are rarely available. And even when they are, they can be prohibitively expensive to include within the training loop. Finally, instead of querying an interactive expert for action labels, we can also encode a prior knowledge about what constitutes realistic driving into sparse reward functions. And then we can augment the behavior cloning objective with a reinforcement learning objective to supervise a policy in other distribution states. The behavior cloning component allows us to efficiently learn realistic human driving behavior from in-distribution states, whereas the reinforcement learning component allows us to improve robustness to out-of-distribution states. However, this requires us to manually design reward functions and manually trade off between the RL and BC objectives. And if we were to take this idea one step further, instead of manually designing the reward function, we can also learn the reward function from data directly. So one particularly common or popular instantiation of this idea is generative adversarial imitation learning, or GAIL. So here the idea is to learn a discriminator to distinguish between the expert's actions and the actions predicted by the learner policy. And then this discriminator can then be used as a sort of realism award to train the learner policy in closed loop simulation. Conceptually, this idea is really nice, really beautiful. It allows us to train realistic driving policies through closed loop training. However, training such a model is notoriously difficult in practice because of its minimax optimization objective. Okay, so the techniques we've seen so far focused on how do we learn realistic and reactive actor behaviors for simulation. And another critically important aspect is how to capture the full diversity of human behaviors possible in the real world. So let's take a look at some basic approaches to do this next. So one popular approach is to learn hierarchical policies to simulate actor behaviors. So this approach builds on the intuition that human driving is intentional. So by explicitly disentangling the high-level goals of the behavior from its low-level controls, we can potentially learn policies that better cover the main sources of multimodality in human driving. So for example, we can learn policies that model a latent variable indicating the goal of the driver, or we can learn more explicit hierarchies using waypoint goals or route goals to model the most salient sources of diversity in human driving. And this approach allows us to generate diverse multimodal simulations of how a scenario would evolve over time. However, trying to learn this hierarchy in an unsupervised fashion often leads to uninterpretable or entangled latent spaces. And explicitly designing explicit hierarchies can be difficult to get right. So beyond explicit hierarchies, we can also just try to learn generative models to capture multimodal distributions of human driving behaviors. And there's many ways we can do this, whether it's variational autoencoders, as we just seen before, or using diffusion models, as in recent works like CTG and Motion Diffuser, or using autoregressive models over discrete tokens, as in Motion LM and Trajaglish. So we've covered this in a little bit more detail in the prediction session of this talk. So I will just, leave it at this for now. And then finally, another popular approach within the community is to train a zoo of RL agents through self-play. So here the idea is to iteratively introduce actors into the simulation environment with different kinds of incentives and different kinds of capabilities, and then train them against each other in the same environment. And over time, what we'll see is a zoo of diverse actors emerge from this training process, which we can then compose together to create increasingly diverse and complex scenarios. So this is another great way to learn very diverse actor behaviors in closed loop. But one downside of this approach is that it can be challenging to encode human-like driving in reward functions alone. So you really need to be careful about how you design those reward functions. And then last but not least, let's take a look at some ways we can control these actor behaviors. As we discussed earlier, part of what we want to do when we specify scenario is to specify the high-level semantics of how different actors should behave in that scenario. So for example, we might be interested in having an actor cut in aggressively in front of the SDV, or we might want to simulate a traffic jam scenario full of extremely cautious drivers, right? And to do this, we need our actor models to be controllable. So let's take a look at some ways we can do this next. So one way we can do this is to learn goal conditional policies. So here we might want to condition each actor's policy on some driving commands like turn left or turn right, or on waypoint goals specifying where we want the actor to be in the future, or simply as routes along the road network. So these policies allow us to control the what of how actors should behave in a scenario, and conditioning and using this to condition is super simple and interpretable for humans to manipulate. However, these policies often fail to generalize to out of distribution or long tail conditions. And the conditions that we want to control usually needs to be known ahead of time and labeled before we train these models. So besides goals, we'll also want to control the style of the actor. So for example, how aggressive or cautious the actor is. In combination with control over goals that we discussed previously, having control over an actor style would then allow us to create scenarios where an actor would cut in front of the SDV, but with varying levels of aggressiveness, from like very cautious to very aggressive cut-ins. Now, as you can imagine, defining what it means to be aggressive or cautious is really challenging, right? But this really hasn't stopped the community from trying. So we can, there's been a couple ways we can do this. We can define style as sort of the courtesy of an actor, which basically measures how much other actors would need to adjust their behaviors from their nominal behaviors, given my choice of actions. So for example, me cutting in front of another actor is not very courteous, right? Because the other actor will have to potentially hard brake in response to what I'm doing. But if I was to just drive beside that other actor, then this behavior is actually quite courteous because the other actor doesn't really need to adjust its behavior at all to account for what I'm doing. Alternatively, we can also define style using something like social value orientation. And this measures how much an actor prefers to allocate its value to itself versus to other actors. So to illustrate what this means, an egoistic actor, for example, might want to optimize his own gain by being quite aggressive, right? And trying to overtake everyone so that it makes a lot of progress. In contrast, an altruistic actor might be one who would yield to these actors because they want to allow others to optimize their progress instead of their own. Other definitions of style include whether an actor is goal or information seeking, whether an actor is goal or safety oriented, or we can also just try to directly discover latent personalities from data using in an unsupervised manner. With these style-based approaches, we can then control how an actor behaves. However, it is quite difficult to define what these styles should be, and the actor model may generalize poorly to novel styles. Cool. Recently, a couple papers have also explored how to control actor behaviors through specifying a reward function for how we'd like them to behave. So using this reward function, we can then use a variety of different techniques to generate the kinds of scenarios we want. So for example, AVSIM uses black box optimization to optimize a collision-seeking objective, thus generating adversarial actor behaviors that stress tests the SDV. Likewise, Strive is another paper that uses latent space optimization to find realistic adversarial scenarios in the latent space of a latent variable actor model, like for example, a VAE. Other approaches include sampling from diffusion models using guided sampling, or using reinforcement learning to learn actors that maximize the given reward function. So this approach is really flexible in how we can control actor models, and it's also quite conceptually simple. The reward functions are also composable, and so using this approach, we can actually compose various rewards together into ever more complex reward functions to create ever more complex behaviors. However, because a lot of these approaches require optimization in the loop, inference is typically quite slow. And in addition, while reward functions are quite flexible as a specification tool, shaping those reward functions so that they can be easily optimized is very challenging. So finally, we've seen goals, styles, and reward functions as different ways to control an actor model. However, these different approaches are either not very flexible or expressive to all the different kinds of behaviors we want to simulate, or they're kind of tedious to tune in the case of, say, reward function specification, right? And a much more natural interface to control actor models is natural language instead. And in an age of LLMs, implementing this level of controllability may not be very out of reach. So for example, Diffusion ES and CTG++ uses a large language model to convert natural language description of the kind of behaviors that we want to simulate into a reward function or guidance function that we can then use to optimize, or we can use as a part of guided sampling within a diffusion model. Alternatively, we can also convert natural language descriptions into lower level maneuvers like drive straight or turn right, which can then be executed by a lower level maneuver condition policy. These approaches to controlling an actor model is super flexible and super ergonomic for human scenario authors. However, we're definitely still in the early stages in exploring how we can make use of natural language interfaces to control actor models. A lot of the preliminary experiments done in these papers show how natural language can be used to control very simple behaviors, right? But it's unclear how well this would work as we try to use them for more complex behaviors as well, especially in a closed loop simulation setting. So this is definitely a very exciting space that we should closely monitor going forward. And yeah, and that concludes our sort of whirlwind tour of actor simulation. So in summary, we've provided sort of a high-level overview of recent work in actor simulation, focusing in particular on diversity, realism, realism, diversity, and controllability. And hopefully this was helpful in giving you an overview of the problem and maybe some of the open questions that remain. And last but not least, I just wanted to take a step back and see how everything fits in back together within the full closed loop simulation system. So earlier in the previous session, Siva covered different ways we can build this asset library from real world data and how we can simulate sensor data and simulate the vehicle platform and its dynamics as well. In this session, we covered how we can actually generate scenarios that specify the content of the simulation and how we can actually simulate the behaviors of the actors in those scenarios in closed loop so that we can test and train the self-driving vehicle. Yeah, so that's it for the simulation session. Happy to take any questions.
This diagram, actor simulation can also affect sensor simulation. So it could be an error effect.
Yes, that's a great point. So the way we see this is actor simulation will output controls or how actors' states should change over time. And this would actually affect the world state representation there in the middle. So that world state representation is then what's fed into sensor simulation as sort of ground truth for where the actors are, how they look like, and how you should simulate camera or LiDAR given that. Yeah.
Other questions on Zoom?
Oh, yes. Does scene? Oh, yep. There's one question on Zoom. Does scene control generate actor behaviors and future actions, or just the starting scene? I don't know if you can hear me, but just the starting scene. So scene control currently only considers the layout of the actors. But there's some other work, related work out there like LCT Gen, which generates both the actor behaviors as well as their initial layouts from natural language alone. One thing to note about those kinds of models, though, is that they generate these actor behaviors in an open loop fashion. So they give you almost like a template of what they expect the scenario to look like over time, right? But then because when they're generating those behaviors, they don't have the SDB executing in the loop, the actors are actually not reactive to what the SDB is doing. So that's why you might still need something like an actor model in the loop so that you can generate behaviors that actually react to the SDB and yeah. Yeah. Cool.
Oh, there's one more.
Yeah.
Do you have any like intuitions or thoughts on the like this form of simulation compared to the more end-to-end one that like Wave and Tesla and Comma are all trying?
Yeah. Let me see.
Just like the world model video generation.
Yeah.
Repeat the question so it's on.
Yeah. So the question was, do we have any thoughts on how this compares and contrasts against other simulation approaches that leverage world models to directly simulate pixels or sensor data, right? So our approach is definitely a lot more modular than those approaches in the world models. And with this modularity, what that means is we can really control how we want the scenario to play out over time. Yeah, we can really control how we want the scenario to play out over time and really encode our prior knowledge about realistic simulation inside the simulator. So for example, we can use or we can incorporate into our closed loop simulator something like a really realistic vehicle model to simulate how the SDB's actions get translated to its changes in states. Whereas if you were to just use a world model where you condition the conditions you send into it is like accelerate or decelerate, right? Then you don't get that same level of fidelity in your simulations. Additionally, with this approach, because from the scenario perspective, with world models, you really maybe only get high level control over where actors are in the scene. But if you want to be able to really characterize exactly how the SDB would perform over, say, the entire parameter space of a given logical scenario, for example, you would really want precise control of where you place the actors and how exactly those actors behave and respond to the SDB over time. So having this sort of like modular approach allows us to do this. Yeah. Any additional thoughts? No? Yeah.
We had a slide earlier in the simulation section that talked a bit more detail about the pros and cons of world models versus this type of closed loop simulation system. Sorry, I'll stand up. I think like one of the major challenges is that because you implicitly encode the dynamics of the world and the appearance in a single representation, you can sort of hallucinate things that you can't really expect to happen. So the example I gave earlier was that even if you have action conditioning in your world models, if, for example, you have a very dense traffic scene, and then you have your self-driving vehicle for some reason accelerate into this dense traffic scene, currently your world model will just kind of hallucinate and say, oh, this isn't very common in my data distribution. I'm going to make these actors disappear and then just create something more realistic that is very common in my distribution. You can see this like with Sora too. Oftentimes like the scene, as you evolve it over time, it morphs a bit so that it just kind of like, so oh, this looks reasonable. And like on the shorter time scale, it is realistic. But in the longer time scale, you actually can't guarantee the reactive behavior you want with your actors with your self-driving vehicle right now. And it's a bit hard to use that type of model for safety critical testing. I think world models can still be very beneficial for building high quality asset representation and generating like data for like good perception representation learning. But to use it for testing evaluation, where you really want to understand the performance of your system in a very particular scenario and make sure that it's safe, world models are not maybe a good solution for that situation.
Cool. All right, we can continue, let's say in 15 minutes at 5 minutes past 4 with the remaining sessions, which will look at the kinds of maps and map representations that we use as well as localization. And then we will end up with additional time for any leftover questions folks might have. Thank you.
Over there, I guess. Or give me a talk now. You can see that. The data-driven simulation version. I haven't seen it. Me neither.
Yeah, no, go for it. Okay, cool. I think we can get started with maps and localization. So hello, everyone, again. For those of you joining us, my name is Andre. I'm a research scientist at Wabi. And at Wabi, I work on a combination of both sensor simulation research as well as state estimation. And in this session, we will be focusing on the types of maps that we typically use in various components of autonomous driving. All right, so there are essentially two major categories of maps that we typically talk about. Namely, there are topological maps and there are the traditional topological maps, and then these HT maps that you hear of quite frequently. And in this talk, we'll provide a bit of an overview of what these maps are, why they're useful for autonomous driving, and how to create them. So first, we will talk about these classic sparse topological maps. So these topological maps contain multiple different attributes, like the road topology, maybe the number of lanes on a road, on a street segment, and the direction of travel. And they're typically used in two major ways in autonomous driving. So they're used to get an understanding of the potential difficulty of an operational domain or a given geographical area. They might be used for tasks like business analysis to figure out, where it's beneficial to deploy a robotaxi or autonomous trucking. And second, they're also used by the self-driving vehicles themselves, basically for high-level route planning. Basically, this thing can tell you how to get from point A to point B, just like a human would use something like Google Maps or Apple Maps or whatever to navigate from point A to point B in an unknown city. In terms of the data that you can use to assemble these maps, they can be produced from a wide range of data sources. So some approaches, and there's entire companies that work on this sort of stuff, for example, could be cameras that are mounted on dashboards. So aggregating this sort of data from dash cams because it's available at scale. Many drivers have them for insurance purposes, so you can crowdsource data for this purpose. You can also use aerial imagery from, for example, drones, from planes, from satellites, and so on. And of course, you can use your self-driving vehicles, whether it's cars or bipedal robots or trucks or whatever. If you can automate, if you can drive them through your environment ahead of time, you can capture this data and assemble it into maps. Now, as far as these topological maps go, in the industry, you have kind of three different approaches to build these maps. You have a more old school approach that is segmentation followed by heuristics. You have energy-based methods, and then you have fully neural network approaches. One of the most sort of classic ways to do this is segmentation followed by heuristics. And the idea here is essentially, for example, if you're interested in road segmentation, you might perform road pixel binary semantic segmentation on aerial imagery or satellite imagery or whatever. And then you would post-process this information somehow to obtain a road network. So maybe doing some sort of graph extraction. And in terms of strengths for these methods, you can just plug in a lot of state-of-the-art semantic segmentation methods that operate on pixels on top of these methods and then run the post-processing. But in terms of the weaknesses, the fact that you just plug in your semantic segmentation and then post-process it might mean that if there's some failures in segmentation, for example, due to partial occlusion or an unexpected angle in your satellite imagery, it will be difficult for the post-processing to recover. And of course, you're also dependent on whatever post-processing algorithm you designed, which might prove to be brittle. So rather than using segmentation that is followed by some sort of heuristic to get the road network, another family of work instead uses more principled approach, where you formulate the problem of road topology extraction as some sort of energy optimization task, possibly with neural network components. And the nice thing about this is that you can encode and optimize things in a structured manner, both semantically as well as geometrically. And in this example of paper, a method was developed that started with OpenStreetMap data namely center lines, and then they were updated with precise road width information by doing inference in a Markov random field. So the idea here was that you would have an energy term using cues like the road segmentation mask, as well as image edges that you obtain from aerial imagery. And you would combine this with human-generated priors like the smoothness and consistency for the road boundaries, the road width. And this let you kind of have a joint optimization objective that had both sort of the neural network semantics as well as priors about the human encoded desirable characteristics of the map. And while mathematically this is more structured, these methods still rely on some handcrafted features and may fail to produce the fidelity and the precision that you require for tasks like automated driving. Now, a learning-based neural network approach for obtaining the road topology can help alleviate some of the limitations of these hybrid approaches. So in more recent papers, methods have used things like recurrent or graph neural networks to directly predict the road topology as a graph rather than having some sort of energy-based method where you use traditional semantic segmentation and some graph extraction. So for example, in this paper by Li et al., they use an RNN approach that iteratively produces the next vertex when you're drawing some sort of lane graph. And they can also use the same model, for example, for related tasks like building footprint estimation, like coming up with contours for buildings that you get in satellite imagery, which is very useful for remote sensing, for map building, stuff like that. And then another approach that we also have on this slide, follow-up work basically did something similar, but with graph neural networks to extract building footprints, which had the benefit that unlike the RNN, you could actually reason about the whole graph jointly, which meant that you no longer relied on a step-by-step inference process for the RNN, which made the network both easier to train as well as faster, just more efficient at inference time, which managed to approach some of these limitations of RNNs. And one cool thing about these graph learning methods is that these new methods are powerful enough to allow actually sampling from the distribution of maps. So we have here an example from a recent paper from NVIDIA called Neural Turtle Graphics, which lets you synthesize new and realistic road graphs from learned priors conditioned on the name of a city. So you can tell it to generate something that looks more like Manhattan or more like Paris, etc., and it will generate feasible maps. So this has applications in many parts of simulation, for example. I'm just going to show this again because it's pretty interesting. Okay. Moving on. Okay, so now let's talk about the second category, which is HD maps. So HD maps contain both the detailed geometric information at a structured level, as well as semantics of the environment. And you typically use them for a wide range of tasks in autonomous driving. You use them for precise localization of the self-driving vehicle. You use them for providing additional prior knowledge for the autonomy system. And perhaps more importantly, you also use them for simulation. So often you will have a component of them that lets you do things like novel view synthesis or LiDAR simulation or stuff like that. So before we talk about the HD maps themselves in more detail, we should highlight the key properties. Oh, sorry. Anyway, we need to highlight the key properties that we want from these HD maps, right? So the most important things that we want from these HD maps is we want them to support very large scales, often encompassing entire cities, and to be globally consistent. And while in some applications you might have multiple passes over the same area that are required for building the maps, ideally we would like to reduce the number of passes through an environment before building these maps in order to reduce costs. We also want the ability to store the maps as efficiently as possible for ease of deployment and updates and so on. And we also want the maps to only contain the permanent elements of the world, so no dynamic traces that will interfere with other tasks like simulation and localization later on. So how do we actually build these HD maps? Well, building HD maps can be grouped into four big steps. So in the first steps, we want to select the operational domain in which we're interested and for which we want to build the maps. We then collect the data. And then we process this raw data to build the geometric maps that contain the 3D information. And then finally, we conduct some sort of labeling to add semantics to these HD maps using human annotations, AI models, or a combination thereof, like hybrid approaches. And depending on the application, we might then simply discard the 3D resulting geometry as a byproduct, or you also keep this, for example, if you want to do simulation. So let's begin by talking a little bit about how we built these geometric HD maps. So once we have this data, the idea is that we want to split it into small chunks and fit trajectories to these individual chunks. And this is beneficial because it can be produced if it can be done in parallel. And then once you have these tiles that have been optimized, you can then align all of these trajectories in a joint optimization process, like some sort of large-scale Postgraph optimization. And last but not least, you assemble these chunks and the raw data into a globally consistent map. So let's now briefly talk about simultaneous localization and mapping, or SLAM, and how it fits into this system. Okay. So SLAM is an important technology to jointly estimate the trajectory in the 3D map. And without going into the details, which could take up an entire graduate course, let alone a 30-minute tutorial, some of the main benefits of simultaneous localization and mapping is that it can be used to build large-scale, high-definition, high-resolution maps. It also enables navigation in completely unknown areas without any prior maps, because it localizes while also iteratively building and refining a map of that area. And another nice thing is that there are very robust, mature software solutions already available for multi-sensor SLAM that can be integrated into production systems. And of course, SLAM as its own field has a lot of applications beyond autonomous driving, for example, in augmented and virtual reality. We might also want to handle asynchronous sensors for a reconstruction system. So autonomous vehicles are often equipped with multiple cameras, which is necessary, for example, to cover the entire surrounding environment. And many existing multi-view SLAM systems often assume that multiple cameras also fire at the same time in each frame. But in practice, the multiple cameras that you have could be asynchronous with respect to each other due to technical limitations or by design. So for example, the cameras might actually be synchronized with the spinning LiDAR so that they fire as the LiDAR kind of sweeps through the scene. And this is actually a common setup in many autonomous driving data sets. So to tackle this problem, there's papers like Spline Fusion and Asynchronous Multi-View SLAM, which formulate a more generic SLAM framework, where you no longer model the frames as individual poses, but rather have a continuous time parametrization for your trajectory. And then you optimize this spline-based or Gaussian process-based or whatever trajectory parametrization instead. And this lets you asynchronously fuse different modalities, not just multiple cameras, but cameras and radars and LiDARs and inertial measurement units, etc. And of course, not everything should be in the map. Dynamic objects should typically be removed. So you typically run a semantic segmentation or at least some sort of object detection offboard on the geometric data you assemble to remove this sort of stuff before you build the final maps. So now let's talk a little bit about how you actually generate the semantic elements of these maps. On top of the geometry, like I mentioned earlier, HD maps contain a lot of different kinds of rich semantic information, like the precise locations of lanes and road boundaries, things like crosswalks, intersections, as well as potentially more abstract information like traffic light to lane associations or whatever the rest of the system might need in some cases. But of course, there are some challenges to adding this kind of information to HD maps. So first, the maps change all the time due to, for example, construction. You need to keep expanding your operational domain and so on. It's also common to require multiple passes through the same area in order to build these accurate, dense geometric representations, for example, because of occluders. And last but not least, relying on human annotators to hand label the location and attributes of all of these semantic elements can be very labor intensive and cost a lot of money. So what we actually want is a way to infer this information in a manner that is fast, that is robust, and that is as automated as possible in order to get all of these, in order to overcome all of these challenges. So one cool thing about this is that we can actually combine humans and robots in this inference process, and humans are still left in the inference loop because they are required because of the fidelity requirements necessary for these HD maps, namely at the centimeter level of precision. So typically speaking, the centimeter level precision that we're interested in is often beyond the current capabilities of machine vision alone. And generally speaking, in order to reduce these costs, we want approaches where machines and humans can collaborate to actually minimize the total number of dollars spent to build a map. And in the next few slides, we will showcase some works that can generate various components of these HD maps in a way which is amenable to human-in-the-loop workflows. So let's start with road boundaries, as we see here. Knowing where the road boundaries are, that is delineating the separation of the drivable surface of the road and the sidewalks, is a crucial aspect for safety and navigation. And the industry baseline is typically to have human annotators draw these boundaries from scratch as part of the HD map production process. But as we highlighted earlier, this can be a very expensive task because we need to annotate entire cities and potentially keep updating these maps. So this is not scalable. And in addition to this initial human annotation process, there's also a need for multiple quality assurance rounds to make sure that the polylines are correct and precise and there's no mistakes. So the question is, can we automate this process so that human labelers only need to do the quality assurance process and quickly and easily adjust incorrect predictions rather than annotating everything from scratch? So in order to tackle this, we need model outputs that are easily editable for humans. So this is why we are very interested in directly outputting polygons or graph structures in general from mapping models rather than pixels, because this matches the final representation that we want to encode the maps under. And it's also easier for the humans to adjust than the raw pixels. Humans can very easily have an interface where they can quickly delete a map vertex or move it around if a model makes a mistake, which is much more efficient than drawing everything from scratch. Okay. So in the previous section, we saw a few methods for computing road networks and their boundaries. And now we want to estimate something that is even more fine-grained. We want to estimate the boundaries of all the lanes, not just the road or not just the center line. So this problem can essentially be formulated as discovery first, and then inference in a directed acyclic graphical model or a DAG, where here the nodes essentially correspond to geometric and topological attributes. So more specifically, given a temporally aggregated point cloud that is projected in a bird's eye view BEV image, we aim to find the best DAG that could describe this road network. Now, the space of possible graphs is, of course, gigantic. So the idea here is to do some greedy methods to instead greedily construct a graph and then use basically a neural network to predict iteratively what the next node of this graph and its topological properties are. So to make this a bit more clear, we can look at the steps of this inference process on the top. So in the first box on the top, we can assume that we already have the inferred DAG that you see at the current timestamp. And then in the second one, we find the direction where we expect the next vertex. And this is highlighted by the yellow box. And then we infer the position of this vertex within this RY and then predict its state. So in this case, we find the coordinate of the vertex that we want, that a human would draw, and then we predict correctly that it is a fork. So the idea is that at this fork, we now continue drawing, as you can see in the image below. And once we finish the current polyline, we remember that we had this fork, and then we go back to it and then essentially do this whole process until we run out of sort of graph nodes to process. Kind of in a, we just grow this tree until we are done with every single branch. And in this video, we can showcase that a model like this can draw boundaries incrementally on road imagery. And it does so kind of like a human. And it can deal with a lot of complex lane topologies, so not just boring straight highway roads, but also forks, merges, and intersections. And in slightly similar, but a little different still direction, instead of lane boundaries, other lines of work aim to extract the graph of lane segment center lines instead. For example, centerline det creates a global map of center lines by first predicting the lane centerline segmentation masks, and then using transformers to iteratively predict the vertices of the center lines, one vertex at a time. And of course, some of these models and the citations that will be easier to see in the recording are just a few examples, because this field is very, very big and it's constantly evolving. So there's constantly new papers that come out that improve the techniques over the previous ones. Okay, so let's now switch gears a little bit away from building these maps offline and look at ways to do mapping online instead. Now, online mapping is a must for safety because maps are, of course, not always up to date, and localization can fail, or we might not have maps at all to begin with. And mapping every area can be expensive, and updating it every time there's a change can also be extremely expensive and difficult to scale. So in some of these cases, it's important to be able to produce the map online as you're driving through an area that you recognize is currently unsupported. Construction alone can change the world in a huge number of ways, as we can see in these pictures, where construction might close a road off completely, it might close off a lane, it might move a lane, and do another 1 million different things to change the way you have to drive. And of course, online mapping comes with its own set of challenges on top of traditional offline mapping. Namely, occlusion is a big concern because mapping elements can often be occluded by objects in the scene like vehicles and pedestrians. But of course, unlike offline mapping, here we have much less information to work with. Online mapping, of course, can only detect elements that are within the range of your onboard sensors. Again, you don't have the luxury of aggregating hours and hours of data and chunking it very nicely, so you always have very dense data. Of course, construction elements and construction vehicles can alter how the map is interpreted, so where the lanes should actually go. So figuring out where all of these elements are and making sure you don't miss them is also very important. And of course, for autonomous driving, it's important that the software runs efficiently, because now you're no longer running your mapping software off-board in some cluster. It's actually running as a node as part of your robotic system. So it must be able to run in real time or very close to real time to react to these changes. And of course, last but not least, you have to be able to create consistent maps over time as you're driving, which is very challenging because, again, you don't have the luxury of waiting until you have all the data and processing it nicely at once. You have to be able to process this as you're getting observations incrementally. So one way to tackle this earlier on was to do 2D lane detection. So detecting the lanes in the camera image. This is like a classic example of a task that you do in autonomous driving. So these approaches typically use some sort of deep learning to segment the lane boundary pixels in 2D, and then clustering them into individual lanes, and then fitting some sort of primitive to a lane, maybe like a spline. And it's important to point out here that doing precise lane detection in 2D does not necessarily mean that these lanes will look good or make a lot of sense in 3D, which is actually the space that we're interested in driving in and planning in. So an example in the image here is that we can show that we predict the probability of a lane boundary in 2D and cluster it in 2D. That's what the color coding means. And then we reproject these probabilities into an overhead view, right? The reprojection is the third image. And for comparison, you also see the sort of unprojected camera image as well. And you can see that although the lane detections look very good in the camera image, the probability output actually becomes pretty diffuse as the image as the distance increases. And then these detected lane boundaries conversely also become less accurate in 3D. They become kind of blurry and wide as you move farther away from the position of the camera, even though the physical distance isn't that long. It's like maybe, I don't know, 50 or 100 meters. So instead, the idea is to reason about the lane structure directly in 3D, because that's the space that we are interested in planning. And actually, as we will see, a lot of the modern approaches to do this, whether it's camera and LiDAR, single camera, multi-camera, the modern methods pretty much all do it like this for this reason. So like I mentioned, there's a ton of papers that approach this. One example being, for example, 3D LaneNet, which applies inverse perspective transformations, to deep features. Starting with a single image and then predicts center lines and lane boundaries directly in 3D. Of course, it's beneficial to be able to process multiple cameras at once. Spoilers. So in the context of online mapping, you can definitely and should use multiple cameras as well. And in this example, we're looking at the paper called Lift, Splat, Shoot, also from NVIDIA, where camera imagery from multiple views is fused to predict the top-down bird's eye view segmentation of all mapping elements. And the idea being that in the first stage of the model, each image is kind of lifted from its local image feature plane that is two-dimensional into a 3D frame that is shared across all the cameras. And this is done kind of in a soft way because you don't have explicit depth information. And then in the splatting stage, essentially, you fuse all of these uncertain features using a point pillars architecture to convert them essentially into this top-down bird's eye view segmentation that includes the lanes, drivable areas, and other stuff you might be interested in when doing driving. And this means that you can produce outputs like this, which look pretty good, and they jointly reason about the map itself as well as about the dynamic objects that you see in the environment. And it processes 6 cameras at the same time. Okay, then you have HDMapNet that similarly maps this deep perspective features from surround cameras through an MLP into a bird's eye view. And then you fuse them with deep LiDAR features. So now you're also adding LiDAR to also output a semantic segmentation map, instance embedding, and a direction map. And then you post-process these features into vectorized outputs for lane and road boundaries, crosswalks, that sort of stuff. So you have the network output some intermediate outputs that are then post-processed into vectorized ones. And the results look pretty good in practice, where the method, again, can reason about where the curbs are online, where the lane lines, et cetera, are, as well as potentially dynamic objects, as you'll see in the intersections. Actually, no, I think that might be, I think it doesn't, yeah, it only does the map elements, and the rest is just what you see in the LiDAR. So you'd need this in addition to a perception system. And the nice thing about this is that you can also accumulate these single frame predictions now that you have them consistent, and fuse them temporally in order to create pretty large scale maps all online. Another recent paper is a line of work which goes one step further. And here you train a network to actually directly extract structured vector graphs from the online camera data alone. So you're no longer reliant in these approaches on a custom post-processing algorithm. Yeah, and then Map Tracker as well. This is yet another paper that produces really nice, consistent results, all in real time and all in a way which can be aggregated over time. And the nice thing about these maps, again, is that they are topological. It basically outputs graphs. Sorry about that. It basically outputs graphs, which can then be very effectively both stored as well as used in downstream tasks like your planner or your perception system, et cetera. And of course, mapping is just a means to an end, right? You'd like to learn representations that are ideally optimal for the task of driving. And here, MP3 is an end-to-end network which tackles this very task. And the name, which you've probably also seen in the perception section, it stands for mapping, perceiving, predicting, and planning. And the idea here is that it is able to integrate an online mapping component to jointly do this together with prediction and perception and plan accordingly to run successfully in closed loop. And it can do this without any reliance on prior maps. So to summarize, we discussed these two big categories of maps that can be used in self-driving, namely topological maps and HD maps, and showcased how to build them using algorithms where humans and machines can collaborate effectively in order to reduce the total cost. Finally, we also looked at several approaches for online mapping and how they can be used to reduce the reliance on existing maps. And with this, we reached the end of the mapping section. The next one will be the localization one, where we will look about how to actually figure out the position of the vehicle into a pre-built maps, which is actually necessary in order to allow autonomy to leverage the information that is stored in the map. So we have a few minutes for more questions, and then we can continue. Thank you. All right, any questions? There's no questions on online. Any questions here? Yes?
So in the beginning of this presentation, you mentioned collecting camera data from a bunch of different sources, right? So do you use all that data to then stitch up a map, like a 3D map, or is that how it works?
Yeah, that's a very good question. So there's some information. I think there's companies that do this. I don't have a lot of details, but there's multiple ways in which you can crowdsource this kind of data. So you can collect the raw data and then run structure from motion or some sort of system like this, maybe combined with GPS tracks in order to build the map models like that. Although in that case, privacy is an important concern because depending on where you're collecting this data from and user preference, you might not be able, or you shouldn't just directly stream absolutely everything from the dash cam. It might not be legally allowed. One way to tackle this, I've seen where I think some automakers, what they do is they actually they basically do online mapping, and then they upload this output. Like, for example, those vectorized outputs that you saw, only that gets uploaded with GPS tracks and everything. So that basically, because you're only extracting lane lines and whatever, personally identifiable information is just completely excluded by design. So then you get these chunks of vectorized maps from your fleet or whatever, your cars, as they're driving to an environment, and then you can aggregate this data on the cloud and then redistribute it once you kind of filter it so it's nice and consistent. And this can let you, because it's vectorized, it can actually let you do things very efficiently and do over-the-air updates.
So you're mostly responsible for collecting the crowdsourced data. Is that it? Or do you do anything?
Yeah, I'm not sure. I think I've seen some papers from some OEMs. I'm not entirely sure. I remember might have been Daimler, but don't quote me on that one, where they talked about a system like this. I don't know exactly what kind of post-processing they do, but that's the idea. You have these lightweight semantic elements that get uploaded, and then you still need to align the information from the various sources that you get and kind of filter out noise and all that stuff. And then once you post-process it, you clean it up. Maybe you have human QA, and then you update the maps that are in your fleet. That's one way to do it. Right.
You mentioned privacy. What's your strategy probably around clinics, military bases, where you're not supposed to collect data?
I can't give any specifics because I'm not an expert. I don't know, but there are people who are in charge of things like safety and certification and operations and all the legal permits. So they are the ones who are in charge of sorting this out. But yes, I agree. This is, there's like entire positions at companies like Waabi and related that are only tasked with this because it's something where special care needs to be taken. Of course, there's special permits you need to get when you're testing vehicles, even with a driver behind the wheel. So there are very talented people that are much smarter than I am that are taking good care of this sort of stuff. I don't know that much about the regulations. Okay, one more question.
We mentioned all the images, cameras, and also mentioned LiDARs. Are there anything else?
Yeah. Yeah, I mean, indirectly, you probably also use GPS and GNSS trajectories for the localization aspect, as we will see in the next slide deck. You can also build maps with radar. They have the advantage of, they're a little trickier to build and to remove the noise before you accumulate the data, but then you have the benefit of basically having maps that are kind of by design more resilient to weather conditions and just fog and stuff like this that you can then localize to. But it's also a function of whether, if you want to do human annotation and human QA, and you're interested in validating that your lane lines make sense and stuff, it's more difficult for humans to validate like radar data, like lane lines and stuff aren't really visible, whereas lidar intensity and cameras are more straightforward to validate by experts.
The expense, how much money such sensors will cost, such sensors will end up being on such cars.
Yeah, and of course you can also do it cross-modally. So there are some papers that build maps with LiDAR and then use cameras or more inexpensive radars to match against the fancy LiDAR maps as well. So you can potentially have like a mapping fleet with more expensive sensors, and then the production line cars that you might sell with assisted driving or whatever, they're using more inexpensive sensors, but still leverage these HD maps. Yeah, of course.
Sensor end up building more accurate. Something like LiDAR is barely, feasible is barely.
Yeah, that's a very good question. So the question was, which sensor leads to the most accurate maps? I think it's more a question of shifting computation almost. So I think you can build really, really accurate maps with all sorts of sensors, including relatively low-end cameras. It's just that you need to do more work, more heavy lifting algorithmically, and spend more time, for example, maybe training a foundation model to learn meaningful depth priors and stuff like this. Whereas with the LiDAR, as long as you have the initial calibration, you can kind of just drive around and run an off-the-shelf LiDAR slam on it, and you'll have like a really nice map typically. But of course, then your algorithmic costs are lower, but then your sensing costs are higher. So it's about finding the right balance. Okay, cool. So let's move towards the final session, which is localization. And then we will have any bonus time for questions. Let's go for it. Okay, so no, this is not the right button. This is the right button. Okay. So we've basically seen the importance of HD maps and what information is encoded within. We saw in the perception section, for example, that you can use HD map information as an additional sort of source of input for your perception or motion forecasting or motion planning model. But it's important to realize that in order for HD maps to be usable, you need to know the location of the SDV within these maps. And in order to figure out your location within one of these HD maps, you need to localize. So this is why you need to perform localization. We'll begin this talk by essentially specifying more precisely what localization is, how it is typically approached, and why it is challenging. We'll then talk about how to quantify how good a localizer is and how to compute localization ground truth, because it's a little different from, for example, perception. Then we'll discuss localization at the systems level, and we will try to understand how accurate localization actually needs to be. And after this, we'll talk, of course, about some methods covering the two major families of localization, namely online localizers and global localizers. So in terms of the problem statement, given a sensor observation and a pre-built map, the goal of localization is to infer the location of the robot within the map. And here we focus explicitly on map-based localization, that is localizing within prior maps, since, like I said before, this is what we need in order to leverage the HD maps that we talked about previously. More formally, we wish to model the robot's belief over its state space, where for localization, really the state space is its pose in the world. Of course, states are more complex. The more actuation you have a humanoid robot or anything like that, the state is much more complex. But here we can afford to simplify it to, at the simplest case, like X and Y, latitude and longitude. If you want, you can add like height, rotation, and all that stuff. And then you condition this on the past states, as well as the current and past observations. And then you typically denote something like the map with something like M. And this is whatever information is in your map. And we will see some examples soon. So what sensors can you use to actually localize? Well, the most obvious one would be something like the Global Navigation Satellite System, GNSS, as a common source of input. And you often use GNSS for computing the initial pose estimate for global localization. And then you refine this with some sort of algorithm that uses cameras or LiDAR. And then you have IMUs, inertial measurement units, and wheel speed sensors or wheel encoders that you can also leverage as additional cues because they provide additional information that is complementary to the stuff that the kinds of cues that you get from cameras and LiDARs. Now, there's a wide range of representations that can be used to localize against. So these are just a few examples. So of course, in the previous section, we saw how HD maps can be built and annotated with information like lane boundaries, lane center lines, and whatever. And of course, these kinds of maps can also be used for localization, right? You can detect your center line online, you can detect signs and whatever, and then match them to whatever you know is in the map. And of course, coarser topological maps like OpenStreetMap data can also be used, but they're a little less accurate in terms of localization. You may also use the 3D geometric models that we saw earlier. They can be represented as some sort of dense point cloud or a sparse point cloud, circles, any kind of 3D primitives, even Gaussian splats. And of course, the recent rise of implicit neural representations for neural rendering tasks has also made them a prime candidate to explore for localization and related tasks. So specifically, it is actually possible to register novel camera images incrementally into an existing trained NeRF. And of course, simple occupancy 2D maps can be used, and you often represent them as some sort of top-down view of the world. And these maps can also contain additional attributes per pixel, like the LiDAR intensity, the color, some sort of semantics. And they have the advantage of encoding rich information about the structure of the world, while also being easier to store than other representations. Fundamentally, you're storing, tiled imagery data, which can be compressed. There's really good software support for this sort of stuff, etc. Now, the main characteristics we would like from a self-localization system that is running at scale is we want to have low costs because we typically want to map very large areas very quickly. We want the ability to localize in real time. We want the ability to localize with high accuracy, ideally in the centimeter level. And of course, we want robustness, that is the capacity to identify and recover from failures. Of course, there are many challenges that we need to overcome in order to do this. We need to be able to have robustness to the presence of distractors, occluders, because these dynamic objects are irrelevant for localization. We want to be able to have robustness to these geometrically degenerate areas, which have no distinct geometry cues. And these can be particularly challenging for things like pure geometry localization systems. For example, if you rely too much on the iterative closest point ICP algorithm. Sensor noise, of course, also affects all sensors in different ways. Multipath effects can affect both GPS and LiDAR and cause difficulties localizing. And last but certainly not least, environment changes like construction, right, mean that localizers must be able to adapt to cases where maps become outdated. So now that we know what properties we want for our localization system, how do we actually know that we've achieved them? Well, this is why we need to use metrics and ground truth to measure them. It's impossible, right, to develop methods for image classification and object detection and the latest advances in natural language processing without well-established, well-understood metrics that are shared by the whole community. And of course, this also applies to localization. Now, all of localization basically happens, all of autonomy basically happens downstream from localization. So any issues with localization may lead to problems in modules like the object detection that uses the HD map, motion forecasting, your own motion planning, and so on. So we need to pay special attention to these components when we're studying localization. We're going to cover some of these metrics in the coming slides, and later we'll also look at the possible methodology for quantifying the impact of localization errors on the downstream tasks. Now, absolute trajectory error, or ATE, is one of the most common localization metrics. And given n poses that are computed by your localizer and then n ground truth poses, ATE, to simplify things, basically just computes this pairwise error at every time and aggregates this information over an entire sequence of data. So for example, in this illustration, we have one ground truth trajectory in black and the candidate trajectory in blue. And then for every of these n time steps, you can basically just draw a red line between the estimated pose and the ground truth pose. And this symbolizes the absolute error at that time. And then, of course, each of these n residuals, you can decompose as you wish into rotation and translation and analyze the components individually. So if you have a car that's driving through a city, your translation error can be decomposed into X, Y, and Z. And maybe you have to focus on the X and Y because they're more important for safety, because Z, which in this case would be height, is not that meaningful because we can always just assume that the car is on the surface of the road. Otherwise, you have much bigger problems. In terms of failure rate, this is an important thing in order to reason about the actual failure cases. Because you compute ATE, and this gives you a time series over various errors. So what can you actually do with this information? Well, one starting point for ATE is to compute statistics like the mean or the median or whatever. And again, you can express these in the vehicle relative frame. So you can have like a long road and a crossroad errors. You can have your yaw, pitch, and roll errors. But these statistical errors like the mean error or whatever don't tell you that much about the robustness of the system. One other approach is to look at where each error exceeds a certain threshold. And this way you can catch all instances where localization is bad enough to potentially affect the downstream parts of the system, like for example, motion planning of the self-driving car, or harm user experience in an augmented reality app. If everything is like a little bit off, it's not so bad, but if there's like a jump in your augmented reality world, then it's going to look really jarring. So we can discuss a little bit later. We're going to talk about how to actually set this threshold. But for now, we can look at an example where we're given this threshold. And we can look at this signed localization error for some localizer that you might be analyzing. And in this case, the plot says that it's vehicle relative X error. So it's a long road error in this convention. So if we look at this, we can identify two peaks. And these peaks basically say that the localizer has a problem in these two areas. And these are basically the areas where we should focus our investigation for our improvements. And fixing these errors will likely not improve the mean error for your localization system that much, but it will definitely improve the overall performance of the system because it will fix these nasty jumps. So just to recap, we saw that ATE is a versatile metric, but it is important to think about once you have the time series, what you do with it. But we also made a few assumptions about our setting. So we assume that the poses are synchronized temporally. Namely, we have these n ground truth poses and these n candidate poses, and we just assumed that we have n of each and they are at exactly the same time step. And if this is not true, then you might need to reparameterize your trajectory, or you might need to perform some sort of interpolation. We also assume that there are no compounding errors. There's no compounding drift. So if you're doing actual pure simultaneous localization and mapping or SLAM, this will not hold. And in that case, you might need to look into using something like relative pose error in order to deal with different coordinate systems. So all the metrics that we saw so far for localization require some sort of reference ground truth trajectory. But the question is, where does this kind of trajectory actually come from? These are, localization ground truth is something that is kind of difficult for humans to label because it's not really feasible to have a human look at data and draw a trajectory through 3D. So there are some other approaches to do this that are a little different from something like object detection or even motion forecasting. One of the most common ways is to have a motion capture system, which is basically a controlled environment where you use trackers to track the motion of a camera or a robot or a drone or whatever. And this can be extremely accurate, but the scale is somewhat limited. Maybe a few meters by a few meters. And these systems are typically pretty expensive to set up. One other option is to post-process GPS and IMU trajectories in batch. And this can actually be easy to set up because if you're deploying robots in the field and you have some sort of GNSS provider, maybe you're using an OXTS unit or a Novatel unit that has this fancy RTK system, they actually provide software where you kind of just give them the raw data you recorded and it spits out a pretty decent trajectory. And now, of course, this will not work if GPS was completely unavailable and the costs are higher than consumer-grade GPS, but it is a pretty good starting point. And of course, kind of the gold standard here is to jointly estimate the trajectory and the map it using some sort of offline large-scale SLAM system. And this can typically produce the best results in the widest range of environments. But compared to the other options, this actually requires a fair bit of engineering work to actually implement this, make sure it works correctly and scale it. But the good news is that depending on the sensor setup that you have, if you're, for example, using LiDARs and cameras and IMUs, there's pretty good solutions that are available off the shelf that you can use as a starting point, and they have permissive licenses. One other thing that is worth pointing out is that the strategy that you use to compute the ground truth information is itself kind of important for the task at hand. So even just more broadly speaking, philosophically, ground truth is an elusive term. And the way we estimate the ground truth could bias our metrics in favor of certain methods, even when one method might not necessarily be better than the other. So if you're interested in learning more about this, there's this ICCV 2021 paper, which looks at this in a lot of detail. I think it's very interesting. Basically, they show that depending on how you define and compute the ground truth for a particular benchmark, the state-of-the-art ranking of a bunch of methods just gets completely jumbled around, which is pretty interesting. There's also a lot of potential localization and SLAM datasets to consider that you would like to evaluate on. So, of course, the dataset section had more, the data mining section that we had, the tutorial has way more references on this, but just to summarize, a lot of recent papers, they evaluate on, of course, KITTI and its various subcomponents like the KITTI odometry benchmark or the semantic KITTI raw sequences, whatever. There's also a data set called Boreas, which is from the University of Toronto, from a different lab than the one I was in. But it's really cool because they actually recorded data with a lot of emphasis on adverse weather conditions. And it has really nice cameras as well, repeated traversals, and quite a lot of data. There's also the Aurora multi-sensor dataset, aka PIT30M, and its asynchronous multi-view SLAM or AMV SLAM subset, which is a very, very large dataset. We actually have a preview of it here below. It has like multiple cameras that are all full HD, a LiDAR, as well as a lot of metadata, which can be very beneficial for tasks like relocalization. And of course, the famous Oxford robot car dataset is also a really cool way of exploring localization. It has a lot of repeated traversals through the world. It has a lot of interesting sensors, including RTK ground truth and radar. And there's rapid motion, there's motion blur, and so on. So there's a lot of challenges to overcome, especially if you're interested in long-term localization, for instance. Okay. So we looked at the data sets, and we looked at how to measure how good localization is. We looked at what kind of ground truth we have and how different sources of ground truth work. But we still haven't answered one important question, which is how good do we actually need localization to be? A lot of the metrics that we saw so far were primarily in terms of minimizing the ego trajectory estimation error. But in autonomous driving, and really a lot of these autonomous mobile robots, we primarily care about the end task of the system, which can be, safely and comfortably transporting a passenger or freight from point A to point B, or delivering a package with a small delivery robot, and so on. So the idea is that a lot of these metrics are primarily motion planning metrics. So how can we actually evaluate motion planning and figure out its issues as a function of localization error? All autonomy systems which leverage maps need to, at a certain point, fuse the information from the sensor data and the information from the prior map. And for example, many architectures might have a little backbone that embeds the voxelized LiDAR, and then a separate backbone that embeds the map at the current location. And the resulting features are then at some point aggregated, for example, with element-wise addition or some sort of masking or concatenation in the channel dimension. It really doesn't matter. And then outputs like detection, motion prediction, cost estimation for your motion planner get derived based on this fused feature volume. But if our localization is off, then these separate embedding branches will work fine on their own, but then the aggregation will be off. So the question is, what is the impact of this misalignment when it occurs on the overall system performance? Or more specifically, how do localization errors actually map into autonomy errors? How big does a localization error need to be before we start getting issues with our motion planner? So we studied this in our lab a couple of years ago in a 2021 paper. And while this is by no means a full definitive analysis, it can still give us a bit of a sense of how sensitive autonomy is to things like localization errors, while also hopefully acting as a foundation for future analysis. The idea here was that we looked at a large test set for an already trained joint perception and prediction model that was trained with perfect pose, this perfect map alignment. And then we started looking at perturbing the poses in translation and rotation and analyzed various autonomy metrics as a function of this perturbation's magnitude. So we looked at detection metrics first, namely the mean average precision. And we saw that essentially as we increased the max translation error from left to right, the metrics started getting worse, but actually not by a lot. And it was much more sensitive to rotational errors, which does make sense because, you know, a rotation can cause increasing misalignment the farther you are from the ego. But it was still interesting to see how little, for example, the MAP would go down with even like half a meter of inaccuracy. We looked at motion forecasting metrics as well, where the trend was pretty similar. And on the bottom row, we looked at motion planning metrics as well, namely the planned collision and the difference from the ground truth human trajectory. And we saw very similar trends. So this can give us a sense of what it means for localization to be good enough or not good enough. Okay, so now that we've established how to measure the goodness of localization and how to think about how good it needs to be, let's look at some actual ways of performing localization. So we'll first draw our attention to online localization models and then look at global localization. So the idea behind online localization is that at each time step, basically you assume you're given a good guess for the initial pose, and then you only need to refine it by a relatively small amount, which basically lets us localize with very high precision without having the need for a large computational budget. And one common element in all of these localization methods is the need to encode observations, to model observations somehow. And observations can take a very wide range of forms, ranging from just direct LiDAR readings to the output of a neural network. And for the scope of this tutorial, we'll very coarsely group them into 4 major categories, which includes geometric alignment, semantic matching, LiDAR reflectance matching, and camera to LiDAR alignment. But this is by no means an exhaustive list. So let's look at some of these approaches in a bit more detail. So semantic matching, which I hinted at in the past, basically means you're not using any additional localization-specific map, and you're just localizing against the semantic layer of the HD map that you want to use anyway. So here you're using stuff like lane lines, signs, maybe the type of road, the shape of the road, and stuff like this. All of this information being stuff that you can then also store in a vector map. And at runtime, the vehicle must recognize these elements and match them against the vector map to localize. You can use like 2D registration, you can use some sort of template matching. There's a lot of ways to do this in practice. But due to the sparsity of the cues, these approaches are not always able to achieve centimeter level or even meter level accuracy, and often struggle in areas where there's a lot of gaps for these semantic cues. Like if you're driving on a highway, you're going to be very starved for cues that constrain your pose, even at like the 5 or 10 meter range along the road. Geometric alignment methods, on the other hand, rely on aligning point clouds from LiDAR or for camera or RGBD sensors into pre-built 3D HD maps. And these approaches can be very accurate because they rely on pretty robust, well-established methods. And they deal pretty well with outliers. So for example, you might be using stuff like the iterative closest point ICP algorithm or one of its many improved variants. But of course, the downside is now that you still have issues if the area you are in doesn't have a lot of interesting geometry for registration to work. And you typically have a somewhat limited convergence basin. So these things work best for online localization, not global localization. And of course, storing as well as building this 3D geometry maps can be a bit of a hassle. It can be challenging and it can be expensive. We can also cast localization as an incremental NeRF task and basically fit a new camera reading to a pre-trained neural field of our scene. And this kind of localization can be essentially done by freezing the actual reconstruction and just running the NeRF optimization process, but only performing updates on the pose of the new camera. And here the benefits are that you can now share the same representation between maybe your online map and your simulation and localization. And you also get photometrically accurate results while also you're only using cameras. But of course, in terms of costs, you're still optimizing a NeRF or a NeRF-like representation, which is more computationally demanding than other methods. and requires a fast GPU, a lot of power draw, etc. And it's still not clear whether this can beat a lot of traditional registration methods or, like feature matching when it comes to just visual odometry. LiDAR reflectance matching, on the other hand, builds a map using LiDAR intensity imagery and then matches online observations to this 2D image with simple template matching operations, like, for example, a cross-correlation operation. These methods can be much more robust and configurable than geometric ones, especially if the environment is mostly featureless. And you can also implement this kind of matching very efficiently in practice, either on a CPU or a GPU. And at the same time, just like the geometry alignment methods, the reflectance matching still requires pretty good initialization, though they are a little bit more robust to this, the width of this basin. And because you're essentially doing template matching, you can actually configure the range you're searching and adapt to areas where things are uncertain. In terms of limitations, continuing this, you still require precise LiDAR intensity calibration. So calibration for the reflectivity returns that you get in your LiDAR. And this can limit the scalability of these methods due to the relatively difficult nature of this process. However, you can overcome some of these limitations, as shown by recent work, by learning a deep feature map for matching in an end-to-end manner. So the idea here is that you pass this 2D online LiDAR sweep image and the 2D map image through two separate fully convolutional network, and then you transform them into basically calibration agnostic representations that you then use to perform the matching. And what you can do is you can actually backpropagate through this whole process by supervising with ground truth poses and optimize these neural networks for the end task of localization, which lets you learn robust and distractor-free calibration agnostic matching functions, basically. And this has been shown to outperform traditional LiDAR matching. Okay, so the methods that we've seen so far continuously update the vehicle pose over time in an online setting based on an initial nearby estimate. But the question is, how do we actually start this process? How do we actually obtain this initial pose that we keep updating in an online way? And how do we recover if your online localizer, for example, fails? And this is where global localization comes in. The idea is that global localization faces a lot of similar challenges to online localization. So we must, if we overcome them for online localization, we also overcome them for the global localization. So things like the fact that the same place could look very different under very different factors, like different weather, different lighting conditions, as well as the presence of occluders. All of these factors are things that we need to overcome when we're dealing with global localization. So let's have a look at a couple of categories for methods that we use to solve global localization. Of course, one of the most common approaches for global localization, as I hinted at earlier, is using GPS or its higher fidelity cousin RTK, a real-time kinematic system. And as we saw in the hardware section, RTK systems can leverage differential GNSS and carrier phase measurements together with IMUs to estimate the position of the vehicle with pretty darn good accuracy. So they can give you centimeter level accuracy, and they don't really require any prior knowledge or any prior map of the world. But of course, in terms of downside, these methods include relatively poor reliability if there's no GPS reception at all. For example, if you're driving through areas with long tunnels or operating indoors or in mines or whatever. At the same time, you still need to rely for RTK on the presence of base stations nearby. So the coverage might be limited. You might need to deploy new stations to do this, and you might need to purchase subscriptions for real-time access to these corrections, which increases costs. Pose regression is a completely different approach, which uses essentially supervised learning to perform global localization by training a neural network to predict the pose of an input image or an input LiDAR sweep or whatever. And these methods essentially consist of just one feed-forward pass. They are extremely fast, but there's still some evidence that they don't yet achieve as good accuracy as other approaches in very large environments. And on the other hand, if you use retrieval-based methods, they could be a little slower, and they might have higher memory requirements because, for example, you need to load up a big database in RAM, but they tend to be more accurate in really large geographical scales. But of course, you should take this with a grain of salt because we're starting to get really, really good at training and running inference in neural networks with billions and billions of parameters. So it could be possible that in the coming years, you might have POSNet-like pose regression approaches with really large neural networks that can overcome retrieval methods, the performance of retrieval-based methods, while also being conceptually simpler. There's also feature matching, of course, where instead of having just a neural network predict a pose, you detect and describe local key points, and then you do this for your training data. You build a 3D scene offline, and then when you get a new image, you try to match features from this new image explicitly to your 3D reconstruction. And more recently, it's actually becoming more common to learn the pooling of the local features into global descriptors and use these to obtain a coarse pose that you then refine with the local features that you started with. So this is what is typically referred to as this hierarchical or hybrid localization approach. And a downside of using local features is still that you need more storage in the map if you want to keep a map that contains these features. And this cost will be often, even maybe 2 or 3 orders of magnitude higher than just storing one neural network or a bunch of global vectors. But one thing to point out is that if you're interested in learning more about this, this hierarchical localization codebase from ETH Zurich is actually really great. It performs well. It's really well documented. It's beginner friendly. So if you want to kind of get your feet wet a little bit with this sort of stuff, I highly recommend it. I worked with it a little bit and had a really good experience. So with that out of the way, it's time to do a little recap. So in this session, we learned about what localization is, right? How we measure it, how we compute the ground truth, what the different types of ground truth are. And we also looked at what it means to analyze the impact of localization performance on the system as a whole. And then we, of course, went through a few approaches of both online and global localization. There are, of course, still many active areas of research in localization and in mapping for that matter, like, for example, how you can leverage multiple sensors to localize, how you can use one sensor to localize against a map that is built with another sensor, like using radar to localize against a LiDAR map, or on how to reduce reliance on prior HD maps altogether. So, all right, before we get to the complete end, yeah, I have a list of references here. We can talk about this some more, but for now we have reached the end of the tutorial. So thanks for sticking around. We'll continue with some more Q&A sessions, but for now, yeah, on behalf of everyone at Wabi and all the organizers, I'd like to thank you all for attending the tutorial and for wanting to learn more about this field that we are very passionate about. Thank you very much. And yeah, now I open the floor up for questions. I'll stick around and I can also redirect questions to some of my my coworkers if I don't know the answer. Okay, there's one on Zoom. Yeah, so the question, the first question, logistics, whether the slides will be available. I don't know about slide availability. It's not really my call, but in terms of the recording, I think the recording will be available on the CVPR platform website, where you can access all the metadata for all the sessions. You should be able to log in with your CVF account, check your email for more info. And then the recording should show up there in a week or two, depending on the organizers. And then as soon as it's allowed, we will also upload edited and cleaned up videos of the sessions from this tutorial to YouTube. Cool. Any questions in person? Yes, please.
So I'm thinking how robust are these algorithms in a situation of localization, a situation where the sensors are becoming faulty?
Yes, that's a very good question. So the question was essentially how robust is localization if there's faults in the sensors and there's issues with your readings. So I think this is an important area to study, and it's important not just for localization, right? It's the same for perception and it's same for pretty much everything. I guess there's multiple levels of faults, right? The sort of the easiest one to deal with is if the sensor itself has some sort of self-diagnostics where it can report that something is going wrong, like one of the motors or part of the optics are failing. In that case, you can start to just drop it as an input, and then you can develop a system and train it so that it, it is easy to prepare for this. Like if you're training a perception or a localization system where you're getting multiple inputs, you can just do like data augmentation where you just randomly drop one or two of the input sensors. But the problem now is, of course, if the data starts getting corrupted, what do you do? I've seen this happen, like for example, like radars lidars can get dirty, and then like part of your field of view is just permanently occluded. Depending on the method, you might be just naturally resilient to this through just robust optimization. So if you're doing, for example, template matching for lidar localization, if like a chunk of your sweep is just completely gone or gibberish, you should still be able to match reliably. And orthogonal to that, I think it's still important to have some sort of out of distribution detectors that can warn you if one of the sensors is completely, it's saying it's green, but it's actually producing complete gibberish, and react accordingly, like cutting it off or something.
How how much do you consider traditional sensor fusion approaches? Like where, you have some sort of a state that, it has some sort of a model in the background, and then it goes there, the traditional sensor fusion system is kind of the way we would like this for this sensor. This kind of traditional stuff. How much you consider, techniques like this?
Yeah, the question was about how much we use traditional sensor fusion in the literature. So do you mean specifically for localization, or just more broadly for tasks like perception and motion forecasting?
Well, I don't know, this is for localization.
Okay.
Let's go.
Yeah. So typically what I've seen used in practical system is the use of loosely coupled systems. So for example, one cool thing to check out, I've seen there's these new DARPA challenges, like for example, for like underground exploration, and they have like some really, really detailed systems papers that are really cool to read. And the way they typically do it is they basically do what you kind of describe, which is they have like multiple separate state estimation systems, maybe one that's more heavily LiDAR based and so on. And then they kind of have some sort of lightweight filter that might be fusing information in a very robust way from these submodules, such that it is able to completely recover if one of these systems fails completely, like if a sensor is damaged or whatever. And for example, if you're doing something like LiDAR matching, it's pretty common to have your LiDAR matcher produce updates that then get passed. Maybe you have like an EKF or some histogram filter, and then you do like a more traditional Bayesian update, and potentially you are getting evidence not just from your LiDAR matcher, but you might have some observations from a GPS or some visual odometry system. And then you're doing like traditional kind of probabilistic approaches where you can kind of assign high covariance to measurements that look really off.
More recent methods were actually combine both of them, actually in that, such as, traditional approaches like column filters, actually end-to-end, data-driven things, so that you learn things that you need to actually fine-tune, like in covariance and stuff like this directly
from data, yeah.
And still use the structure, from the filters to avoid faulty sensors, for example.
Yeah, I agree. That's a very promising area of research. I think you were first. Okay. Yeah. So the question is about ground truth generation for central line extraction. I'm not super familiar with that part. I think for networks that do the central line extraction, there's probably more details in their respective papers. I would imagine that you still probably want to derive it from human annotations of boundaries. I think you probably want to derive it from something that is easy to verify by humans. I think just like it's difficult for humans to label localization like trajectory ground truth, I think it's also ambiguous to just label the center line. So I would imagine they probably label something that's visible like lane markers and curbs, and then kind of derive central lines from that, but I'm not entirely sure. Depending on the method, you might still need to start with some sort of human annotated data to train your auto labeler, and then it would like run on novel data. Yeah. But in terms of what the human would need to annotate, I would imagine you want the humans to annotate stuff that's very obviously visible in your data, because that makes the annotation and then the quality assurance process more clear. Whereas otherwise it's much more ambiguous and you probably end up with worse quality labels. Yes.
I got two questions for you. So my first question
Mhm.
is, I was wondering how you generate the topological map or the bird's eye view from sensor data.
Mhm.
The second question is, are you able to calculate the change in elevation in case the car goes up or down when it's sensor?
Yeah. So sorry, can you repeat the first question?
Generating the bird's eye view.
Okay, generating the bird's eye view from this. How do you generate the bird's eye view from the sensor data? Well, if you're doing something like a LiDAR or a similar 3D sensor, then it's somewhat straightforward. You don't have to do anything too fancy. You can kind of, for example, do an orthographic projection from top down, and then you do some sort of aggregation for pixels that fall, for points that fall within the same pixel, and then you get an image. And the aggregation can be, you can do like the mean intensity, you can render the height, you can take the max intensity in your column. And then if you have camera data, it's a little more complicated, but typically there's two ways. One of them is to combine the camera data with LiDAR to get the depth information, and then you can kind of reproject it accordingly. Or you can make some assumption about the structure, the geometry of the environment. So if you assume that you're on a plane and you know the camera calibration, you can kind of compute your homography and kind of reproject the camera so that it will look top down. But then anything that violates that assumption will look extremely distorted. So you can see there's some examples where you can reproject like a monocular camera as a top-down road and it looks good. But if there's like a car that would actually stick out from that plane, it's like very distorted. So that's one way to do it. And the other one is with some better ground truth. But for LiDAR, it's more straightforward. And sorry, and then the second question?
It's about whether you can calculate the change in elevation. Let's say the car goes up.
Is this when you're building the map or when you're localizing?
That's when you're
Typically, if you're doing a three-dimensional, if you have some sort of 3D map and you're registering against it, your optimization or your registration process will almost always be 6 degrees of freedom. So you're automatically going to be solving for your XYZ, roll, pitch, yaw, all the full rigid transform anyway. So you will have your height within that environment as well. Yeah. If you're doing bird's eye view everything, like for the 2.5D matching, it's a little trickier, but you can still do it. So one way of doing this is you match like lateral, longitudinal, and yaw with the intensity imagery, and then you do another stage where you're trying to align your observation vertically. And then that will give you the altitude in the environment. Although a lot of the time what you can do is you can more or less clamp the position of the vehicle vertically, because you kind of have the calibration of the vehicle, you kind of know the height of the sensor from the ground, and you also know that the car is on the ground, so you can also infer and you know the map, so you can just figure out relative to the map where you are based on these assumptions. Yeah, you're welcome. Of course. Yeah, of course.
So I'm a student.
Mhm.
Probably I don't know the realistic settings industry. So my question is like, what maximum GPU memory you can use for truck during inference? And can your proposed foundation models such as occupancy prediction model can actually run real time?
Yeah, that's a very good question. It's a very practical question about memory requirements and compute requirements. So I cannot give specifics on the exact GPUs and the exact computers that we have. But generally speaking, there are many ways in which you can improve the efficiency of these kinds of complex models to run them on board vehicles. So for example, NVIDIA and other companies provide optimized, like specialized computers that are designed for like basically inference optimized AI accelerators, which can have quite a lot of memory, support for things like quantization of your model weights and other optimizations that can let you run relatively large models very quickly. So typically you can aim for something like between 5 and 20 hertz for inference. So if you have a bigger model, you can run it with a 200 millisecond budget that can get you pretty far. And then in terms of memory requirements, depending on the size of the model, you can, for example, quantize its weights. There's a lot of research on that. It's not always trivial, just a drop in, but you can quantize your weights, for example, to 8-bit or even lower and get pretty good results in terms of lower memory as well as faster inference. And actually, there's some recent improvements, I think, based on the latest NVIDIA architecture that they were talking about at GTC. They have this new technology for even lower precision inference. So you can do stuff like FP4 or even lower. And it actually works based on some papers that have come out that studied it theoretically so far because the GPUs aren't available yet. It looks like there's quite a lot of potential. Yeah. Yes.
So to follow up on the sensor question,
Mhm.
the sensor calibration, like there's a failure, but there's also like calibration of sensors, like intrinsic and
Mhm.
maybe even extrinsic
Mhm.
respect to each other, and maybe even with respect to the weight or
Mhm.
change over time.
Mhm.
Maybe show that the rotation matters, right? Like,
Yeah.
The calibration of sensors that affect each other intrinsically.
Yeah. That's a very good question as well. So the question is about the risk of misalignments happening over time in the field and whether it's possible to compensate for them. So yeah, this is a pretty widely, actually not widely studied, but very important area. So it definitely happens that sensor drift occurs, even if you've calibrated really well. If you're driving an autonomous vehicle or even any kind of robot through an environment for long enough, your sensor alignment will either completely drift away or because of vibrations, you will see a lot of weird artifacts. So there's many ways to do this. You can run some sort of subset of your main calibration algorithm periodically online, or you can embed some sort of resilience or corrections for this in your perception system. So I think there's some papers that do this. I think there's also a blog post from Aurora where they describe this, where for a very long distance perception, you're heavily reliant on cameras because, if you're like looking at something that's 500 meters away, you might get like 2 or 3 LiDAR points if you're lucky. But if you have a telephoto lens for a stereo array, then these objects will still be pretty visible. But then the problem is if your LiDAR is even a little bit misaligned with your cameras, everything is going to be pretty far off. So you can have a model that basically tries to actually predict a little correction between the two modalities. And then once you predict, you correct, and then you actually do the fusion. And it seems to work pretty well in practice. And once again, you can have validated data that's high quality and then train this with manual perturbations as data augmentation and learn these corrections. And actually for the paper where I talked a little bit about the analysis of the misalignment between the online data and the map, we did train a perception system that was able to self-heal basically by doing a little bit of LiDAR matching as part of the inference process. So it would try to align the feature maps, and if they were misaligned, it would figure out that they were, and they would like correct them and then run the headers. And it actually helped improve performance. It would let the model basically recover from this kind of issue. Yes, question.
Where do you see the field of autonomous driving? So what is your opinion, the biggest challenges that need to be overcome until it's more widely adopted?
Yeah, that's a very good question. It's a broader question about the big challenges in autonomous driving. I'm gonna give I guess a more academic or personal view on this. I think there's a lot of them. One of them is in terms of standards and validation. I think right now, even things like crash testing is somewhat limited. let alone like even stuff like drivers assist systems like automated braking, I think could be improved in terms of how we test them, but it's very difficult to standardize these things. So having like standardized testing, kind of like a driver test, like humans do, but for autonomous vehicles, is something that I think could help kind of make it easier for companies themselves as well as authorities and the public to compare against different kinds of autonomy software. I think this is like on one level. I think it's also important to build better simulators to maybe enable this. Having like the ability to generate very complex but realistic scenarios is very important as well. As well as developing systems that can really help with deal well with the long tail, like really weird. Like Sergio pointed out in the PNP session, it was literally the first mile that we did our internal demo on. In the first like 2 minutes, there was like a house being towed by a pickup truck. It was like all of these weird things happen all the time. So you need some way of validating this as well and having open set capabilities. Cool. No more questions on Zoom either, right? Yeah, of course. Yeah, I'm here.
You have experience building with large scale Postgres optimization, like large scale model adjustment, or for example, 100K number of images.
Yeah, that's a very good question. The question was about how to deal with large scale Postgres optimization. Personally, I haven't worked on very, very large scale PGO problems, and the stuff that I worked on with enough care would still fit on one machine. But I think there's probably some papers which deal with this. I think it's pretty tricky. I don't know if something like the series solver or G2O work in a distributed setting.
Yeah, as you build up, I tried with around 10K images and use a series solver, but then the problem that it took a couple of days or even it's not solvable. So that's why
I don't have any like practical tips from my experience, but I know in academic sources that I read, one way to do this is potentially chunk up the data into tiles, process the tiles separately, potentially having tiles with overlap, and then running some sort of subsampled postgraph optimization at the end to kind of enforce global consistency. I think that's one approach, but I don't know. In practice, I haven't used it myself, so I can't speak for whether it works that well in practice. Was there another question? No? Okay. Right. Thanks also to the people on Zoom. Thanks for asking questions. I'll stop meeting now. Ending the meeting for